Good afternoon to Ananda. Good afternoon. Please kindly confirm audio, video, and screen once. Please kindly confirm audio, video, and screen. Is it okay? Good, good. So let's continue with the calculation of critical clearing angle, what we said in the yesterday class, right? So I'm taking in the next heading, that is critical clearing angle calculation. Critical clearing angle calculation. So generally we denote this with a letter delta CR, delta suffix CR. That's a letter which we'll take for the critical clearing angle. First, I want to tell this one to you. Just listen. See, as we said earlier in this graph, particularly, if the fault is cleared a little away, means if the fault is cleared after a large amount of time or after a large angle, obviously the system will become unstable. So our aim is to know what is that angle, what is that rotor angle before which the fault has to be cleared, such that the system should be in the stable mode. Means I can say in a different words also. What is the maximum angle seen by the rotor? Maximum angle seen by the rotor before which the fault has to be cleared to make sure that the system is stable, that we are going to name as critical clearing angle. First, to write this definition, I will explain you about this by looking at the graph. Okay, yeah. So have a look here. Delta CR is the maximum angle, maximum angle seen by the rotor, before which the fault has to be cleared. Before which the fault has to be cleared. To make sure that the system is stable. Okay. To make sure that the system is stable. To make sure that the system is stable. Simple. Delta CR is a maximum angle seen by the rotor before which the fault has to be cleared to make sure that the system is stable. Yeah. So in the next slide, I will be showing that power angle curve diagram and all. Thereby, I will be asking you the question, what angle we are going to consider as delta CR. Thereafter, we'll move to some derivation. Yeah. So let's move to the next slide. Next slide. So I am showing the axis here is a delta axis, one thing, and this is a power axis. Okay, so it's a power axis I am showing, and this was of delta axis. And I will show PE1 curve, P maximum 1 sine delta. PE1 curve, it is P maximum 1 sine delta, something like this. PE1 curve. Next, what about the PE2 curve? PE2 curve will be 0. In the present case study, PE2 curve was 0. And the PE3 curve is same as PE1. So this itself is PE3, we can say. And this peak value, what we have here, peak value, that is either P maximum 1 number, or you can call this as P maximum 2 number. Sorry, 3. Either P maximum 1, or you can say that as P maximum 3. Okay, simple. So let me show the PS line here. PS line, steam input. So like this, we'll have the steam input PS line. And this is a initial operating point A, which we said earlier. That's the initial operating point A, at which the angle is delta naught. Right? This was the angle delta naught, and the speed at this point is synchronous. Speed at that point, omega is equals to omega. Yes. Look here. All of a sudden, we have a short circuit fault. After the fault has been occurred, this point A on the PE1 curve shifted to some other point, maybe B on the PE2 curve like this. So this operating point A was shifted down to this point. Okay, fine. Next. From this point onwards, we know we have acceleration. Omega will become more than omega s. d delta by dt will become positive, delta will continue to increase, but electrical power output will be remains 0. So operating point will move in this particular direction. Operating point will move in this particular direction. Now, just look here what I am saying you. This is some point C, that is some point C at which the fault was cleared, and I will call this as a clearing angle delta. It may be critical or may not be critical, that we have to decide now. At some angle the fault was cleared, I am naming the angle as clearing angle, saying that as delta C. Simple. After the fault has been cleared, simply this point C on the PE2 curve will be shifted to some other point, so-called D on the PE3 curve. Okay. So I'll say like this. So this point C, what we are having here, it was shifted to this point, so-called D on the PE3 curve. But you know, at this point D, definitely speed is more than synchronous speed, and in this zone B2C speed was increasing. Okay. I'll show a previous slide. Please wait for some time. Just listen here what I'm saying. Okay, but you see at the point D, accelerating power, that is mechanical input minus electrical output, PS minus PE, that is negative. Say as accelerating power is negative, omega starts decreasing from this point D speed. So because of that omega decrement, you know, the speed is decreasing, but still it is more than synchronous speed. D delta by dt is positive. Delta will continue to increase. So electrical power will change something like this on this curve. Okay, I am asking you one very simple question. Very simple question to you. For example, if you are getting speed is equals to synchronous speed at this location, means speed is decreasing continuously as we said, but still the speed may be greater than synchronous speed. But after touching to this point, blue color point, what we have shown, I'm getting omega equals to omega s. Omega equals to omega s. Can we call this as critical clearing angle? Tell me please. Can we call this as critical clearing angle? Tell me. No, it won't be called as critical clearing angle. Why in the sense? Because still we have some more region before touching X, right? Before touching this X point, still we have some more region. So I can say the fault need not to be cleared early at this delta C. You can clear the fault little ahead also. There is no problem for us. I think all of you getting my words, what I said. Is this clear? Okay, now tell me please. For example, I didn't touch omega equals to omega s here. Same question I am asking you, same question. For example, I am getting omega equals to omega s at this place. I'm getting omega equals to omega s at this place. Can we call this delta C as a critical clearing angle? Same question I am asking you, same question. Can we if you get omega equals to omega s at this point, can we call this as critical? No. Then also it is not going to be called as critical. Okay. For example, in this space, if you are getting omega equals to omega s at this place, can we call this delta C as a critical? Very simple question. If you are getting omega equals to omega s at this point where we have shown, can we call the delta C as critical? Yes or no? Yeah, actually, it is impossible to get omega equals to omega s at this point, right? It is impossible to get omega equals to omega s at this point. Yes or no? Before touching this X point itself, we should get omega equals to omega s. If it is not the case, you don't touch to synchronous speed at any other point further, and we will say the system is unstable. Okay, now tell me, when we are going to call this delta C as critical clearing angle means, if you are getting omega equals to omega s, exactly at this point X. Yeah, touching omega equals to omega s exactly at this point X, delta max angle I am saying, then we are going to name this particular clearing angle as critical. We are saying that as critical. All of you getting this? All of you getting this one? Please tell me. Yeah. So I can say now, so delta CR, it is a clearing angle. clearing angle for which omega equal to omega s occurs at point x. Occurs at point x. Omega equal to omega s is going to occur at point x. Okay, now I will show these areas. I'll show these areas. First area is this one. I'll say A1 area here. First area I'm naming as A1 area. And second area I am showing here this one. This area I am naming it as A2 max area. A2 max. Okay. So this A1 plus A2 max value should be equals to 0. A1 plus A2 max value should be equal to 0. Then we can say we are going to get this angle as critical clearing angle. Okay, what is this delta max angle? Anybody tell me? What is the delta max angle formula? 180 degree minus sine inverse of PS by P max 3. On which curve we are standing? Is it PE3 curve or PE1 curve? PE3 curve we are standing. The fault was already cleared. We are standing on the PE3 curve. So it will be 180 minus sine inverse of PS by P maximum 3. Very simple, very simple. Okay. See, critical clearing angle means it is an angle, maximum angle seen by the rotor before which the fault has to be cleared. Very simple thing, very simple thing. For example, in this graph, what we have shown, you take this A2 max value, A1 value exactly equal. Exactly equal. At that time, whatever the clearing angle you have, that fills as critical clearing angle. For example, if the fault is cleared above this angle, what we have calculated. For example, I will tell some number. I'll tell some number to you. This delta CR is something like 80 degree to assume 80 degree. If the fault was cleared above 80 degree, what will happen is A2 max area will come down, A1 area will go high. Means A2 max area will come less compared to A1 area and system is unstable. Clear. And if the fault was cleared before this 80 degree, maybe at 70 degree if it was cleared, at 70 degree if it was cleared, A2 max will go high, A1 is less. Then A2 max is greater compared to A1 and the system will be definitely stable. So what is it margin angle? What is it margin angle? Above which the fault clearance will cause for the system instability. For the system instability is going to be called as critical clearing angle. Is it clear? It may be. It will be definitely. Delta max will be always greater than 90 degrees. Yeah, please go through the mathematics. How you are asking me, how you have written this 180 minus sine inverse of PS by P max 3. Just to go with the mathematical term, if it's a sinusoidal signal, symmetrical angle concept. Symmetrical angle concept. Okay? Yeah. So let's continue. Let's continue. That's what I said just now, Ankur. I explained again as somebody asked here. See, I should say d delta by dt value at the point x, so called at the angle of delta max, is equal to 0. D delta by dt value at this angle of delta max is equals to 0. Means what we should say here is integral PA d delta is equals to 0. Up to what angle you should do it? Delta max. Starting from which angle? Delta naught, I can say. So starting from the angle delta naught to delta max, starting from the angle delta naught to delta max, I should take integral of PA d delta is equals to 0. But you know that accelerating power equation is not same in the throughout integration duration. First to duration, delta naught to delta CR, we have one accelerating power equation. Delta CR to delta max, we have a different accelerating power equation. That we have to take now. So I can write first one, integral delta naught to delta CR, PA d delta is one thing. Next one, integral delta CR to delta max. And here you get PA d delta, that is equals to 0. Let me write the PA equation here. PA equation. PS minus P max to sine delta during fault. PS minus P maximum to sine delta with respect to delta. Next one. After clearing the fault, delta CR to delta maximum. What is the PA? PS minus P max 3 sine delta. P maximum 3 sine delta and with respect to delta, that is equals to 0. Clear? Okay. So now you take up that integration and all, continue further, and finally we have to get the expression for the delta CR from this one. Yeah, please write it quickly. I will go with the next slide to expand that one. So I will do the integration and I will apply the limits in one step. So first term, it is PS into integration I done, and I am applying the limits here. Delta CR minus delta naught is one thing. Next one is plus Pmax to P maximum to cos delta CR minus cos delta naught. Cos delta CR minus cos delta naught. Okay. And then next you have plus PS into delta max minus delta CR. Delta max minus delta CR plus P maximum 3 into cos delta max minus cos delta CR. Cos delta max minus cos delta CR, and this number is equals to 0. That number is equal to 0. And you take that PS common here. PS common. Delta CR will be cancelled here. Delta CR will be cancelled. You will get this as delta max minus delta naught. Plus, you can write it now in expanded way, P max 2 cos delta CR minus P max 2 cos delta naught, okay, plus P maximum 3 cos delta max, P maximum 3 cos delta max minus P maximum 3 cos delta CR. P maximum 3 cos delta CR, that is equals to 0. That is equals to 0. Okay. Don't keep Pmax to 0. Don't keep Pmax to 0, even though it is 0. You extend this one. This is some sort of concluded derivation I'm making. Okay, done. See, from this, you try to write down the cos delta CR equation. Finally, I'm writing the final step here. In between that, you have to do some intermediate steps. I'm writing directly. PS into delta max minus delta naught plus P maximum 3 cos delta max minus P maximum 2 cos delta naught, P maximum 2 cos delta naught whole by P max 3 minus P max 2. P max 3 minus P max 2. Like this, you can write the cos delta CR expression. Cos delta CR expression. PS into delta max minus delta naught plus P max 3 into cos delta max minus P max 2 cos delta naught by P max 3 minus P maximum 2. This is an expression for cosine delta CR. It is an expression for the cos delta CR. After that, you have to apply cos inverse in order to get the delta CR angle. In order to get the delta CR angle, you have to apply the cos inverse. Okay, done. I think all of you getting this? Clear? Next. One small thing you have to observe here. This delta max minus delta naught, you should keep in the form of radians. This delta maximum minus delta naught angle, we have to keep in the form of radians. This we should be clear. Delta max minus delta naught, we should keep in radians. Okay, done. Next. Next thing. See, after calculating this angle, again I am saying the same words here. Again I am saying the same words. Listen please. After calculating this delta CR angle, if you move back into this waveform, sorry, this graph, I said delta CR, I got some number as 80 degree. 80 degree. The intention is very clear now. If the critical clearing angle is 80 degree, if the critical clearing angle is 80 degree, then if the fault is cleared before 80 degree, system is stable. If it is cleared above 80 degrees, system will be unstable. Who is going to clear the fault here? Who is going to clear the fault? Right? Is it the rotor which is clearing the fault? Breaker, circuit breaker, or you can say protective switch gear. Protective switch gear is a thing which is going to clear the fault, right? Yes or no? Now, that protective switch gear, what you are saying, maybe relay and circuit breaker combination, don't know about this angle. That protective switch gear don't know about this angle. What the protective switch gear knows here? Only time. operating time only it will know. So within how much time the fault has to be cleared, that we have to set for the protective switch. Okay, so the timing we have to set for the protective switch gear. That time we are going to call here is critical clearing time. Critical clearing time or critical fault clearing time also you can say. Let me write that word. After that I will try to tell the definition even more clearly. Critical clearing time. Critical clearing time. So I'll call this one TCR, or you can call critical fault clearing time. You can call this as critical fault clearing time. Fault clearing time. Critical fault clearing time. So simple. It's very simple. It is a time before which, from the instant of fault occurrence. It is a time from the instant of fault occurrence before which the fault has to be cleared to make sure that the system is stable. Okay. It is the time from the instant of short circuit, from the instant of short circuit, right? Before which the fault has to be cleared. Before which the fault has to be cleared. To make sure that the system is stable. To make sure that the system is stable. Okay. To make sure that the system is stable. Okay. Now listen. So can I say in another way? Just listen here. Yeah, you can ask me that doubt in doubt session. Anonymous attendee, you are asking about that angle, right? You asked me in the doubt session. Instant of fault cleared. What is the instant of fault cleared? It is a time from the instant of the short circuit before which the fault has to be cleared. That's the meaning. If you assume that fault is occurring at a time t equals 0, from that time t equals 0, within how much time the fault has to be cleared? That's the meaning here. Okay, see, simply from this graph, I can say TCR is nothing but the time taken for the rotor angle. To rise from delta naught to delta CR. To increase its angle from delta naught to delta CR. How much time it will take? That we are calling as critical clearing time. Okay, so TCR is a time. TCR is a time taken to rise the angle. To rise the angle from delta naught to a value delta C. Delta naught to delta C. Yeah, you please tell me now. Please tell me. See, who is going to tell about this time variation with respect to angle, or angle variation with respect to time? Who is going to tell about it? Swing equation. Okay, let's take the swing equation. What we have? Swing equation. So, you know, swing equation md square delta by dt square is equals to accelerating power. Is it possible to do integration for this? Anybody please tell me? Is it possible to do integration for this? Yes. When we can do the integration? Only if the accelerating power value was constant. Only if the accelerating power is constant, then we can do the integration for this. Let me write. If accelerating power is constant, PA is constant. Okay, then if you write the delta of T equation, already we have said that delta of T equation already we have taken. That will be 1/2 PA by M into time square plus delta naught. Half PA by M time square plus delta naught. Is it clear? Right? By assuming that fault was occurred at time t equals to 0. By assuming that the fault was occurred at time t equals to 0. Simple. See, in the span between delta naught to delta CR here, in the span of delta naught to delta CR, how is your accelerating power value? PS minus PE. PE is 0 during fault. PE is 0. So we get only PS, right? So PA value is equals to PS, we can say. PA value is equals to PS. That's it. So I can say from delta naught to delta CR, delta naught to delta CR, accelerating power is equals to PS, which is constant. Accelerating power is equals to PS, which is constant. So at time t equals to TCR, delta of TCR value will be equals to delta CR, you can say. Delta of TCR value will be equal to delta CR. So just you keep the time t equals to TCR in the equation 1 and you continue further. Yeah, let's say from equation 1, and if you keep TCR here, delta of TCR is equals to 1 by 2 PA by M TCR square plus delta naught. And this you replace with the delta CR, that you replace with delta CR, and by using this you try to get this TCR equation. TCR equation will come to be delta CR minus delta naught into 2m. Okay, so I'll write in a proper order. Try to write in a proper order. 2m into delta CR minus delta naught by accelerating power PA. 2m into delta CR minus delta naught by accelerating power PA under root, we should consider. So it will be square root of 2m into delta CR minus delta naught by accelerating power. So this is an expression for the critical clearing time. Critical clearing time, you can say. Critical clearing time. So in fact, it is a critical fault clearing time, you can call. Critical fault clearing time. Yeah, next. I'll tell in a very, very simple words further, very simple words. If the clearing time TC, say, if you want to tell clearing time, I will call simply TC. Critical clearing time means we should call it as TCR. I'll say in the next line. If clearing time clearing time TC less than critical clearing time. Tell me please. If the clearing time TC less than critical clearing time, then can I say system is stable? Then what will happen is, definitely delta C will be less than delta CR. Means if the fault is cleared within the critical clearing time value, definitely clearing angle will be less compared to critical clearing angle. If that is the case, A2 max area from the equal area criteria will be definitely greater compared to A1 area. So we don't touch the point X at all. Right? So operating point will not touch X. Operating point will not touch X. That implies system will be stable. Operating point will not touch X. That implies we can say system will be stable. Yeah, what is there? Just if I missed one square, you can write it right. Okay, fine. System will be stable. And in the other word, if you write, if the clearing time TC greater than critical clearing time, means if the fault was cleared ahead of critical clearing time. For example, if you get the critical clearing time as 0.2 seconds. 0.2 seconds. If the fault is cleared at a time of 0.25 seconds, then obviously your clearing angle delta C will be greater compared to critical clearing angle. Clearing angle delta C will be greater compared to critical clearing angle. That implies if you calculate the A2 max area from the graph, it will come definitely less compared to A1 area. Then even after touching X, we don't get omega equals to omega S. And you write simply system is unstable. System will be unstable. System will be unstable. I think all of you getting this one. Yeah, this formula we have to use only whenever accelerating power is constant. A2 max is A1 means it won't touch X. That's what I have written here, uncertainty. That's what I have written. If A2 max is greater compared to A1, it won't touch X. Before touching X itself, you get A2 magnitude equals to A1 magnitude, and the system will become unstable. Yeah, okay, fine. And again, you write, if you want this TCR formula, what we have written, it is valid only if accelerating power is constant. PA is constant from delta naught to delta CR. From the angle delta naught to delta CR. In between the delta naught and delta CR, if the accelerating power is constant, means during fault, then only it will be valid. Means the TCR equation will be valid. Okay, I'm showing the previous slide. If anybody is still writing, please complete it. 296 I am showing. 296 I am showing. Please complete it quickly. Yeah, so let's take one simple problem on this one. What would be the minimum value of delta C? What is that minimum value of delta C? Can you tell me? TC equals to TCR, then the system is marginally stable. TC equals to TCR means system is marginally stable or marginally unstable, you can say. What is the delta CR? Minimum value of delta CR, that will be decided by system. From system to system, it is going to be changed. From system to system, it will be changed. Fine. Yeah, let's continue with one more problem here. Go through this problem. It's a very simple one. Yeah. Look at this question. Look at this. So an alternator connected to infinite bus has an inertia constant of h 5 seconds. Alternator connected to infinite bus bar having an inertia constant of h equals to 5 seconds. F equals to 50 hertz. 4 poles. 4 poles. The pre-fault power angle equation is given as PE equals to 3.0 sin delta. Pre-fault power angle equation is given as PE equals to 3 sin delta. Okay. In the pre-fault condition, the electrical power transfer from the alternator to infinite bus, is 1.5 per unit. Okay. During fault, the electrical power transfer will fall down to 0. And after clearing the fault, network will be restored to the pre-fault state. Network was regained its pre-fault state. The critical clearing time is dash seconds. Critical clearing time is dash seconds. Yeah. So just look here. Very simple. So this is one alternator and it is connected to infinite bus through some network here. So I'll show some network simply like this. And this is a infinite bus. Fine. And it's a mechanical symbol. Let me show h equals to 5 seconds here. Frequency of operation 50 hertz. Frequency of operation is 50 hertz. And we have a 4-pole machine. 4-pole machine is this texting. Power angle curve equation P equals to 3 sin delta. Power angle curve equation PE is equals to 3 sin delta. 3 sin delta. Okay, done. Next, the pre-fault condition. In pre-fault condition, the electrical power transfer from alternator to infinite bus is 1.5. Okay, so initial electrical power flow is 1.5. Initial electrical power flow electrical power flow. I'll call it is PE naught here. PE naught, which is equals to 1.5 per unit. 1.5 per unit. See, if the initial electrical power flow is 1.5 per unit, then how much is the mechanical input we can say? What's the value of mechanical input? It will be same as this number, right? Because initially we don't get any acceleration as well as deceleration. So definitely initial electrical power flow in the line or in the network and steam input, both will be exactly equal, right? So therefore, steam input, PS is equals to PE naught. That implies you can write the steam input as simply 1.5 per unit. Steam input you can treat as 1.5 per unit. Good. Next. Simple. Just by looking at the question again. During fault, the electrical power transfer will fall down to 0. Means PE2 is equal 0. PE2 equals 0 means definitely I can say P maximum 2 is also 0, right? P maximum 2 value will be 0. And after clearing the fault, network was restored to the pre-fault state. Let me write the things quickly. First, pre-fault state. What is the maximum power transfer capacity in the pre-fault state? P maximum 1 is equals to 3. Next, during fault, P maximum 2 is equals to 0. During short circuit fault, maximum power transfer capacity is 0. After clearing the fault, means in the post-fault condition, P maximum 3, this number is equals to P maximum 1 we have, and this is nothing but 3. P maximum 3 is equals to P maximum 1, that is equals to 3, we can say. Next thing. Okay, what is it? Critical clearing time, TCR. Critical clearing time, TCR. What's the formula for TCR? 2m into delta CR minus delta naught by accelerating power PA. 2m into delta CR minus delta naught by accelerating power PA. We have to take the square root of this. Okay, first we should calculate what is the m value and what is the delta CR, delta naught also. What is delta naught here first? First you tell me, what is the initial rotor angle delta naught? Initial rotor angle delta naught. That is nothing but sine inverse of PS by P maximum 1. Sine inverse of PS by P maximum 1. So you can write sine inverse of PS number is 1.5. P maximum 1 is 3. So it will come to be 30 degree. Delta naught value was 30 degree. Okay, let's calculate delta CR also. Then we will come back to this equation of TCR. First tell me, is it possible to apply this equation or not? That you have to discuss first. Before writing this equation itself, is it possible to do by using this equation? Yes. Why? So means during short circuit fault, electrical power transfer is 0. During short circuit fault, the electrical power transfer is 0. So you can say accelerating power during fault, it will be PS minus PE2. PS value how much? 1.5 minus 0. This number will be 1.5. That's it. Okay. So this is accelerating power during fault. Accelerating power during fault. PA is equals to 1.5 per unit. Okay, next. Let's think about delta CR. Critical clearing angle. Just I'll say cos delta CR formula. Which is PS into delta max minus delta naught plus P maximum 3 cos delta max minus P maximum 2 cos delta naught, P max 2 cos delta naught whole by P maximum 3 minus P maximum 2. P max 3 minus P max 2. That's it. Let's take up these numbers quickly. PS is 1.5. I'll substitute. What is delta max? Formula? That is maximum angle seen by the rotor. Before which we should get omega equals to omega. Okay. So I'll say 180 degree minus sine inverse of PS by P max 3. P maximum 3. I have written this in the discussion of cos delta CR equation. Let's keep these numbers. 180 degree minus sine inverse of PS number is 1.5 and P maximum 3 is 3. So it will come to be 150 degrees. Delta max value was 150 degrees. Right. Let's substitute the numbers because I know all the things here. We keep all the numbers in this cos delta CR equation. So cos delta CR will be equals to PS 1.5 delta max 150 degree minus delta naught 30 degree into pi by 180 plus P maximum 3 cos delta max 150 degree P maximum 2 0 into cos 30 degree, that will be 0 only. P maximum 3 P maximum 2 0. You calculate this cos delta CR value. Tell me cos delta CR value first. Cos delta CR value. Yeah. Delta has to be taken in radian. That's why I have multiplied with pi by 180. This angle, what we have 180, 150 minus 30. This angle we should keep in radian. That's why I multiplied with pi by 180. Tell me how much? How much? How much? Tell me that cos delta CR value first. After that, we can find out the delta CR number. 0.18117. 0.18117. So this angle we are going to get like cos inverse of this delta CR will come as cos inverse of this number. See, anywhere if you are multiplying the angle with some other number without keeping that cosine, sine and all, right? Just we have some angle multiplied with some number as your answer. Most of the times we have to give that in the form of radians. Okay, see, this is some number for you that we are adding to some other number, and cos inverse we are applying to get the angle right. At this value, what we have, this we should keep in the form of radian for simple mathematical analysis. Yeah, tell me what is this 79.56 degree? 79.56 degree. For a proper mathematical analysis, if anywhere you are multiplying angle with some number, better you keep that in the form of radians. Else you can think in this manner also, in this manner. Completed? This is a critical clearing angle. Now you can find out the TCR value. Before going with TCR, we should be confirming what's the value of M. What's the value of M? What is PA? 1.5 per unit, right? PA value was 1.5 per unit. And M value also we have to keep in per unit. M value also we have to keep in per unit. In which units you want to keep this one? Is it in degree or radian? Let us take in degree. Listen, please, listen. If you keep this in degree, you can keep this angle directly in degrees. But strictly speaking, what you should do is delta CR minus delta naught, we have to keep in radian. M also we have to keep in radian. By that way, radian will be cancelled out. If you are not doing that, keep the angle in degree, M also in the form of degree, then the units will be cancelled out. Clear? Okay. So anyhow, I will write M in terms of radians only. M per unit. H by pi f, electrical. GH by pi f, if it is in per unit, H by pi f. It's second square by electrical radians. So what is the H number you have? H number, how much they have given? 5. Okay. By, and it is 50 pi. Second square by electrical radians. 1 by 10 pi, you are going to get it. Let me move with the TCR calculation time. 2 into M. 1 by 10 pi. Delta CR angle. What is the delta CR angle? 79.56 degree. 56 degree minus delta naught is 30 degree. You have to keep this in radian. So multiply with pi by 180 whole by accelerating power is 1.5 during short circuit fault, and you have to apply square root for this whole number. Apply square root for whole this number. How much TCR value? How much TCR? Obviously, the complete transient stability analysis we are doing by assuming system as lossless only. Anybody tell me this TCR value? Critical clearing time. Please make it quick. 0.1916 seconds. What is the meaning of this number? After the fault has been occurred, the fault has to be cleared within this much amount of time. Within this much amount of time. If you are unable to clear the fault within this much amount of time by using your protective switchgear, then definitely the system will lose synchronous. System will be losing its synchronous. Okay, so this is the value of critical clearing time. Yeah, next. If you don't remember, leave it. If you are unable to remember, leave it. This is one of the very famous formula which will be asked in many examinations. Huh? Then the people has to make the engineering as an open textbook. Then only we can do. Huh? If you are unable to remember the formula. Yeah. Let's move in the similar question. In the same question, what we are discussing. What is a critical speed? What is a critical speed value? Yes, I will tell you in a definition mode. What is the speed, maximum speed attained by the rotor? Maximum speed attained by the rotor before which the fault has to be cleared. Okay, so I'm showing in the next slide. Maximum speed attained by the rotor before which electrical radian Abhijit, electrical radian only. Same question, same as previous question, you write. Previous question, write like this. What is the maximum speed seen by the rotor? Maximum speed seen by the rotor in bracket in RPM before which the fault has to be cleared. Before which the fault has to be cleared to make sure that the system is stable. Clear? See, it's a very simple one. You have to find out the speed at an angle of delta CR. That's it. That's the critical speed actually. Critical speed means critical speed attained by the rotor means NCR you can call. It is nothing but speed at delta CR angle or speed at TCR time. Speed at TCR time. That value we have to calculate. Do you have any relationship between that speed and time? Do you have any relationship between that speed and time? You know, d omega by dt is equals to PA by M. D omega by dt is equals to PA by M. Now, this we can integrate. Again whenever this PA is constant. Whenever PA is constant, then we can integrate it. Already we have done that integration. I will write the final equation for the speed. I'll write the final equation for the speed in the next slide. Yeah, kindly go through it. In the next slide, I am saying, as PA is constant, we can do the integration. And by doing that integration, NCR or N of T better. N of T is equals to 60 by 2 pi into PA by M into time plus NS. Already we discussed about it, right? Already I have derived this one. Yes or no? Have you remembered this one? Have you remembered this? Yeah, good. See, simply you keep the time t equals to TCR in this one, thereby you are going to get it. But one thing, whatever the M we have here, that M we should keep in the form of mechanical radian because it's a mechanical term which we are calculating now. M we have to keep in mechanical radians. Okay, what is it M value? Where M should be in mechanical radian. What's the formula for M? You know, this is 2GH by omega s basically. But if you want to take this in per unit, because PA is in per unit, I'll write M in per unit form. M will be equals to 2 into H by omega S. And you can write this 2 into H by omega S is 2 pi ns by 60. 2 pi ns by 60 in the mechanical radians. In the mechanical radians, let us substitute the numbers here. 2h. H is 5 seconds. Okay. 2 pi ns. What's the synchronous speed? What's the synchronous speed? How many number of poles given for the machine here? It's a 4-pole machine, right? 4-pole machine means synchronous speed will come to be 1500 rpm. 120 f by p. 120 f by p. It will come to be 1500 rpm. So I'll keep 1500 here by 60. 2 pi ns by 60. Okay. To calculate this value, it will come in the form of second square by mechanical radians. Second square by mechanical radians. Yeah. Now you go with the PA by M also if you want. Else I can say 10 and 60, 600 in the numerator. Denominator you have 2 pi into 1500. So 0 zeros will be cancelled. 6 by and it is 30 pi. And it's 1 by 5 pi, I think. 1 by 5 pi. It will be in second square by mechanical radians. That we can substitute in that and we'll get the critical speed. So this is one of the untapped area. This is one of the untapped area of getting the value of speed, critical speed calculation. So now you write at the time t equals to TCR, critical speed NCR is equals to, critical speed NCR equals to 60 by 2 pi into accelerating power is 1.5 by M 1 by 5 pi PA by M. Okay, multiplied with time. What is the critical clearing time we have? Critical clearing time is 0.1916. 1916 plus what's the synchronous speed? 1500 RPM we have to add. This is in RPM plus 1500. How much is that? How much is that? 1586. Is it? Kindly cross check that. How much is the speed? 1543. Somebody is saying. Okay, 1543. 1543 RPM. Many people are getting this one. 1543 RPM. That's the speed. Critical speed or speed attained by the rotor. Speed attained by the rotor before which the fault has to be cleared. This is a way of understanding. At the instant of the short circuit, rotor speed is 1500. Rotor speed is 1500. From that time onwards, speed starts increasing. Speed starts increasing. Before this speed touches 1543, before this speed touches 1543, the fault should be cleared. If you are unable to clear it, definitely system will become unstable. Okay? Yeah. Fine. So I'm showing the previous slide. Showing the previous slide. So in the view of the system stability, I can say whether the system is stable or unstable in various ways. One way of saying that is, we should clear the fault before critical clearing time. Or else, we should clear the fault before touching the critical clearing angle. Or else, we should clear the fault before touching the critical speed. All these three will simultaneously happen. Means if the fault is cleared before touching the critical speed, I will say definitely it was cleared before critical clearing time. And it was cleared before critical clearing angle. And we will say A2 max is greater compared to A1. We don't touch the point X, and obviously the system will be stable. System will be stable. Yeah. So this is the end of that second case study. You should not call this as a maximum speed imtiaj. It's not the maximum speed imtiaj. Because in the backswing, you may get a speed more than this also. It means in the second swing, strictly. Okay, let's continue. Let's continue as in the case 3. Case 3. Just turn your pages in your notebook. Just look at the case 3, what we have given. Look at the case 3, what we have given. Case 3. A 3-phase short circuit fault. 3-phase short circuit fault at midpoint of one of the line in parallel line system. Parallel line system. Of course, in SMIV, the single machine connected to infinite bus bar. Single machine connected to infinite bus bar system. We have a three-phase short circuit fault at the midpoint of one of the line. So I am showing something like this. We have a generator, and these are two lines running in parallel, and at the end you have that infinite bus. This is the infinite bus. Okay, and this is a mechanical input. I am showing it is PS, and these are the breakers I am showing, circuit breakers, I can say. Circuit breakers like this. Done. Next thing. So as we have already studied the previous case study and all, we have some idea already. That's why I'll take directly the fault at this midpoint of line. F is a location of fault. F is a location of fault. Now I will say like this. I have three states of operations. One, pre-fault. Next, during fault. Next, post-fault. Okay, PE1, PE2, PE3. All the three curves definitions I will tell. I will draw the three curves. Then I will start with the initial conditions of our system. Okay, yeah, I'll show in the next slide. Pre-fault, electrical power output during pre-fault condition. PE1 is a curve name, which is P maximum 1 sine delta. Next, during fault. During fault, I can say it is PE2, P maximum 2 sine delta. Next, after clearing fault, in the sense, it is post fault, PE3. This is nothing but P max 3 sine delta. P maximum 3 sine delta. Okay, PE1 is P maximum 1 sine delta, PE2, P maximum 2 sine delta, PE3, P maximum 3 sine delta. And if you compare these P max 1, 2, 3 numbers, already we have done one problem, right? By taking fault at midpoint of line, we have done one problem. Yes or no? Right. If you take up this comparison between these three P maximum values, P max 1 will come highest number. Then you get P maximum 3. Lowest number we will get for P maximum. Lowest number we are going to get for the P maximum. So during short circuit fault, we are going to get the lowest value of maximum power transfer capacity. Lowest value of maximum power transfer capacity. Now, I'll show the three curves, but you have to understand now that P maximum 2 value is non-zero. P maximum 2 number is non-zero. We will get some number. We'll get some number, non-zero number, but that's the lowest peak compared to the remaining two. Let me show the three curves first in the power angle curve plot. P versus delta plot. So I'm showing here, this is the delta axis. I'm showing it's a power axis. Power axis. Observe now. First, PE1 curve, P maximum 1 sine delta. PE1 curve, P maximum 1 sine delta. Next, PE2 curve. PE2 curve. We'll get something like this, PE2 curve. Okay, so this is PE2 curve. All are sinusoidal signals only. All are sinusoidal signals only. 0 point will occur for the three curves at the same point. Peak value, maximum value will occur for all the three curves at 90 degree only. Again, 0 value will occur at 180 degree only. Okay, all the three curves will touch to the peak power at 90 degree because it is simply a power angle curve, P maximum into sine delta curve. Okay, yeah. So next PE3 curve, I will show something like this. So this is the PE3 curve we are calling post-fault power angle curve PE3. PE1 curve pre-fault. During fault, we are saying it is PE2. After clearing fault, we are saying that as PE3 curve. PE3 curve. Yeah, let me show these indications in this graph. It is P maximum 1. And this is P maximum 2. Sorry, 3. P max 3 it is. And this is P maximum 2 we have. P maximum 2. P max 2. Okay, done. Next, I have to show the PS line, mechanical input. At some point, I am setting first PS line. After that, I will tell you the variations. After that, I will tell you the variations. First, I will set the PS value or PS line at some place here. Look here. So this is the location of PS. This is the location of PS. Stream input PS. Next thing. Whatever the intersection point you have between the PS line and PE1 curve, PS line and PE1 curve, that intersection point we are calling as initial operating point A, at which you know the angle is delta naught. At which we have an angle of delta naught. Clear? Let me write those initial conditions and all further. Initial conditions I am going to write in the further slide. Okay, next slide I will take up and I will write the initial conditions. Else here I will write better. Initial conditions. Similar to the previous case study. Rotor angle is delta naught. And then rotor speed omega is equals to omega s, you can say. Rotor speed omega is equals to omega s, we can say. Next one. I'll say steam input is PS, constant, of course. Steam input is equals to PS, that is constant. And if you think about the electrical power output, that is nothing but the value of P1 at this delta naught angle. That is nothing but P1 at an angle of delta naught. So I can continue with this. P1 is P maximum 1 sine delta naught, you can say. But you know, in this initial operating time, mechanical input as well as electrical power output both are exactly equal. So PS is equals to P maximum 1 sine delta naught. From this, you are capable to get this delta naught angle. From this, we are capable to get the delta naught angle. So I'll write in the next slide. Delta naught is nothing but sine inverse of PS by P maximum 1. Sine inverse of PS by P max 1. That's the angle delta naught, we can say. Okay, what are the disturbance we are talking now? All of you listen here. It is similar to the previous case study as it. What are the disturbance we are talking now? Fault at the point F shown in the figure, midpoint of line. Okay, as and when we have a fault at the point F, instantaneously there is no change in the rotor speed, as well as there is no change in the rotor angle, right? So I'll write it disturbance here. Disturbance is nothing but three-phase fault at point F. Okay, and you write now, there won't be any instantaneous change. In the rotor speed. Change in rotor speed and rotor angle. There won't be any instantaneous change in the rotor speed and rotor angle. In bracket, you write due to inertia. Just after the fault occurrence. Fault occurrence. Okay, done. Just after the fault occurrence, you don't have any instantaneous change in the rotor speed as well as the rotor angle. But what it will be changed here instantaneously after the fault occurrence? What value was changed instantaneously after fault occurrence? Anybody? Anybody tell me what value was changed instantaneously? Maximum power transfer capacity. Maximum power transfer capacity was suddenly changed from P maximum 1 to P maximum 2. Accordingly, electrical power output will change from P max 1 sin delta naught to a number P maximum 2 sin delta naught. Right? But the network was disturbed. Network was disturbed. So P max, maximum power transfer capacity, changed from P max 1 to P max 2. Changed from P maximum 1 to P maximum 2 suddenly. Maximum power transfer capacity value was changed from the value of P max 1 to P maximum 2 suddenly. So because of this, I can say that implies electrical power changes from P max 1 sin delta naught, P maximum 1 sin delta naught to a number, I'll say P maximum 2 sin delta naught. It changes suddenly from P maximum 1 sin delta naught to P maximum 2 sin delta naught. So I will show that in the graph. So all of a sudden, whatever the operating point A we said, that is shifted to this PE2 curve as point B. Simply this point A was shifted to point B as P maximum to sin delta naught output. Clear? P maximum to sin delta naught output. So you can write it. You can write that also. That implies point A on PE1 curve, on the PE1 curve, shifted to point B on PE2 curve. Shifted to point B on the PE2 curve. Fine. Next thing. Next thing. I've shown the previous slide. Please complete it if you are still writing. Tell me, at the point B, where we are standing, how is the accelerating for PA? How is the accelerating for PA? PS minus P maximum to sin delta naught. Electrical power was falling down. So PS minus PE, that is positive. PS minus PE, that is positive. So omega starts increasing from omega S. Omega starts increasing from omega S means omega will become definitely more than omega S. Then d delta by dt will turn to positive. Delta starts increasing from delta naught. Delta starts increasing from delta naught. Okay, let's continue. Let's continue like this. So at point B, just after fault occurrence, you write in bracket. Just after fault occurrence. Just after fault occurrence. Okay. Rotor angle will be remains at delta naught only. Rotor angle will be remains at delta naught only. Rotor speed, again, omega is equals to omega S. Omega is equals to omega S. But if we calculate the accelerating for PA, which is mechanical input PS minus electrical output right now is P maximum to sin delta naught. Right? Mechanical input is PS and electrical power output is P maximum to sin delta naught. And this number is positive. That number is positive. Means we can say d omega by dt is positive. Omega starts increase from omega S. Yes, first you write simply d omega by dt number is positive. But what is the value of d delta by dt at this B? Anybody tell me what is d delta by dt at this point B? Anybody? D delta by dt. That will be 0, right? That will be 0 right now. That will be 0. Now what we should write further is from B onwards, from the point B onwards, as d omega by dt positive, omega starts increasing. Omega will become more than omega S. If that is the case, d delta by dt will turn to positive. Delta starts increasing. We have to come. Okay. So I will say in the next slide again. Next slide. Right. From point B onwards. Just look from point B onwards. Omega increases from omega s. Omega greater than omega s occurs. Means we can call d delta by dt, which is omega minus omega s value, that will turn to positive. That implies you can say delta increases from delta naught angle. Delta value will increase from delta naught angle. So now these things I will try to show in the graph. Delta increasing from delta naught. Yeah, I'll show in the next slide. Means in the previous graph slide. Just observe now. So delta is increasing from delta naught, something like this. Means obviously the operating point will be moving on the PE2 curve. Operating point will be moving on the PE2 curve, something like this. And in this region, in this whole region, PS minus PA, that is positive. PS minus PE, that is positive. Then definitely, as PS minus PE is positive, and obviously accelerating power is positive, and omega is increasing in this zone, and omega is more than omega s, d delta by dt is positive, delta will continue to increase. Okay. See, if the fault was not cleared, let's say if the fault was not cleared, simply you observe that this PS minus PE. PE curve is below PS, right? PE curve is PE2 curve. PE2 curve is below PS. All the time, mechanical input minus electrical power output is positive. All the time it is positive. So PA is positive means all the time d omega by dt is positive. Omega will continue to increase and it's always more than synchronous speed. D delta by dt positive. Delta will continue to increase and system will become definitely unstable for this particular scenario, for this particular graph, what we have shown here. Okay. Yeah. Let me write it. If the fault was not cleared, then always accelerating power PA is equals to positive. So always d omega by dt is positive. Omega will increase. Omega greater than omega s. D delta by dt is positive. So delta will continue to increase towards infinite. Delta increases continuously and the system is unstable. System will be unstable. Okay, delta increases continuously and we can say the system will be unstable here. System will be unstable. So I think all of you getting this one? Fault was not clear, then always PA is positive, d omega by dt positive. Omega will continue to increase and the system will be unstable. Yeah. So this is one end of stability actually. This is one end of stability. You keep it in bracket and keep it aside. For example, if the fault was cleared at some point, then we should investigate whether the system will become stable or unstable. Okay. So let's show here. At some point, see, I am showing here at this place. This is the point. See, I am showing, right? And this angle I am saying as clearing angle delta C. Fault clearing angle delta C. Fault was cleared. So within that time, B to C observe, and omega is continuously increasing because accelerating power is positive and omega is more than omega s. Okay. One thing I want to show in the next slide here. Next slide. Let's assume that the fault was cleared at. Let's assume that the fault was cleared at point C, right? Set the point C, we'll say that the fault was cleared. Next. So that implies operating point operating point C on PE2 curve, point C on PE2 curve will be shifted to point D on PE3 curve. Shifted to point D on PE3 curve. Okay, will be shifted to point D on the PE3 curve. Yeah, have a look here. So I can say this is simply moved on to this location D. Moved on to this location D. Like this. Okay. Now at that point D, or first you write from B to C. B to C during fault I will write first. B to C I will write during fault. After that we'll take after clearing the fault. Okay. In bracket you write it is during fault, during short circuit fault. Next, what will happen to accelerating power during short circuit fault? Accelerating power during short circuit fault is PS minus P maximum to sine delta, right? PS minus P maximum to sine delta. That number is positive. That number is positive. Means obviously you can call d omega by dt number is positive. D omega by dt number is positive means omega was increasing in that zone. And you know omega is greater than omega is. And if you calculate the value of d delta by dt, that is positive. So delta value was increasing in that zone, you can see. Delta value was increasing in that zone. Delta value was increasing in that zone. Simple, simple. Same thing I have explained earlier that I am writing in words for your understanding, Next, I can say a fault was cleared at point C this side, and point C was moved to that point D on the PE3 curve. Now I will write at that point D. At point D in the next slide. At point D, I can say at point D. Observe at point D. For the rotor angle, what's the rotor angle at point D? Delta C. Delta C. And already you know speed is more than synchronous speed at D. At the point D, we know the rotor angle as delta C, as well as omega is greater than omega s. Omega is greater than omega s. Okay, just look here. See, what is accelerating power at D? What is accelerating power at D? In this particular case, PS minus PE3. PS minus PE3, that is turning to negative, right? Accelerating power at D is negative means d omega by dt is negative. It is expected that omega starts decreasing. Omega starts decreasing from this point D onwards. Omega starts decreasing from this point D onwards. Means the thing what you have to observe now is B to C, omega is increasing. Omega is increasing. C to D, no change in the speed. From D onwards, speed starts decreasing. From D onwards, speed starts decreasing. Means I can say that at the point D, or you can say point C, we might have reached to maximum speed. We might have reached the maximum speed. So I can call here omega touch to omega max. Omega touch to omega max. Okay, next, let's continue. What is accelerating power just now we said? It is PS minus, fault was cleared just now. So P max 3 is a maximum power transfer capacity, sign, angle will be remains same. But this number is negative. So as it is the case, d omega by dt number is negative. Not only that, what is d delta by dt? D delta by dt. Omega minus omega is. Already we said omega is more than omega is at this location, and this number is positive. D omega by dt value negative, d delta by dt value yeah. So d delta by dt value positive we can see. Done. Next. From D onwards, in the similar way, what we have studied earlier, analysis will be same. From D onwards, omega starts decreasing. From where? Omega starts decreasing from where? Omega max. Omega starts decreasing from omega max but still omega greater than omega s we have. That implies d delta by dt is still positive. You can say delta value was increasing. Delta value was increasing. Okay, delta will increase up to what location? Delta value will increase up to what location? Up to the time whenever we have d delta by dt is 0. Clear? Or up to the time whenever we touch omega equals to omega s, up to that location only delta increment is going to happen. So delta increases up to the point where omega equals to omega s will occur. And who is going to decide whether you are going to get that omega equals to omega s or not? Who is going to decide whether we are going to get that omega equals to omega s or not? Yeah, tell me please. Who is going to decide whether that omega is going to touch omega s or not? Areas. What's the area already we have covered? What's the area we have already covered? That's the area in between delta naught and delta c. Delta naught and delta c. Okay, that's one limit. Other limit is PS line. Next one is PE2 curve. Whatever the gap between these curves, what we said, that's the accelerating area which we are going to call. Because in that zone, PA is positive. That's why the speed was increased up to that point, what we said. Right? So I will be showing that area here. I will be showing that area. So this is the accelerating area. Calling this as A1. This area we are calling as A1. And whatever the next area we are going to cover now, from D onwards, whatever the next area we are going to cover now, if that area was matched with A2, A1, then I can say that the system will be stable. Okay, maybe I can say from D onwards, it will move in this manner because omega is more than omega s, but still the speed is decreasing because PA is negative, right? PA is negative, that's why speed is decreasing. And at some point, maybe here, after reaching here, point E, I will show point E. I got both areas is equal. After touching to this point E, angle is delta 1, I will say delta 1. After touching to that point E, we got this area, what we have covered freshly, A2, matched with A1. Our integral of PA d delta coming 0. Integral of PA d delta is coming 0. Okay, so let me highlight this area. This is that second area we are covering just. Second area we are covering, and we are touching omega equals to omega s at this particular point E. At that particular point E, we are touching omega equals to omega s. Clear? Equal areas. So I'll write in the next slide. So I'll say let by reaching to point E, integral of PA d delta equal to 0 occurred. That implies, you can say, omega equals to omega s occurred at point E. At that point E, we are touching that speed is equals to synchronous speed. Correct, Dinesh. Correct. If you understood one what we call case study clearly, then it will be same repetition. Conditions will change little bit. That's it. Yeah, fine. Next thing, make it quick. So I can say from the point D to E after clearing the fault. From the point D to E after clearing the fault. So you can write accelerating power formula here. Mechanical input is PS and electrical power output is P maximum to sine delta. Ps minus P maximum to sine delta, that number is negative, right? Negative. And you know, d omega by dt value was negative here. D omega by dt value was negative, right? So I'll write here. D omega by dt value was negative. And you know, the speed was decreasing here. Omega value was decreasing. But still omega is greater than omega s. Omega greater than omega s. And you know the value of d delta by dt, which is omega minus omega s, that is positive. Positive. Delta value was increasing in that zone. Delta value was increasing in that zone. Okay, so now you write at the point E, we will get omega equals to omega s. We get omega equals to omega s. And you write, if you want, d delta by dt at that angle delta 1. We have considered that angle as delta 1, right? Delta 1. Okay. At that angle delta 1 is equals to 0. D delta by dt at that angle delta 1 is equals to 0. It's P max 3. I'm sorry. After clearing the fault lines, it is P maximum 3. P max 3. Maximum power transfer capacity was changed to P max. So d delta by dt at an angle of delta 1 is 0 means we should say integral of PA d delta equals 0. Integral of PA d delta equals 0. At what angle we have to consider delta 1? Up to delta 1. Starting from where? Delta naught we have to say. So I'll write now. I'll write integral PA d delta is equals to 0 up to delta 1 angle starting from delta naught. Starting from delta naught. Delta naught. So again, you divide this into two parts. One is a pre-fault case, sorry, during fault case. Next one is a post-fault case. So I can rewrite this integration into two parts. First part is from delta naught to delta C PA d delta. Second part is from delta C to delta 1 PA d delta is equal to 0. Okay, but PA equation is different in both cases. First case, accelerating power equation is during fault Ps minus P maximum to sine delta. Second case, Ps minus P maximum to sine delta. So first case you can call delta naught to delta C Ps minus P max to sine delta with respect to delta, you can say, plus second case delta C to delta 1 Ps minus P maximum 3 sine delta with respect to delta equal to 0. With respect to delta equal to 0. Clear? Ps minus P maximum 2 sine delta in the first case. Second case, it is Ps minus P maximum 3 sine delta. So the first area what we have here, we are going to call as acceleration area A1. Second area we are going to name as deacceleration area. I'll call it is A2. First area we are calling as acceleration area A1. Second area we are going to name it as deacceleration area A2. And you can call A1 plus A2 is equals to 0. A1 plus A2 is equals to 0. Else you can write A2 is equals to minus A1 and magnitude of A2 is equals to magnitude of A1. Magnitude of A2 is equals to magnitude of A1. Okay. I think all of you getting this one. A1 plus A2 is equal to 0. A2 is equals to minus A1. Magnitude of that A2 area is equals to magnitude of A1 area. So can we confirm that the system is stable? Can we confirm that the system is stable by stopping here? Can we stop our analysis here itself? Yes or no? Yes, definitely the system will be stable, provided that there is no second disturbance. Provided that there is no second disturbance. This is what we said earlier as equal area criteria study is a type of first swing stability study. First swing stability study. Yeah, let's move. Let's move in the next slide. I'll write like this. The system is transiently stable. System is transiently stable provided that there is no second disturbance. Provided that there is no second disturbance. Provided that there is no second disturbance. Okay, provided that there is no second disturbance. And one more thing I want to tell you, whatever the point E we have, this is not the final stable point. Means the operating point will not stop at location E, what we said. Why it is so means, even though you are saying you are touched omega equals to omega s at E, but accelerating power is non-zero at that place. Accelerating power is non-zero. So the rotor will not stop finally at the location E. It will oscillate further. It will oscillate further, right? So I can say, but point E is not the final stable point. Final stable point to be expected. Final stable point to be expected. But point E is not the final stable point to be expected. Good. So to know where that rotor is going to stop finally and all, we have to extend this study as a backswing in the similar way. Backswing we should take, and we have to take between what points the rotor is continuously oscillating and what will be the final stable angle by considering the damping. And then you should check how the delta versus time curve will be, similarly omega versus time curve. Okay. So can I move ahead to the next slide to take up the backswing? Yeah, yes. So which curve we should take in the backswing? Anybody? First, let me write the statement in the backswing. Before drawing the power angle curve and all, let me write the statement in the backswing. Simple. At point E, where we have stopped the analysis, of the forward swing, where we have stopped the analysis of forward swing, at point E, accelerating power is still negative. Okay, so that implies from E onwards, from the point E onwards, omega decreases, and omega less than omega s will occur. From E onwards, omega decreases further, because up to that point it is decreasing already, and omega will decrease further, and omega less than omega s will occur. And that implies you can say d delta by dt will turn to negative number. That implies delta starts decreasing from point E. From that point E onwards. From that point E onwards, delta starts decreasing, we can say. Delta starts decreasing. Yeah, many of you are giving the answer. Which curve we should consider now? Only PE3 curve we have to consider. Okay, again, you will be getting a doubt. Sir, in the first case, you said it is coming from A to B, B to C, C to D, and then D to E. Why you are not going to trace the same thing? Why you are not going to trace the same thing in the backswing? Why? In the sense, why you are moving from A to B? Because of fault occurrence. Why you are moving from C to D? Because of fault clearance. After the fault was cleared, the operating point will stay only on the PE3 curve. Operating point will stay only on the PE3 curve. So oscillations will occur only on the PE3 curve, I am going to say. Okay, let me copy this thing. Just observe. Only PE3 curve we have to consider. I no need to consider the PE1 curve here. I'm removing that PE1 curve. PE1 curve I am removing. And I am removing the PE2 curve also. Right. Yeah. Next thing. So let me copy that previous one also once. That delta. the previous power angle curves which we have shown, that also I am copying just for the sake of reference, right? Just for the sake of reference, I am copying these things, these curves, previous analysis curves like this. Okay. Done. So this is P3. This P max 3, of course, you have here. P maximum 3 we have. Look here, please. Look here. You know PS line, mechanical input PS line. I'm showing here. This is a PS line, I think. Let's quickly. This is a PS line. And what is the point at which we have stopped our study? We stopped our study is E. This is the point E. We are saying at which you know omega is equals to omega S. Angle will be delta 1 and you will have omega equals to omega S. Omega equals to omega. Okay, let's continue. Yeah, I am showing the previous slide. If anybody still want to write, please complete it quickly. Previous slide. Yeah, so let's continue. So as I said just now, at E we have omega equals to omega S, but you know PA is negative. As PA is negative, d delta by d omega by dt is negative. Omega will be less than omega S. D delta by dt negative means delta will decrease like this. Delta will decrease. If the delta is decreasing in that manner, electrical power will change on this curve like this. Electrical power will be changing on this curve. So by that way, you can say omega is decreasing in this zone and it is less than omega S. Less than omega S. So d delta by dt is negative. Delta will continue to decrease in this way. Delta will continue to decrease in this way. But you know, at some point here, maybe this one, I'll call it F. Calling it is F. At that point F, we are touching to accelerating power equals to 0. At the point F, we are touching to accelerating power equals to 0. Let us call this angle delta F for some time. I'm calling that angle as delta F. Okay, next. Listen. But you know, even though you are having accelerating power is 0 here, but still the speed is less than synchronous speed, right? Speed is still less than synchronous speed. If that's the case, d delta by dt is negative. Delta will continue to decrease below the value of delta. Delta will continue to decrease below the value of delta F. See, as and when the delta is falling below delta F, you know the operating point is moving into a region where accelerating power is positive and omega will start increase now. Omega will start increase, but it won't catch up the synchronous speed instantaneously. It won't catch up the synchronous speed instantaneously. It will take some time. Okay, within that time, omega is continue to increase, but still omega is less than omega S. But still omega is less than omega S. Okay, so omega continue to increase, omega less than omega S. At some point, you may touch omega equals to omega S. And I am identifying that point something like this here. G. G is a point at which we are touching omega equals to omega S. Will that operating point will move into negative angle region or will it stop in the positive angle region? That will be decided. That will be decided by the first area what we have. So this is the area we have, right? This is the area we have. I am showing this portion, highlighting this portion. Kindly observe. So this area is A3 area we have. A3 area. This area is A3. And whatever the next area to be covered, A4, it should be matched with the area A3. So this is the area A4 I am calling. Area A4 we are calling. And that might be matched exactly with A3. So I'm calling this is a point G at which we might be touching omega equals to omega s. Let me call this angle as delta 2. We are getting omega equals to omega s. And at delta 1 also we are getting omega equals to omega s. Yeah, one thing I want to make you clear, some people might have a confusion like this. In this particular graphs, whatever we are discussing, listen all of you once. Listen all of you. In the graphs, whatever we are discussing, y-axis is representing power. Y-axis representing power. X-axis is representing the angle. X-axis representing the angle. There is no axis representing speed. No axis here representing the speed. But according to our what we call understanding, we are keeping speed at each and every location. At each and every location, we are saying how much is the speed, how is the speed variation. That we are indicating on the figure. But no axis here. X-axis, delta axis, y-axis is a power axis. There is no omega axis in this graph. Omega axis in this graph. Okay, fine. Next. Let me write quickly. What is the speed at F? You can say now. What is the speed at F? Less than synchronous speed is okay. Can we call minimum? Anybody? Can we call this as minimum? Yes. So we can call the speed at this location as minimum. Why it is so means E to F it is decreasing. From F onwards it starts increasing. It starts increasing. Okay. Yeah. So if you want, I will write these things quickly. That's your wish. Backswing. E to F. Accelerating power is negative. Omega value decreasing. Omega is less than omega s. Delta was decreasing in that zone. That's it. Sufficient. Okay. At F. Accelerating power is 0. Accelerating power is 0. Omega is equals to omega minimum. Omega is equals to omega minimum. Next one. From F onwards. Delta will decrease. Why it is so means omega less than omega s. Omega less than omega s at F. That's why from F onwards, delta will start decreasing further. As and when delta is decreasing, delta will become less than delta 1. Delta will become less than delta 1. PA becomes positive. So omega starts increase, but it won't catch up the synchronous speed. But still omega less than omega s. From F to G, from the point F to point G, how is the accelerating power? How is the accelerating power from point F to point G? Positive. Omega value increasing. And you know, omega less than omega s. Delta was decreasing in that zone. And finally at G, point G, we are touching omega equals to omega s. But still the accelerating power is positive. From G onwards, from point G onwards, what you can say? Omega increases from omega s. And omega greater than omega s will occur. Delta starts increasing from delta 2. Delta starts increasing from delta 2. Delta starts increasing from delta 2. Yeah, if you want, you write these things quickly, what I have shown on the board. Delta increases from delta 2 means the swing will go from G towards E now, and comes back to G, goes back to E. So the rotor will be continuously swinging in between these 2 points, E and G. Rotor will be swinging in between the points E and G continuously with respect to time. Yeah. So once if you have completed, please let me know. I will move to the next slide. Once if you have completed, please let me know. I will move to next slide. So I can say in the next slide, the rotor will be continuously swinging. Rotor will be continuously swinging. Rotor will be continuously swinging in between the points, E and G. E and G. In between the points E and G. So, already at the point E and G, we have omega equals to omega s. So, always, as we said earlier, the rotor will be swinging in between 2 points at which you have omega equals to omega s. At the end points, always you have omega equals to omega s. Okay, let's continue. The back swing should be also. For example, if the damping is considered means we have some frictional loss and all. At that point, definitely these points E and G will come close together swing by swing. Maybe in the next swing, it may not touch E. Before touching to that E, maybe E1, at which you get omega equals to omega s. In the back swing, it may not touch G. At some point G1, you will get omega equals to omega s. Again, in the other swing, it may not touch E1, it may touch E2, at which you get omega equals to omega s. Again G2. Means I can say these points E and G will come close together swing by swing with respect to time. And finally, both will be inclined onto the point F, we can see. Okay? Yeah. So I'll write here. If damping is considered, damping is considered, the operating points E and G will come close together, swing by swing with respect to time, will come close together, swing by swing with respect to time, and finally inclined onto point F. Inclined onto the point F, you can see. Okay, and the speed at point F here. The speed at this point F, kindly observe. How is the speed at F? Speed at this point F. In the back swing, you have minimum speed. In the forward swing, you can touch maximum. Again, minimum, maximum. Means the speed at the point F is continuously changing between minimum and maximum values. And finally, we are going to get that omega equals to omega s at the point F. Okay? At F, rotor speed varies between omega minimum and omega maximum. And finally, omega equals to omega s will occur. Omega equal to omega s will occur. Finally, at some time you will touch omega equals to omega s. Okay, so finally at that point F, what we are talking. At this point F, what we are talking. Omega is equals to omega s. Means you call d delta by dt value as 0 and accelerating power equals to 0. So I can say d omega by dt is equals to 0. D omega by dt value also equals to 0. Okay, very simple question I am asking you. Very simple question. I will show the previous slide. I'll show the previous slides. This one. Just listen. Disturbance occurred, means fault occurred. From point A, we have moved to B. And at C, fault was cleared. We have jumped to D. And we have some deceleration. At point E, we touch the speed equals to synchronous. And the rotor will be oscillating. See, anybody observe that? Anybody observe that? The accelerating power value will become 0 at only one point. Anybody observe that? Accelerating power value will become 0 at only one point in the swinging. In the swinging zone, starting from the E to G, can we say that PA is equals to 0 occurs at only one point? Yes or no? Right? At only one point. That is at F. That is at F. So see, you have a possibility. You have a possibility of getting accelerating power equals 0 at only one point. At that point, F, what we are saying now, if speed is equals to synchronous speed also occurs. If speed is equals to synchronous speed also occurs, then I can say that the rotor will be standing at that point finally. Okay, so without doing that complete analysis also, I can guess what might be our stable point. What might be our stable point if the system is stable? If the system is stable. Is it clear? Right? So finally, we reach to steady state. System reaches to steady state. System reaches to steady state. After reaching to steady state, what value we have to check? What is the final stable angle now? What is the final stable angle? Delta F, right? What is the delta F angle? Simple. Sine inverse of PS by P maximum 3. Sine inverse of PS by P maximum 3. Clear? Sine inverse of PS by P maximum 3. It's a final stable angle. Final stable angle. Final stable angle. Yeah, tell me now. After reaching to steady state, what we have to check? After reaching to steady state, what we have to check now? dP by d delta. dP by d delta. Could you please tell me what is dP by d delta at this point F? Positive. Because this point F is on the rising portion of the power angle curve. Rising portion of the power angle curve. So finally, at F location, as dP by d delta is greater than 0, system is stable under steady state. System is stable under steady state. Under steady state. System is stable under steady state. Clear? dP by d delta greater than 0, and we can say the system is stable under steady state. Fine. Next, draw the delta versus time curve, swing curve, expected or approximate swing curve, you can say. Delta versus time curve. Swing curve. Swing curve. So I'll show first here time axis, and it's a delta axis here. Time axis and delta axis, like this you can say. And this is a time t0 at which we are getting the disturbance. Time t0 at which we are getting the disturbance. We call it is simply instant of disturbance. Instant of disturbance. Okay. Instant of disturbance, the time t0. Yeah, already I said you have to observe these angles while you are drawing the delta versus time curve. As you are drawing the delta versus time curve, these are the things you have to observe. What is your initial angle? What is the maximum angle seen by the rotor? What is the minimum angle seen by the rotor? What is the final stable angle? These are the 4 things I will be asking you to observe. I will say delta naught here. Some angle, delta naught at this place. Delta naught at this place. Next thing. How is the maximum angle seen by the rotor? Maximum angle seen by the rotor in this swinging. Please kindly understand my words. In the present analysis, what is the maximum angle seen by the rotor? That is delta 1. That's it. That is delta 1. That is not the value 180 minus sine inverse of PS by P max 3 what we have written earlier. Following all of you. So maximum angle seen by the rotor in the present swinging, in the present stability study is the value delta 1. Okay. So I'll say it is delta 1. What is the minimum angle seen by the rotor? What is the minimum angle seen by the rotor? Anybody? Tell me please. In the backswing graph, you observe that the minimum angle seen is delta 2 and that is positive. Delta 2, moreover, it is positive. How is the final stable angle? How is the final stable angle? Just observe now. How is the final stable angle? Delta F here. For example, if you want to show this F point, listen please. If you want to show this F point in the PE2 curve, if you want to show the F point in the PE2 curve, this is the point to be expected now. This is the point to be expected. And this is delta F. Delta F location. Of course, you observe that delta F angle is greater compared to delta naught. Delta F angle is greater compared to delta naught. So the final stable angle is greater compared to the initial stable angle. This is one observation we have to make. Okay? Yeah, fine. Simple, simple. Now I'll take the delta max line first. Showing the delta max line, something like this. Okay, and then delta minimum line, I am showing something like this. Delta minimum line is here, and delta final angle line is somewhere here. Final angle line. So what you do simply is, you start from this delta naught angle, reach up to the maximum, then come back to the minimum and make some oscillation, and finally it will be settling down to delta F location. That's it. So it is a delta F angle, final stable angle, and it is a delta maximum angle, and this is a delta minimum angle. Delta minimum angle. So I can say this angle will rise up to maximum and comes back to minimum like this, then goes up, comes down like this, and it will be making oscillations. And finally it will be staying at delta F. Finally it will be staying at delta F. That's what we are saying as final stable angle. Final stable angle. Simple. Don't think what is the point A, what is the point B, what is the point. Doesn't matter. Simple. What is the initial angle? What is the maximum angle seen? What's the minimum angle seen? What is the final stable angle? That's it. Just to plot the approximate swing curve. Approximate swing curve. Approximate swing curve. Okay. Next thing. Omega versus time you attempt. Speed curve. Omega versus time curve. Omega versus time curve. So you can call it a speed curve. Omega versus time curve, or you can say it's a speed curve. So I'm showing now it's a time axis, and it is omega speed axis. I'll show omega, and this is time axis, and this is a time t0 at which we are getting the disturbance, time t0, and you call it the instant of disturbance simply. Instant of disturbance. Instant of disturbance. Right. So I will show the speed up to the time t0 will be omega s only. Speed up to the time t0 is omega s. Like this we have omega s. Speed up to the time t0 is omega s. Next. I'll show some maximum and minimum speeds, as we said, right? Speed is increasing up to some maximum value and coming back. Let's say points again here for our understanding clearly. This is a point A, B. Both are having same speed as we are at the initial stage, AB, both are having same speed. Next. Tell me please. Tell me. B2C speed is increasing. That's it. B2C speed is increasing like this. Point C. Next one. CD both are same. D2E speed is decreasing, reaches back to synchronous. C, D both are same, but D2 that point E, D2E speed is decreasing and reaching back to synchronous speed, something like this. This is the point. Next one observe. E, okay, E to F minimum speed, F to G omega s. E to F, we are touching to minimum speed, something like this. Underneath is reaching back to synchronous. At G. E to F minimum, F to G synchronous. Next, tell me. All of you concentrate here. G to F, what will happen to speed? G to F, what will happen to speed? In the next swing, we might be talking here. G to F, what will happen to speed? Will it increase or decrease? Increase. Okay, increases. How is that second omega max compared to first omega max? How is that second omega maximum value compared to first omega maximum? Anybody? Greater. Why it is so means areas comparison again. In the similar way, what we have done earlier. A2 and A1 are equal. A3 is more than A2. A3 is more than A2. Yes. So A3 is more than A2. So definitely A4 is more than A2. A4 more than A1. So the first acceleration is less. Second acceleration is more. In that perspective, definitely we will be touching a speed higher than the previous omega max. This is the point at F. Then again, from the point onwards, it will oscillate and finally it will settle down to synchronous speed simply. So from this point onwards, it will come down like this and it may make some oscillations in this manner. Okay, and finally you will get omega equals to omega s. Finally, you will be touching omega equals to omega s, and these endpoints will be F, at which the speed is continuously changing between maximum, the minimum values. Endpoints will be F, at which we are touching omega equals to omega. Omega equals to omega s, finally. Max and min changing, and finally you get omega equals to omega s at the location F. Speed curve, I will say omega versus time. Yeah. So next, let's continue with the next slide. I'm taking different discussion now. Kindly go through it. So I'm showing this one, this forward swing, which we have drawn earlier. I will make some little modification to that. Observe now. For example, after touching to this point E, we didn't touch the omega equals to omega s. Assume like that. Assume that you are not getting omega equals to omega s even after touching that point E, what we have shown there. Okay? See, listen. Again, same question. What is a point which we should not cross? In the sense, what is a point before which we should touch to omega equals to omega s to make sure that the system is stable. To make sure that the system is stable. Yeah, to make sure that the system is stable. Before touching which point, we should get omega equals to omega s. You are saying point x, that's okay, point x. Where is the point x here? Where is the point x? That is nothing but the second intersection between the P3 curve and PS line. Means this is the point x which we should not cross. This is the point X which we should not cross. And this we are denoting something like delta max. It is 180 degree minus, anybody tell me this angle? 180 degree minus sine inverse of PS by P maximum 3. PS by P maximum 3. Simple. 180 degree minus the final stable angle expected. 180 minus the final stable angle expected, delta F. 180 minus delta F is this angle. Okay. So before touching to this angle at this point X, we should get omega equals to omega S to make sure that the system has stable. Clear? Yeah. So I will write that statement. The maximum angle seen by the rotor, maximum angle seen by the rotor, before which omega equals to omega S shall occur. Omega equals to omega S shall occur. Will be 180 degree minus sine inverse of PS by P max. 180 degree minus sine inverse of PS by P maximum. -180 minus sine inverse of PS by P maximum. Yeah, so I think all of you getting this one? Tell me. Next thing. I will ask you one very simple question. In the previous case, maybe this one. Observe here in this one. 1 minute. Yeah, this one. What is the maximum angle seen by the rotor in the swinging? In these graphs, I am asking you, what is the maximum angle seen by the rotor in these graphs? Delta 1, that's it. Delta 1 is a maximum angle seen by the rotor in these graphs. Look here the statement. The point X which we are saying all the time is this one. Point X is this one. See, the maximum angle seen by the rotor in the swinging should not be more than this angle, I can say. Should not be more than this angle. 180 degree minus sine inverse of PS by P max 3 to make sure that the system is stable. All of you getting my words? Please tell me, all of you getting my words? Maximum angle seen by the rotor in the swinging. Should not be more than 180 degree minus sine inverse of PS by P max 3. If it is crossing this angle, definitely system will lose the synchronism and we will say it is unstable. Clear? So always in the examination, if they say simply, maximum angle seen by the rotor in the present swinging is some angle, let's say some 120 degree, 150 degree, like that they give. We should not say that angle is equals to 180 minus sine inverse of PS by P max 3. That's what my intention to tell you. Maximum angle seen by the rotor may or may not be equals to that one. It should be less than that. 180 minus sine inverse of PS by P max 3 to make sure that the system is stable. I don't know whether you have understood this or not. Is it clear? Are you clear about this, what I said? Okay. Fine. So let's show the present slide which we are discussing now. Please identify this one. This whole area what we have now, I will name it as A2 max. I'm naming this whole area as A2 max. And this is the area A1. Then simple question I am asking. A2 max value greater than A1. A2 max value greater than A1. What you say? System is stable or unstable? Yeah. System will be stable. Can we touch X? Can we touch the point X? Can we touch the point X? No, we don't touch the point X. Before touching X itself, at some point you get omega equals to omega S, A2 equals to A1. The rotor will swing back, system is stable. That's it. That's it. Next one. Listen, please. Next one. If A2 max is less than A1, A2 max is less than A1, then what we will say? System is unstable. Even after touching the X, still the speed is more than synchronous speed and the system will be unstable, you can see. Clear? Now, who is going to decide? Same question. Who is going to decide this A2 max area and A1 areas? Who is going to decide this A2 max area and A1 areas? Anybody? Anybody tell me? Who is going to decide that? That is going to be decided by definitely delta C angle. One factor is delta C angle. See, other than, listen, other than, okay, we'll discuss about delta C angle. Later on, we'll discuss about the remaining factors also. Delta C angle right now. So again, what is the maximum angle seen by the rotor? Listen to my words. What is the maximum angle seen by the rotor before which the fault should be cleared? Before which the fault should be cleared to make sure that the system is stable. That we are going to call as critical clearing angle. Critical clearing angle. So that we are attempting to calculate now. Same derivation which we have done earlier, that we will be writing up to some extent. So the next heading in this is critical clearing angle calculation. Critical clearing angle calculation. Delta CR. Okay, very simple. Today only we have explained about this one. I'm copying this graph. Okay. Here. And this is the delta max angle. We are saying 180 minus sine inverse of PS by P maximum 3. 180 minus sine inverse of PS by P maximum 3. See, for example, if you are getting omega equals to omega S. Omega equals to omega S. Exactly at this point X. Exactly at this point X, if you are touching omega equals to omega S. That particular clearing angle we are going to name as critical. That clearing angle we are going to name it as critical. Okay. Critical. And delta CR is a critical clearing angle or clearing angle for which delta CR is the clearing angle. Same definition we have written earlier also. Clearing angle for which omega equals to omega S occurs at point X. Occurs at the point X. So I can say d delta by dt value at this delta max angle is 0. D delta by dt value at the delta max is 0. So we write simply integral of TA d delta starting from delta naught to delta maximum equals to 0. Yeah, please draw it quickly. Please draw this one quickly. So I can say integral of PA d delta is equals to 0. Up to delta max, you should do the integration starting from delta naught. So I can say this like integral delta naught to delta CR PA d delta. What is that PA equation? PS minus P maximum to sine delta during fault. Next, integral delta CR to delta maximum PA d delta, that is PS minus P maximum 3 sine delta. PS minus P maximum 3 sine delta with respect to delta is equals to 0. Okay, so you take up this integration which you have done just now today at the beginning slides. And finally, you can get the cos delta CR equation as PS into delta max minus delta naught plus P maximum 3 cos delta max minus P maximum 2 cos delta naught. P maximum 2 cos delta naught whole by P maximum 3 minus P maximum 2 whole by P max 3 minus P max 2. That's it. This is the equation to be expected for the cos delta CR. Cos delta CR. Same equation. Same type of system. Rosemary, we are discussing before how much angle we should clear the fault to make sure that the system is stable, right? That we are discussing now. So this is a delta CR angle before which we should clear the fault. For the same case study, we are discussing all these things. Of course, this angle delta maximum minus delta naught we should keep in radians. This angle delta max minus delta naught we should keep in radians. What is the critical clearing time before which the fault has to be cleared by the breaker? Critical clearing time. Critical clearing time, TCR. It's a time before which the fault should be cleared by the breakers or by the protective switchgear. So we have already derived some formula for TCR. 2m into delta CR minus delta naught by accelerating power PA under root square root of 2m into delta CR minus delta naught by accelerating power PA. Can we use this one? Critical angle, what is your doubt, Guravakan Satish? Please tell me. No, we can't use this equation because accelerating power is not constant. This equation can't be used. TCR equation can't be used. Can't be used because accelerating power PA is not constant with respect to time. Is not constant with respect to time. Not constant with respect to time, or not constant in delta naught to delta CR duration. The delta naught to delta CR duration means during short circuit fault that accelerating power is not a constant value, not a constant value. Yeah. Fine. So this is one of the drawback of equal area criteria. Definitely, this is one of the drawback of the equal area criteria. Let me list out now. Let me list out what are the various disadvantages of equal area criteria. Okay, see, one main advantage what we are getting is within very less amount of time by calculating the areas after the disturbance has been occurred, we are confirmed to say whether the system is stable or unstable. That's one of the easiest or one of the advantage we are getting with the equal area criteria. But along with the advantage, we are going to get many disadvantages also. Many disadvantages also. Tell me, what are the disadvantages? First disadvantage is we can't do this equal area criteria if you consider the damping. Right? We can do the equal area criteria only for an undamped system. That's one thing. Next disadvantage is TCR value, so-called critical clearing time, can't be calculated for any case study, what you say. Right? TCR can be calculated only for reserved case studies. Okay? TCR can't be calculated always. Next disadvantage is swing curve can't be constructed. We can't plot the swing curve. Delta versus time curve can't be constructed. Okay? Yeah. Let me write here. Let me write disadvantages of equal area criteria. Disadvantages of equal area criteria. First one, it can be applied. It can be applicable only by neglecting damping. Only by neglecting damping. If you neglect the damping, then only we can apply this method. One thing. Second one. It can be applicable only for SMIB. For a multi-machine system, we can't apply this, right? It can't be applicable for a multi-machine system. Can't be applied on multi-machine system. Applied on multi-machine system. Multi-machine system. Okay. Third one. TCR, critical clearing time, can't be calculated in all cases. Calculated in all cases. TCR can't be calculated in all cases. And swing curve can't be constructed. Swing curve can't be constructed. Can't be constructed. So these are various disadvantages you can get with the equal area criteria. At swing curve, you know about y-axis numbers, but you don't know about x-axis, right? In the swing curve, what you have constructed here, the swing curve, what you have constructed, you know about y-axis numbers, delta minimum, delta f, delta max, delta naught, you know, but you don't know how much time it is taking to rise from delta naught to delta maximum. We are not clear about x-axis. So it's an expected swing curve. It's an expected swing curve what we have done. Strictly speaking, by equal area criteria, it is not possible to construct the swing curve. Okay. So after break, I will be discussing some variations here, some variations with respect to different quantities. Pmax1, Pmax2, Pmax3, Ps. With respect to these things, how the stability is going to be decided. That I am going to discuss. After that, I will introduce one term to you, that is a transient stability limit. Transient stability limit. That term I will introduce, and I will define it, and I will take up that value for the previous case studies also what we have discussed. Okay, then we'll do one problem. We'll move to the next case. Okay, so have a break for 10 minutes. 10 minutes break. Okay. I have resumed the audio video on screen. So I have resumed the audio video on screen. Please kindly confirm. Please kindly confirm once. Yeah. So I will be moving to the next slide. Let's take. Yeah. See, so I am drawing the power angle curves, PE1, PE2, PE3 curves, what we are discussing till now. Let us say, for example, so it was the delta axis we have, and it's a power axis, delta axis and power axis here. First I am showing PE1 curve, which is P maximum 1 sine delta, P maximum 1 sine delta, PE1 curve. Showing something like this, PE1 curve, P maximum 1 sine delta. And then PE2 curve, P maximum 2 sine delta, I am showing something like this. Is PE2 curve, P maximum 2 sine delta curve. And then PE3 curve, that is P maximum 3 sine delta. So I'm showing something like this. Okay, this value was P maximum 1 number, and this peak is P maximum 3 number, and this is P maximum 2 number, P maximum 2 number. See, here we are going to discuss about system stability with respect to PS variation. System stability with respect to PS value variation. Okay, very simple, very simple. Listen please, listen please. For example, if the PS value means PS mechanical input line is something like this. Look all of you. This is a PS line I have shown you. This is the PS line I have shown. Kindly observe my words. It is a PS line I have shown. See the intersection between the PE1 curve and PS. Intersection between PS1 line, PS1 and PE, that is this point A we are talking. Okay? Fault occurred. Fault occurred means this point A was shifted down to this point as B on the PE2 curve. It's a movement we are saying. Operating point A on the PE1 curve was moved down to the point B. And we have an acceleration. Omega will become more than omega s. D delta by dt is positive. Delta will start increase. And operating point will move in this manner. So I can say operating point will be going in this way. Okay. And at this point, fault was not clear. Kindly understand. Fault was not clear. But still, we are touching a point C where accelerating power is 0, right? We are touching a point C where we have accelerating power 0. See, in the range B to C, omega value was increased and it is more than synchronous speed. Omega value was increased and it is more than synchronous speed. And you observe now, beyond this point C, at C, omega more than omega s means d delta by dt is positive. Delta will continue to increase like this. Means electrical power will change like this. And accelerating power, PS minus PE, that will become negative. Omega starts decreasing. And there may be a chance to say, before reaching this point, maybe X here, right? Before reaching to this point, definitely at some point, you may get omega equals to omega s. That chance is there. And the system may be stable. Even though the fault was not clear. All of you getting my point? Just look the statement what I am going to say. If PS value means mechanical input value is less or better in reverse way I have to write. If maximum power transfer capacity during short circuit fault is greater compared to PS. If maximum power transfer capacity is greater compared to PS value, then what we can say? The system may be stable. System may be stable even though the fault was not cleared. System may be stable even though the fault was not cleared. Okay, the system may be stable even though the fault was not cleared. Even though the fault was not cleared. So if the P maximum 2 value was greater compared to PS value, then the system may be stable even though the fault was not cleared. All of you getting me? All of you getting? Okay. So next case. It's conclusion number 1 you take. You want conclusion number 1 you take, and I will show in the next slide conclusion number 2. Conclusion number 2 in the next slide. Yeah. Say I will show the power angle curves here: PE1 curve, PE2 curve, and PE3 curve. So power and delta axis we have power axis, and this delta axis we have. Let me show. It's a PE1 curve, which is P maximum 1 sine delta like this, and PE2 curve, PE1 curve, so called P maximum 1 sine delta curve, and this is a PE2 curve. I am showing something like this PE2 curve, and then PE3 curve is something like this. I can say PE3 curve we have something like that. So it's a P maximum 1 number, and you know it is P maximum 2 number, and this is P maximum 3 number, P maximum 3. Okay, done. Next, listen please. For example, the PS value, I am showing at some place, maybe here. The PS value I am showing at some place here. Just observe my words. PS value I am showing here. So this is a PS value. And let me show the initial operating point here. Initial operating point will be this one, A. Between PS line and PE1 curve intersection, there's a point A. Fault occurred. All of a sudden, this point A will be falling onto this one, B. So this point A was fallen down onto the point B. But you know, at B, accelerating power is positive. So omega will become more than omega s. D delta by dt will become positive. Delta will increase. So operating point will move something like this. For example, fault was cleared at some time. Amount of time. Yeah, just look the case studies in the different way. Just look here. So fault was cleared at this point C, and this point C will be moved on to this point D, obviously. This is a point D. And how is the speed at D? More than synchronous speed. Because B to C speed was increased. Then definitely at D also we have speed is more than synchronous speed. And how is PA at this point D? Still positive. In the sense, as PA is positive, omega will further increase. And it is already more than synchronous speed, and it will continue to increase. And angle will continue to increase, and operating point will move down something like this. And always, you know, PS minus PE number is positive, and omega was continue to increase, and system will become unstable. So what is the comment you should make now? If P maximum 3 value, it is less compared to PS. The value of P maximum 3 is less compared to PS. Then the system will be remains unstable, even though the fault was cleared. Even though you clear the fault, still the system will be unstable because you don't have a chance of getting the deacceleration region. Okay, if Pmax is less than PS, then the system will be unstable, even though the fault was cleared. fault was, even though the fault was cleared, the system will be unstable. Okay, let me tell you one more thing here. In the previous slide, I am going to show in the previous slide. Just observe in the previous slide. For example, if this P maximum 2 value less than PS, fault is not cleared. If the P maximum 2 value less than PS, means your PS line may be something like this. I will show. Your PS line is something like this. Okay, if the fault was not cleared, as we have said earlier, the system will be definitely unstable, right? System will be definitely unstable. All of you getting my words? You need to repeat it. I'm repeating that, kindly observe. If the PS line is little ahead, then what I can say is P maximum 2, what we have here, it is lower compared to PS. P maximum 2 is lower compared to PS. At that time, if the fault was not cleared, then the system will be unstable. Is it correct or not? Yeah, I am writing that statement in the case 1 itself. If the value of P maximum 2, it is less compared to PS, the system will be unstable if the fault was not cleared. System will be unstable if the fault was not cleared. If the fault was not cleared. Okay? Fault was not cleared. Now, for example, if P max 2 is equals to PS, P maximum 2 is equal to PS. Fault not cleared, right? By the breaker. Fault was not cleared. That's a heading you can feel, and you can continue with this conclusions in the case. I'm repeating the terms now. If the P maximum 2 value is equals to PS, fault was not cleared. Tell me whether the system is stable or unstable. Then also unstable, right? Then also we can say it is unstable. All of you getting this word? Right? Yeah. So I can say here P maximum 2 less than or equals to PS. Then the system will be definitely unstable. Less than or equals to PS, then the system will be unstable. Yeah. So simple. For example, if you keep your PS line as P max 2 line only, fault occurred, the point will move on to PE2 curve, and we have an acceleration. It may touch a point where accelerating power is 0. But still omega is more than omega is there. d delta by dt is positive. Delta will continue to increase. Again, it will enter into acceleration region. Following all of you, if the P maximum 2 value and PS values are exactly equal, the operating point will touch to one point where accelerating power is 0. From that point onwards, again accelerating power is positive. Omega will continue to increase and system will be unstable for the fault not cleared case. Clear. Next one. The second case what we are discussing here is fault cleared. Next, tell me. P maximum 3 less than PS, then the system will be unstable. For example, if P maximum 3 is equals to PS, P maximum 3 and PS values are equal, what will happen? Fault cleared. System is stable or unstable? P maximum 3 value is equals to PS. Then tell me whether the system is stable or unstable. Again, unstable only, right? What will happen? For example, this is your PS line. P maximum 3 line itself is PS line. Fault cleared, and it will jump to the PE3 curve. It will touch a point where accelerating power is 0. Beyond that, again accelerating power is positive. Omega will continue to increase and system will be unstable. So P maximum 3 less than or equals to PS. Even though the fault was cleared, the system will be unstable. So can we say now? The initial loading on the system. Kindly listen. Initial loading on the system, PS value, is one of the factor on which the system stability will be depending. Initial loading, PS, initial power flow in the network is one of the factor on which the system stability is depending. Yes. Other than this PS value, P maximum 1 number, P maximum 2 number, P maximum 3 number. All these 3 numbers will decide the system stability. Okay. So I will say in the next slide, transient stability of the system. Transient stability of system depends on PS, R is a initial power flow. Okay, next one. P maximum 1, maximum power transfer capacity 1, maximum power transfer capacity 2, maximum power transfer capacity 2, as well as the next one, maximum power transfer capacity 3. Okay, these four numbers, which is going to decide the system stability, transient stability of the system. So I think all of you clear at this point. Okay. Next thing. I'll show that graph, that delta CR graph what we have shown. This one. I will copy this and I will tell you what I'm going to say exactly in this. Very simple discussion. Just look here, all of you. It won't come back to the initial conditions. Vishnu, just you look that previous final stable angle and initial stable angle. That will tell you the answer for your question. Yeah, kindly observe here. See, to have a good stability for the system, all of you listen here. To have a good stability for the system, A2 max magnitude should be higher, A1 magnitude should be lower. Is it correct or not? From equilibrium criteria? To have good stability, good transient stability, magnitude of A1 should be low, magnitude of A2 max should be high. Will you accept this statement? Yes or no? Yes. Yes or no? Just if you look at the graphs, if you talk with respect to graphs, that's it. Only with respect to graphs. A1 value should be low in magnitude, A2 max should be high in magnitude. See, very simple. If you move this PS line, just have a look here. If you move this PS line down, what will happen to A1? If you move the PS line down, what will happen to A1? Decreases. A1 area decreases. What will happen to A2 max area? Increases. A1 area decreasing, A2 max area increasing. Then can we say for lower values of PS, the system will have high stability? For lower values of PS, the system will have high stability. Yes or no? Yeah? Simple, very simple thing, very simple. So if your initial operating power flow is very low, then we can say the system stability will be very high. Good stability we can experience. Yeah. Okay. Next thing. Very simple again. How should be the value of P maximum 2? Look my words, please. How should be the value of P maximum 2 to have a good stability? How should be the value of P maximum 2 to have a good stability? It should be low or high? P maximum 2. It should be low or high? Again, you are saying low. It should be high. High value of P maximum 2 is required. Why it is so means, if P maximum 2 is going high and your curve will be shifted something like this, right? I'm drawing here. Your PE2 curve will be shifted something like this. Yes or no? If P max 2 is high, PE2 curve will be shifted like that. and A1 area will come down. A2 max is remain same. If A1 area is coming down, definitely system stability will be improved. System stability will be improved. All of you getting this word? Okay, next. So P maximum 2 should be high. That I will write. Higher value of P maximum 2. Higher value of P max 2 will lead to good stability. Next one tell me. How should be the value of P max 3 to have good stability? How should be the value of P maximum 3 to have good stability? Yeah. Tell me please. How should be the value of P maximum 3 to have good stability? Again high. Again high. Why? In the sense, if you make this P maximum 3 as high, P maximum 3 as high, definitely your A2 max will grow, and definitely we can say system stability will be more. So higher value of P max 3 also one of the way of having good stability. How should be P maximum 1? How should be the value of P maximum 1? If that is also high, then we can say system stability will be high, definitely. Because if it is high, your initial rotor angle will be less, right? So we can say higher value of P maximum 1. P maximum 1. See, simply, if the power angle curve peak values, P maximum 1, P maximum 2, P maximum 3, if these values are large in numbers, definitely system stability is going to be improved, we can say. System stability is going to be improved. Okay? Yeah. Next. So these are some conclusions. In the view of the system stability here. Next, I am copying the same diagram to the next slide to define the transient stability limit. Anyway, first let me write that heading. After that, I will copy this diagram. Transient stability limit. Shortly, we will call this as TSL. Shortly, I am calling that as TSL. Transient stability limit, TSL. Yeah. Next thing. Well, actually, stability limit, maybe in case of steady state also we have discussed. Same term we are repeating now here. Stability limit is a type of power limit actually. Stability limit, it's a type of power limit. It is the highest amount of power. Flowing in the network, right? For which the system will not lose synchronism with respect to a large disturbance. It is called as transient stability limit. For a small disturbance, we will call it as steady state stability limit. Okay, so I am writing now. TSL is the highest amount of power flow in the network. TSL is the highest amount of power flow in the network for which the system does not lose synchronism with respect to a large disturbance. With respect to a large disturbance. Yeah. With respect to a large disturbance, we can say. TSL is the highest amount of power flow in the network for which the system does not lose a synchronism with respect to a large disturbance. Okay, next step. I will be showing this delta CR curve. Delta CR curve to you. This one. Very simple, very simple. Exactly at this point X where you are standing, so-called delta max angle, we are touching that speed as synchronous. We are touching that speed as synchronous at this point X. At that point X. Okay. Yeah, A1 will decrease. A1 will decrease if the Pmax 1 is high. Look, all of you. Somebody is asking about Pmaximum 1. For example, in this curve, if your PE is something like this, let us say. P1 is something like this. Then this is your initial operating point, and it will fall down. And it is moving on this curve. It is moving on this curve, but A1 is increasing. Okay. But what about this delta CR? It will come down, right? Delta CR, critical clearing angle, will come down definitely. And with respect to that, we are saying the system stability will be good. Okay, all of you getting this one? Critical clearing angle will change now. Critical clearing angle will change. Yeah. So let's continue. Let's continue with this. Look here. Look at this statement. TSL is the highest amount of power flowing in the network. For which the system does not lose the synchronism with respect to a large distance. Okay. This is a marginally stable condition. It's a marginally stable or marginally unstable condition. Could you please tell me among these numbers, P maximum 1, P maximum 3, PS, P maximum 2. Among these 4 numbers, which value is going to be called as TSL? Which value is going to be called as TSL? Please tell me, which value is going to be called as TSL? Highest amount of power flow in the network. Highest amount of power flowing in the network for which the system will not lose the synchronism for a given large disturbance. Yeah, I'll tell you. Please listen. Very simple. I'll give some numbers to you. P maximum 1, let us say this number is some 500 megawatt. And P maximum 3, I am saying it is some 350 megawatt. And PS number, I am saying it is 200 megawatts. And P maximum 2 is some 100 megawatts. Just observe my words. P maximum 1, 500. P maximum 3, 350. PS value 200. P maximum 2 is 100 megawatts. See, right now, this is the system what we are discussing. Okay, so these are some breakers associated here. Tell me, very simple. No fault on the system. Nothing. No fault on the system, nothing. What is the power flowing in the network? Anybody tell me? No fault on the system. What is the power flowing in the network? What is the power flow in the network? 500. How it is 500? Power flowing in the network? Huh? What is the value of power flow in the network? All of you saying 500. Why? 500 is the maximum power transfer capacity of the network. How much is the power flow in the network? 200 megawatt, right? Kamala, why Pmax 3 came here? Why Pmax 3 came? Very simple question. Just I have given all the graphs here. What I'm asking you simply, how much is the power flowing in the network before the fault has been occurred? 200 megawatt. Maximum power transfer capacity of network in that period is 500. Okay. So power flow in the network is 200 megawatt only right now. Right. Okay. Now listen here. Listen. Very simple. With respect to this 200 megawatt power flow, what we are having in the system, we got a fault on the network. Fault was cleared at some angle delta C. After the fault has been cleared, we know we can say Operating point will be shifted to the point D and the system is stable. Almost. The system will be almost stable and we are getting omega equals to omega s exactly at x in our theoretical study. But practically speaking, you may not touch x. Before reaching to x itself, you will get omega equals to omega s and the rotor will swing back and we can say the system will be stable simply. All of you getting my words? All of you getting my words? Okay. Now, same system. Rather than 200 megawatts, if I have a power flow of 250 megawatts, let's say. If I have a power flow of 250 megawatts, then PS line will go up. PS line, what we have here, this will go up. Whenever PS line is going up, definitely A2 max will come down. A2 max will come down. Then we will touch X at which you get omega greater than omega S and system will be unstable. Yeah. I don't know whether you are following this or not. Please tell me. For 200 megawatt, system is stable. Okay. I am taking 250 megawatt power flow initially. Before the fault occurrence, power flow in the network is 250 megawatt, for which the system will become definitely unstable. Definitely unstable. That's what I said, this PS variation. PS variation. This is a PS 200 megawatt line, right? And if you make this PS line 250 megawatt line, 250 megawatt line, something like this, if you make, then obviously A2 max area is coming down and definitely the system will lose the synchronism. Is this clear now? Is this clear? Yeah. Yeah, good. Now, if I make this power flow, let us say 180 megawatt. If I make this power flow, let's say 180 megawatt. Now we tell me, 180 megawatt is a power flow. 180 megawatt is a power flow now. Tell me whether the system is stable or unstable. System is stable or unstable? Yes, definitely system is stable because A2 max is increasing. A2 max is increasing, system will be stable. Yeah, stable. Now the question is very simple here. Question is very simple. What is the highest amount of power flow in the network? What is the highest amount of power flow in the network? For which the system should not lose the synchronism for a given disturbance or for a given large disturbance. What is the power flow we have here? That is nothing but the value of PS. Means for this example, what we are studying now, if the power flow in the network is more than 200 megawatt, and if the same disturbance occurred, same clearance, system will be unstable. Right? If the power flow in the network is less than 200 megawatt, same disturbance occurred, same clearance, system will be stable. So what we are going to call the 200 megawatt power flow now? That we are going to call as stability limit. We are going to call it as stability limit, which we are going to call as transient stability limit. Is it clear at least now? Okay. Clear? So in this particular graph, this PS value what we have here is going to be called as transient stability limit, TSL. Transient stability limit. Okay. If you are clear about this one, I will ask one simple question to you again. Tell me, in this graph, we are getting omega equals to omega s at the point E, and the rotor operating point is falling back like this and making some oscillations. Can we call this PS as PSL? Very simple question. Can we call this PS as PSL? Yes or no? Yes or no? No. It is not the value of PSL. Why in the sense? For this power flow PS, system is stable. That's okay. But If the power flow is even higher than this number, system will be stable, right? If the power flow is even higher than this number, then also the system will be stable. So this is not the stability limit. This is not the highest amount of power flow in the network for which the system will not lose a synchronism. Even though the power flow in the network is higher than this PS value, still the system will be stable. Still the system will be stable. All of you getting this word? Yeah, good Manish. TSL will be higher than PS. TSL will be higher than this PS value. Okay, next one. Just for a cross check. Can we call this PS as TSL? All of you. Can we call this PS as TSL? Better, I will show here. This PS as TSL, can we call? Yes or no? Yes, definitely. Right? This PS, we can call it as TSL. Because if the power flow is higher than this number, it will be unstable. If it is lower than this number for the same disturbance, same clearance, it will be stable. Okay, I'll show the previous case study graphs also once. Just go through it. 1 minute, please. I'll show the previous graphs also. Yeah, can we call this PS as TSL? In the previous case study, I'm going. Can we call this PS as TSL? Yes. Dinesh, why no? Because you are getting the omega equals to omega s at this corner point x, right? If you are getting omega equals to omega s at this corner point x, A2 max and A1 are equal. This is the highest amount of power flow accepted by the system without losing the synchronism for a given large disturbance. So this PS can also be called as PSL. Okay. Yeah. One last question for confirmation. Can we call this PS as TSL? Just for confirmation. No. It is not going to be called as TSL value. So I think all of you getting the exact meaning of the TSL here. Let's continue with the present case study now. Okay, have a look at this one. So what is steady state stability limit of this network? Means in the pre-fault condition only you should say. In the pre-fault condition, what is steady state stability limit of the network? The PS for TSL X should have omega equals to omega s. Correct. Tell me please, what is the steady state stability limit? 500 megawatt, or you can say P maximum 1. So for this network, pre-fault condition only we should say without disturbance. Triple L is P maximum 1 value, whereas TSL is PS value in this graph. Now tell me, how is a TSL value compared to triple SL? How is a TSL value compared to triple SL? Definitely less. It will be less. So transient stability limit of the system will be less compared to steady state stability limit. Transient stability limit of the system will be definitely less compared to steady state stability limit. Okay. So I think all of you understanding this. TSL value will be definitely less compared to triple SL number. Yeah. So I'll take one small problem on this one. You just go through this problem 22, question number 22. Question number 22. The additional questions 5. Additional questions 5. It's question number 22. Go through it, please. Very simple question it is. Very simple question. Options also there. You go through the options later. Just read the question. Read the question and try to give the answer. Consider the following SMIB with all reactances and voltages are given in per unit form. You see, generator voltage 1.2 at an angle delta, reactance is 0.2, transformer 0.2, lines 0.2, 0.2, and mod V 1 at an angle 0 degree. Means P voltage. Next, the electrical power flowing from generator to infinite bus is 1 per unit. Real power flow. Real power flow from generator to infinite bus is 1 per unit. A three-phase short circuit fault occurs at midpoint of line F. This is the point F, right? At which we have the three-phase short circuit fault, as shown in the figure. And the fault was cleared subsequently by opening CB3 and CB4. See, subsequently in the sense, subsequently by the CB3 and CB4 means after some time. That's the meaning, right? After some time, breakers CB3 and CB4 are opened, and whatever the faulted line here, that is going to be disconnected. That is the meaning of subsequent opening of the circuit breakers. Okay, next thing. What is the maximum angle seen by the rotor before which the speed shall reach to the synchronous speed to make sure that the system is stable? To make sure that the system is stable. All of you? Only pre-fault, Sai Sandeep, it's only pre-fault. You say in the way of practical, anonymous certainty, please say in the way of practical for the question what you have asked. Please tell me. Subsequently means after some time the breakers are going to be opened. What's the question I am asking you? What is the maximum angle seen by the rotor before which the speed shall reach to synchronous speed to make sure that the system is stable? Anybody tell me the answer? What we have to calculate here? What we have to calculate? The angle at X point, right? We have to calculate the angle at X point, which we should not cross to make sure that the system is stable. I don't know whether you are clear this or not. Yes. So we have to calculate, or we have to write this statement first. Maximum angle seen by rotor. Seen by rotor before which omega equals to omega s should occur. To make sure that the system is stable is 180 degree minus sine inverse of PS by P maximum 3. 180 degree minus sine inverse of PS by P maximum 3. What is PS value from the data? PS value is nothing but initial electrical power flow, which is 1 per unit. PS value is equals to 1 per unit. What is P maximum 3? Post-fault maximum power transfer capacity. So in the post-fault condition, means after opening the breakers CB3 and CB4, let me copy the same diagram. I'll copy the same diagram. Okay, very simple. This is a network we have, and this breaker 3, breaker 4 were opened simply like this. These are open, and we have a open circuit now. We have a open circuit here simply in this manner. Now, what is the maximum power transfer capacity of this network? That itself is a value of P maximum 3. So, you know, E dash into mod V by X equivalent. X equivalent is XD dash plus XT plus XL. Fine. Yeah. Let's show in the next slide. X equivalent, X3 equivalent, in fact, which is nothing but XD dash plus XT plus XL. That summation will be 0.6 per unit, and maximum power transfer capacity P maximum 3 is equals to magnitude of E dash into mod V by X3 equivalent. and E dash is 1.2, V is 1 by 0.6. This will be 2 per unit. Maximum power transfer capacity in the post-fault condition is 2 per unit. Now, you can call that delta max angle, what we are saying, 180 degree minus sine inverse of PS by P maximum 3. So it will come 150 degrees. 150 degrees. Clear? 150 degree. 150 degree you get exactly 150. Simple question. Yeah, please complete it. I'll take one more question. One more question. After that, we will discuss the next case study very briefly. Next case study we'll discuss very briefly. Damping is considered, we can't do with our present study. If damping is considered in the problem, we can't do with our present study. Okay. If damping is considered, there is no other choice for you. There is no meaning of equal areas. If damping is considered, there is no meaning of equal areas. There you should go with a laborious analysis of solving swing equation. XL is 0.2. Already one line was removed. Already one line was removed. Is this equals to critical angle? How you ask? Is it critical clearing angle? No. What we are saying, what is the maximum angle seen by the rotor before which we should get omega equals to omega s? It's not critical clearing angle. For example, I will copy the same question. I'll copy the same question and I will keep here. Same question I am copying. Right? Just observe what I am going to say further. Okay. So this was a question. But a small change I will make in the requirement. Okay, let me read it. Consider the following SMIB with all reactance and voltage in per unit form. The electrical power flowing from generator to infinite bus bar is 1 per unit. A three-phase short circuit fault occurs at midpoint of line F as shown in the figure. And the fault was cleared. Fault will be cleared subsequently by opening CB3 and CB4. Okay. What is the maximum angle seen by the rotor before which the fault has to be cleared? Before which the fault has to be cleared. Fault has to be cleared to make sure that the system is stable. What you have to calculate in this case? Anybody? What you have to calculate in this problem? We should calculate the value of delta CR. Critical clearing angle we have to calculate for this problem. All of you getting this? Attempt to calculate the critical clearing angle for this problem. Attempt. Critical clearing angle. Solution will be critical clearing angle requirement. Just they said the definition of the critical clearing angle there. They said the definition of the critical clearing angle as the requirement. Anybody tell me what is P maximum 1 here? I write very briefly. I don't give a detailed solution to you. I don't give a detailed solution to you. Just I am writing briefly. Just look here. P max 1 will be E dash into V by X1 equivalent. X1 equivalent. I'll write better. Not in this way. I'll show pre-fault and then I will do this. Okay. Look, pre-fault. Pre-fault I am taking. First X1 equivalent. X1 equivalent. How much? It's a 0.2 plus 0.2. It's a 0.4 plus 0.1. 0.4 plus 0.1. 0.5. And P maximum 1 in the pre-fault condition is E dash 1.2. Terminal voltage 1 by 0.5. So this number is 2.4 per unit. Simple. 2.4 per unit. Next, during fault. During fault, you should do some exercise to calculate this X2 equivalent during fault transfer reactance. To calculate it, we have to do some exercise. Yeah. In question, if they want to ask something related to damping, they mention damped or undamped. See, Manish Kumar, if they didn't mention anything about the damping, obviously the system will be undamped system. Undamped system. Okay. What is X2 equivalent? X2 equivalent how much? Just tell me. It's 0.4, 0.2. Yeah. It's 0.4 plus 0.2 plus 0.4 into 0.2 by 0.1. I think it's 1.4. Cancel this 0.8 and 1.4 per unit. Cross check this number X2 equivalent. All of you. X2 equivalent. You try to cross check this. Anyway done. Correct. Good. Good. Do it. Already we have done one problem. That's why I'm writing directly. What is Pmax 2? 1.2 into 1 by 1.4. 1.2 into 1 by 1.4. What is that number? 1.2 into 1 by 1.4. 0.85. 0.85 per unit. Yeah, please kindly cross check your answer. Anybody is getting different numbers. If anybody getting different numbers, please kindly cross check your answers, your solution. Already we have done post fault just now. Pmax 3 value 2 per unit. Just now we have done in the previous solution, right? Post fault condition. X3 equivalent value 0.5. Sorry, 0.6 I think. And Pmax 3, if you calculate, that number is 2. That number will be 2 per unit. Done. Next thing. Cos delta CR formula, critical clearing angle we have to get now. Cos delta CR formula, PS into delta max minus delta naught plus P max 3 cos delta maximum minus P maximum 2 cos delta naught, P max 2 cos delta naught, whole by P maximum 3 minus P maximum 2. Whole by P maximum 3 minus P maximum 2. Okay, take up these numbers. What is delta max formula? Delta max formula 180 degree minus sine inverse PS by P maximum 3. I think we have done this number already. Okay, it is 150 degree. Substitute the numbers and check. It will be 150 degree. 150 degree. Kindly cross check your answers. Anonymous attendee. X3 equivalent is 0.6 per unit. Kindly cross check your option. Kindly cross check your solution what you have done. Yeah. Next thing. All the people are getting same option, same values here. Let's think about delta naught now. So it will be sine inverse of PS by P max 1. Sine inverse of PS by P maximum 1. So this value, sine inverse of PS number is 1. And what is the P maximum 1 value? P max 1 is 2.4. Anybody tell me this angle how much? Delta naught angle how much? Delta naught. Yeah, 24.62 degree. 24.62 degrees. Yeah, next thing. So let's go with the cos delta CR calculation. Cos delta CR calculation. How you are giving a cross question to me, anonymous attendee? Many people are typing answers here. Huh? How come you know? Yesterday you did pi model for Pmax 2, when to convert and when not. Please tell. Please go through the previous problems once. If you have practiced those problems well, I think you may not get that type of doubt. See, look here. PS number is 1. Delta max is 150 degree minus delta naught is 24.62 degree into pi by 180. We should keep this in radians. Plus P maximum 3, 2 cos delta max 150 degree minus P maximum 2 is 0.857 cos 24.62 degrees whole by P max 3 minus P maximum 2. Okay, you calculate cos delta CR value and finally you tell me what is delta CR number. Cos delta CR value and finally you tell me delta CR number. Critical clearing angle. Both you tell. Cos delta CR you tell. Then you tell what is delta CR. Both you give the answers. 0.0985. Somebody say 0.0985. And delta CR angle from this will be 84.86 or 84.5 degree approximately. Somebody getting 84.34, somebody is saying 84.86. Yeah, fine. Good. Cos inverse of 0.0985 will give this 84.86 degrees. Right. Next thing. So this ends the case study number 3. The next case study what we have, that is case study number 4. Just look back to your notes and check what is the case study 4 you have. Look back to your notes and tell me what is the case study number 4. Case study number 4. That is a 3-phase short circuit on one of the line in parallel line system. Parallel line system. Very close to bus bar, just after CV. Very close to bus bar and just after circuit breaker. Nearby circuit breaker. Just after, nearby the circuit breaker. So TSL is a PS at which A1 equals to A2 max when fault clearing angle is delta CR. Correct, Arvind? Correct, Arvind. So the way how you can understand is okay, Arvind Vasu. That statement what you said is correct, but if anybody asks you what is TSL, you should not answer that statement. Whatever the definition I have given, that you have to answer. But for the calculation and examination purpose, you can keep that in your mind. Yeah, good. Yeah, I will upload the key. For additional questions. Maybe tomorrow or day after tomorrow, I will upload it surely for all the questions. Let's move ahead with this case study. A 3-phase short circuit on one of the line in the parallel line system, very close to the bus bar, just after the CV. See, this is one generator. And we have 2 lines running in parallel. And this is an infrared bus. And this is a mechanical input. And these are the breakers I am showing now. Circuit breakers. Right? You name these things. 1, 2, 3, 4. These are the breakers. Yeah, next thing. And I'm locating the fault very, very close to the bus bar, just after one of the circuit breaker, maybe CB. So at this location, we are considering that fault. At the location F, we are considering the fault. We are taking that fault. Okay, again, we have 3 states of operation. Pre-fault, during fault, after clearing fault. P1, P2, P3 curves. Those things we'll draw. We'll write initial conditions as it is we have done earlier. Take the disturbance. Check the what we call operating point movement. Right? If the fault is not cleared, if the fault is cleared, how the system will be. And when we can say the system is stable, when we can say the system is unstable. Only the previous things, whatever we have discussed, we are going to repeat here also in a quick way. Okay, right. Only the location of fault was different. Let's move. Pre-fault. This also we have done as a problem. This calculation of P maximum values also we have done as a problem. So it is P1, which is P maximum 1 sine delta. During fault, electrical power equation is P2, which we say P maximum 2 sine delta. And after clearing the fault, else you can say in the post-fault condition, P3, you can name this as P maximum 3 sine delta. P maximum 3 sine delta. Simple. Similar to case study, grounding fault, it's not the thing, Ankur. It's a three-phase fault, Ankur. Just the indication of fault I will be showing like that. You say similar to previous case study or case study 2. That's your wish, okay? Tell me, how is P maximum 2 number here? During fault, how is the P maximum value? During fault, how is the P maximum value? 0. During fault, P maximum value was 0 because the fault was very close to the bus bar. Now, how is P max 3 and P max 1? How is P max 3 and P max 1? Equal or unequal? Unequal. Not only that, P maximum 3 is less compared to P maximum 1. P maximum 3 value was less compared to P maximum 1. Here we are going to get some difference in the analysis. Unequal. Good. Let me show P1 curve, P2 curve, P3 curve. Okay. In the next slide. So I'm showing here. It's a power axis. And it was a delta axis. Right? Power axis. And we are showing it is delta axis. First, let's show P1 curve. P maximum 1 sine delta, like this we have. P1 curve, that's P maximum 1 sine delta. P maximum 1 sine delta. Okay, P2 curve 0. P2 is 0. Okay, what is PE3? What about PE3? It will be coming below PE1, right? PE3 will be coming below PE1. Or maybe like this, I can say. It is PE3 curve. PE3. So this peak I am going to call as P maximum 3. Next. PS line I should show. PS line. Right? Mechanical input, or you say the same thing as initial electrical power flow. Initial electrical power flow I am showing here. Like this I am showing. So it is a PS line. PS line. Let me write the initial conditions in the similar way what we said earlier. PS line, sorry, initial conditions. Rotor angle is delta naught. Rotor angle delta naught. Rotor speed omega equals to omega s. Rotor speed omega is equals to omega s. And then mechanical input is a PS, steam input. You can say steam input, it is equals to PS. Initial electrical power output. Initial electrical power output. That is nothing but the value of PE1 at delta naught angle. PE1 at an angle of delta naught. So this is nothing but P maximum 1 sine delta naught. P maximum 1 sine delta naught. And mechanical input, what we have PS, and the initial electrical power output, these two are equal. Okay, in the initial stage of operation, this PS value and P maximum 1 sine delta naught are exactly equal. And you can get delta naught from this as sine inverse of PS by P maximum 1. You can get delta naught here as sine inverse of PS by P maximum 1. Completed quickly. Delta naught is sine inverse of PS by P maximum 1. P maximum 1. Okay. So I am showing the initial operating point here. It's an intersection of PS line and PE1 curve as A. Initial operating point is A. Right? All of a sudden, we have a short circuit fault at the point F, what we have shown. Right? Because of that, at that instant of short circuit, you don't experience any change in the rotor speed as well as change in the rotor angle. But electrical power output will be changed from P maximum 1 sine delta naught to a value P maximum 2 sine delta naught, as it is we said. So I am showing this angle delta naught here. Delta naught. And we know omega is equals to omega s at this location. Omega is equals to omega s at that location. Let me write in the next slide. Disturbance. Disturbance. Right. So I'll say fault at F location. Fault at the location F. No instantaneous change. No instantaneous change in rotor speed and rotor angle. Speed and rotor angle due to rotor inertia, in bracket due to inertia. Due to inertia. Okay, but network was disturbed. Network was disturbed. So as a network was disturbed, maximum power transfer value changed from maximum power transfer changed from a value P maximum 1 to P maximum 2. It was changed from a value P maximum 1 to P maximum 2. Analysis is same. All analysis are same. All analysis are same. Just write it quickly. Yes, just listen. That will be also sufficient. Okay. Yeah. P maximum 2. That implies electrical power flow changed from P max 1 sine delta naught, P maximum 1 sine delta naught to a number P maximum 2 sine delta naught. So I can say the point A on PE1 curve shifted to point B on the PE2 curve. Please write it quickly if you are writing. Please raise your hands after completion. Yeah. So operating point A on PE1 curve shifted to shifted to point B on PE2 curve. On PE2 curve. Shifted to point B on the PE2 curve. Pmax2 is 0. Pmaximum 2 is 0. We discussed that, Suresh, in one of the questions we have discussed about it. So this is that subsequent point on the PE2 curve as B. So point A on the PE1 curve was shifted to this one. In this way. Okay, now you see at the point B, just after the fault has been occurred, accelerating power is positive, PS minus PE positive, right? So as accelerating power is positive, omega will start increase now. Omega will become definitely more than synchronous speed. D delta by dt is positive. Delta will continue to increase now. Delta will continue to increase means operating point will move on PE2 curve only. PE2 is 0 means your electrical power output will be remain 0. Even though the angle is increasing, electrical power output will be remains 0. Right. Let me take that statement first. After that, I will tell. Right. Same as a previous case study. Same as a previous case study, but now we have taken the fault very close to the bus bar, we said. Very close to the bus bar. Same thing I am saying. Same thing I am saying what we said in the previous case study. But now the PE2 is 0. Only that difference you have to observe. In the earlier case, PE2 is non-zero, but now the PE2 value was 0. Yeah, let's take it. So at point B, just after the fault occurrence, just after fault occurrence, at point B, just after fault occurrence, listen, delta naught, rotor angle will be remains stay at delta naught only, and speed will be equals to synchronous speed. Rotor angle remains at delta naught, and the rotor speed will be omega s. It will be remain same at synchronous speed. What is accelerating power? What's the value of accelerating power? Anybody? Tell me please. That is positive, right? PA, accelerating power. Mechanical input is PS, and electrical power output right now at this angle is P maximum 2 sine delta naught, and P max 2 value was 0. So it will be simply PS. Simply PS. So which is positive, you can say positive. And not only that, you write d omega by dt, which is PA by M, positive. But you know, d delta by dt value was 0 right now. D delta by dt value was 0. Okay. Clear? Next tell me. From B onwards, what will happen? As d omega by dt is positive, omega starts increasing. Omega starts increasing. From B onwards, omega starts increase, and definitely this omega will come more than omega s, and d delta by dt, it is omega minus omega s, it will be positive. Then delta will be definitely increasing. Delta will be definitely increasing, we can say. Fine. So you can see in this graph now, delta is increasing. That's what we said. And omega value was more than omega s. Omega value was more than omega s. Now, if the fault was not clear, what we can say? System is stable or unstable? If the fault was not clear, what we can say? System is stable or unstable? Tell me please. Definitely unstable. System will be definitely unstable, we can say, if the fault was not clear. Yeah. So let's show in the next slide. If the fault was not clear, if the fault was not cleared, then system will be unstable. Or you write, then omega increases continuously, come on, always omega greater than omega s, come on, delta increases continuously, and we can say system is unstable. System is unstable. System is unstable. Okay. Yeah, done. Next step. If the fault was cleared at some point C, if the fault was cleared at some point C, let's say I am showing this point C. This is some point I am showing C. After the fault has been cleared, the operating point will jump to some other point as D here. Operating point will jump to some other point as D, something like this on the PE3 curve. On the PE3 curve. Then we have to investigate whether the system is stable or unstable for me. Following, right? So I'll say here, let the fault was cleared. Fault was cleared at point C, and operating point will move to D on the PE3 curve. And the operating point will move to point D on PE3 curve. On the PE3 curve. Operating point will move to the point D on the PE3 curve. Fine. That I have shown in the graph already. Then if you want to write quickly what is that B to C, what happening in the range of B to C here, let's move. I'll take from B to C, right? Yeah. So you can write from B to C. Is of course during fault, you can say. During fault. And what's the accelerating power in this region? Accelerating power in this region is PS minus Pmax to sine delta. Pmax to sine delta is 0. So it is simply PS. Positive. d omega by dt number Pa by m. Also positive. Omega value was increasing. Omega definitely more than omega s. D delta by dt number also positive. Delta value was increasing. Fine. That's it. Fault was cleared at C. Operating point was jumping to D. I'll write at the point D. So already fault was cleared. So what is accelerating for PA? PS minus, now it is P maximum 3 sine delta C. The delta C is a clearing angle. At which the fault was cleared. Let me show it. Have I shown it or not? This angle we are naming as clearing angle delta C. Fault clearing angle. You call it as fault clearing angle. Yeah. So this value looking to be negative now. This value looking to be negative from the graph. You can observe. Then d omega by dt negative. But how is the speed at d? More than synchronous speed? Because in the zone of B to C, speed was increased. So obviously the speed at this location was greater compared to synchronous. Speed at that location was greater compared to synchronous. then definitely you observe that d delta by dt number is positive. Still, you have the d delta by dt number as positive. Okay, I want to tell one more thing. Because at point B you have PA negative, so omega starts decreasing. So B2C speed is increasing. C to D no change. From D onwards, speed is decreasing means we might have reached to maximum speed at the D location. So I can say here we might be getting maximum speed. Okay, now you tell. From D onwards, omega decreases from omega maximum, but still it is more than synchronous speed. So delta will continue to increase. From D onwards, omega decreases from omega max. Omega is decreasing from omega max, and still omega greater than omega s. So delta will increase. Up to what point we will say we have an increment for delta? Up to a point where we are going to touch omega equals to omega s. Who is going to decide whether we are going to touch omega equals to omega s or not? That will be decided by the area what we have covered earlier and what is the available deceleration area in the given figure, right? So I can say delta increases up to the location where omega equals to omega s occurs. Up to the location where omega equals to omega s occurs. Yeah. Next thing. Just have a look here in this graph. Again, this graph. So operating point is moving something like this because omega is more than omega s. That's why it's moving like that. Because delta is increasing. But in this zone, speed is decreasing, but still it is more than synchronous speed. How far it will go means up to the point wherever we are going to touch, the speed is equals to synchronous speed. So this is the point E we are showing here, at which we might be touching omega equals to omega s by satisfying the equal areas. I'm showing here at this point E. We might be getting this angle, let's say delta 1, at which we are getting omega is equals to omega. And you just highlight these two areas, what we are showing. Highlight these two areas. First area A1. Starting from delta naught to delta C. Yeah, look here. So this is the first area we are calling. We are naming this area as A1 area. Right? And the next area, what we have covered now, I am saying this area as A2 area. And almost these two areas are coming equal. A2. So A1 plus A2 is equals to 0. A1 plus A2 is equals to 0, we can say. Yeah, please ask me the doubt, anonymous attendee, in your doubt session once. Please ask me in the doubt session by coming live. Okay. Look here. So I'll say simply in this zone, particularly starting from the D to E, PS minus PE number, that is negative, right? D to E after clearing the fault, of course. Point D to point E, after clearing the fault. Accelerating power, it is PS minus P maximum 3 sine delta. This number is negative. Okay, so and you say d omega by dt number is negative. Omega value was decreased in the zone, but still it is greater compared to synchronous speed. Greater compared to synchronous speed. And you say d delta by dt, that is positive. D delta by dt value was positive in that zone, and delta value was increased in that region. Delta value was increased in that region. Yeah. Next. So at point E, as we are saying now, angle we have something like delta 1 in the indication, and we get omega equals to omega s here at this point E. So after saying omega equals to omega s at point E, d delta by dt at this angle delta 1 is equals to 0. How come I know that d delta by dt equals 0 at that angle means? We should say first integral of PA d delta equals 0 up to the angle delta 1, then we should call that d delta by dt equals to 0. So you can say integral PA d delta is equals to 0 up to the delta 1 angle starting from delta naught. Starting from the angle delta naught. Right? So now you can divide that integral into two parts. One starting from delta naught to delta c. Next one is from delta c to delta 1. Yeah, please write this expansion. Write this expansion and show the areas A1 . Yeah. See, I'm rewriting this integral into two parts as we have done earlier. First one, delta naught to delta c, PA d delta. Second one is from delta c to delta 1, PA d delta. Of course, in the first one, delta naught to delta c, PA is PS minus P max 2 sine delta. Same as a previous. Same as a previous. With respect to delta, you can say. Second one, delta c to delta 1, PS minus P maximum 3 after clearing the fault. Sine delta with respect to delta is equals to 0. Clear? And already we have shown the areas. The first area is acceleration area A1. Acceleration area A1. And second area we are calling as deceleration area and naming it as A2. A1, A2. So A1 plus A2 is equals to 0. A1 plus A2 is equals to 0. Okay, done. So can we say system is stable by stopping the analysis here? Yes, of course, by means of equal area criteria, or you can say first swing stability study. So simply you can write system is transiently stable provided that there is no second disturbance. System is transiently stable. Provided that there is no second disturbance. Second disturbance. Okay, provided that there is no second disturbance. But E is not the final stable point what we have shown. In bracket you write, but E is not the final stable point. Not the final stable point. E is not the final stable point. To know what is the final stable point and all, we have to do little further analysis. Little further analysis. Okay. So after this one, means after doing this conclusion and all, we'll be thinking about which fault is more severe. Till now, we are doing the complete analysis with respect to three-phase fault only, right? Till now, we are doing the yes. Analysis procedure is same for every case. Listen, till now we are doing that on the three-phase fault. If you have a LG fault, if you have LL fault, if you have LLG fault, okay? And among these faults, which fault is more severe? These things we are going to discuss further. Anyway, let me complete the backswing quickly. Backswing, just I will draw the diagram. Just I will show the diagram. Backswing. I don't write anything. Just I will write it in the backswing. Backswing. Which curve we should take in the backswing? I said only PE3 curve, right? We should take only PE3 curve in the backswing. Yeah, I'm showing previous slide. If anybody is still writing, please complete it quickly. Still somebody is writing, I think. Okay. So only PE3 curve we have to consider. You don't need to consider the curve PE1 as well as PE2. So let me clean these things. Only PE3 curve we need. So this is the PE3 curve we have. PE3 curve. It's a PS line. And this is P maximum 3. P maximum 3. Yeah, next. Let's copy that previous one also, means a forward swing analysis which we have done. Let me copy that also quickly. This one. So I'll show that here. Done. Okay, the point at which we have stopped our forward swing is point E. That let me identify that in this graph. This is a point E at which you know the angle as delta 1. At which you know the angle as delta 1. And already we said omega is equals to omega s. Omega is equals to omega s at that point. And accelerating power is PS minus PE, that is negative. So omega starts decreasing. Omega starts decreasing and it will become less than omega s. D delta by dt is negative. Delta starts decreasing like this. So operating point will move on the PE3 curve, something like this. Okay, in the whole region, omega decreasing and it is less than synchronous. And we touch it to this point F. Touch it to that point F, at which I will call this angle as delta F. I'm calling that angle as delta F. And from this point, so at this point F, omega is still less than synchronous speed only. So d delta by dt is negative. Delta will decrease from delta F. Operating point will move down like this. We are entering into acceleration. Omega starts increasing, but still it will be less than synchronous speed. Okay. So operating point will come down and it will go up to the extent where you can get the A3 area will be equals to the A4 area. A3 area will be equals to A4 area. Up to that extent, it will be going. Let me show that. This is the area we are calling as A3. This is the area we are naming it as A3. And A4 area, whichever I am going to show now, A4 area, whichever I am going to show now, it should be matched with A3 area. A3 area. So I will be showing that here. Like this, I am showing. This is A4 area. So that A3 plus A4 is equals to 0. And let me show this is a point G at which we are getting omega equals to omega s in the expectation. And I'm calling this angle as delta 2. Calling that angle as delta 2. I think I no need to write anything. Do you want me to write anything now? From E to F, at point F, from F onwards. Do you want me to write? Not required. Yes, good. Sir, in previous case, could delta go negative? That depends upon A3 area, Vishnu, that depends upon the first area, what you have covered. The first area, what you are covering is a bigger one. Obviously, if it is needed, you can go for negative also. So I can say simply the rotor will be swinging in between these 2 points, E and G, continuously with respect to time. If damping is considered, both will be inclined onto F point. So F is a final stable point to be expected because already at that point F, accelerating power is equals to 0. Okay, let me write final comments. Rotor will be swinging in between points E and G. Rotor will be swinging in between the 2 points E and G. Okay. Next, if damping is considered, you write quickly to fulfill the case study. If damping is considered, points E and G will come close together. Points E and G comes close together. Swing by swing with respect to time. Swing by swing with respect to time, and finally incline onto F. Finally inclined onto F or coincide to F. Finally incline onto the point F, you can say. Yeah. And speed at F varies between minimum and maximum values. Varies between omega min and omega max. And finally, omega equals to omega s will occur. And finally, omega equal to omega s occurs. Omega equal to omega s will occur. Rotor is rotating, that's okay. If you are standing on infinite machine, it will be looking like stationary, right? If you are standing on infinite machine, it will be looking at stationary. So you write finally at F location, omega equals to omega s we have. Omega equals to omega s means you write d delta by dt 0. And accelerating power already is at 0 at that point all the time. So d omega by dt also 0. And we say we reach it to steady state. System reaches to steady state. System reaches to steady state. System reaches to steady state. I'm showing previous slide. If anybody is still writing, please complete it. Same as a previous case study, just you can copy from that also. Why I am writing this means just to fulfill this case study, I am writing this. Yeah. Next, Look here. After reaching to steady state, what we have to check it is dp by d delta. See, if we check the value of dp by d delta at this point f, that is positive, because this point f is on the positive slope region of the power angle curve. Positive slope region of the power angle curve. So I can say at f, already you know the value dp by d delta was greater than 0. So system will be stable. System will be stable under steady state. Stable under steady state. Okay, and that final stable angle here, final stable angle that is delta f. Delta f, what you can say that 180 degree minus sine inverse of PS by P maximum 3. Sorry, final stable angle is sine inverse of PS by P maximum 3. Delta f, delta. Final stable angle, delta f. Just if you can look in this graph, you can get it. Delta f is sine inverse of PS by P maximum 3. P maximum. Okay, you just draw delta versus time curve and omega versus time quickly. Delta versus time and omega versus time you draw quickly. Swing curve I am going to draw delta versus time. Expected or approximated swing curve. Expected or you can say approximate swing curve. I'll show axis here. So time axis. It was delta axis. What are the things I have asked you to observe? What are the things I have asked you to observe? Delta naught angle, how much? Delta max is how much? Delta min, how much? Delta f, how? Only these four. Only these four. Delta naught, I will show something like this. This is a time t naught. Up to that time t naught, we have this angle delta naught. I will show here. Kindly look. Delta naught angle. Next one. What's the maximum angle seen by the rotor in the analysis? What we have done? Delta 1 is a maximum angle seen. Okay. Delta 1 is a maximum angle. Delta 2 is a minimum angle which is negative. Minimum angle seen is negative. Delta 2. Okay. Let me write this one. Maximum angle seen is delta 1. I am showing like this. Okay. Delta 1. Minimum angle seen is delta 2, which is a negative angle. Like this I am showing. Okay. And how is your final stable angle? How is your final stable angle? That is greater than delta naught. Just if you want, you can check that in the previous graph in the comparison. The comparison you can check that. How is the final stable angle? Final stable angle, if you show the same thing in the previous graph, this is that point we can say. This is the point we can say. Yes. Okay, fine. Let me show. The final stable angle was little higher compared to the delta naught angle. So I am showing the final stable angle line something like this. Okay. Now, just simply you start from this angle delta naught, just show the variation and finally you make it settle down to delta f. Yeah. So I will be showing like this. Reaching to maximum and comes back to minimum angle like this, negative angle it is. And then rising up and it will be making some oscillations continuously like this. Okay. And finally, you are going to get that delta f as a final stable angle. Simple, final stable angle. You try to draw omega versus time on your own. So many of you are feeling it will be similar case studies. You try to draw omega versus time for this one. Okay, on your own. Try to draw omega versus time on your own. Okay. So what is the maximum angle seen by the rotor before which we should get omega equals to omega s? Starting point will be linear. In this one, omega versus time, starting point will be linear because accelerating power is constant with respect to time. So it will be linear and then it will become non-linear. Second omega max will be greater compared to first omega max because of high area in the backswing, right? The similarly. Let's check now. Let's check what I said just now. What is the maximum angle seen by the rotor before which we should get omega equals to omega s means that is this point x we should not cross. And what is the angle at x? Obviously, that is nothing but 180 degree minus final stable angle. 180 degree minus final stable angle, or is a 180 degree minus sine inverse of PS by P max 3. Same equation, same equation. That's it. I'm not writing it. I'm not writing it. It will be similar way of previous. Okay. What is critical clearing angle formula? Critical clearing angle formula. Yeah. Critical clearing angle formula. Same as previous, cos delta CR equals to that. Okay. If you want, I'll say. Critical clearing angle formula. Critical clearing angle formula. So I'm saying simply like this. Okay. If you want, you write it, else you can skip, no issue. Same formula as a previous. Can we calculate critical clearing time now? Is it possible to calculate critical clearing time in this case study? In this case study, is it possible to calculate the critical clearing time? TCR 2m into delta CR minus delta naught by accelerating power under root. This is the critical clearing time. Critical clearing time. Yeah, we are capable to calculate it because accelerating power is constant in the span of delta naught to delta CR. This equation can be used in the calculation of critical clearing time. Okay, done. Yeah. Next thing. Next heading I'm taking up. Comparison between different faults with respect to stability of the system. Comparison between various faults with respect to system stability. Yeah, that's right. Next slide. Comparison between various faults with respect to stability. Respect to system stability. System stability. Okay. All the stability analysis valid if machine operates less than synchronous speed. Yes, Vishnu. Yes. Look here. Look here. See, this is a generator we have connected to infinite bus bar through two lines running in parallel. Two lines running in parallel. We have a system like this, and these are breakers. I am showing breakers. Look. So this is a mechanical input. We have PS. Next, listen. This is one word what you have to remember. This one word what you have to remember is this is the location of fault. F. I am showing very close to bus bar. Means you feel that the fault is on the bus bar itself. Electrically speaking. Electrically speaking, you can feel that the fault is on the bus bar itself. Okay, listen here. This is the location of fault. See, actually, we have shown only one line here, but physically speaking, we have three wires there. It's a single line diagram, right? Single line diagram. So maybe line 2, what we have that I am drawing now, line 2 expanded way. This is A, and this is B, and this is C. Only line 2. Only line 2 I have. And you are having one breaker at this place. You are having one breaker at this place. At this bus bar, you have one circuit breaker, which is a 3-phase, 3-pole circuit breaker. 3-pole, 3-phase circuit breaker, you can see. 3-phase, 3-pole circuit breaker we have. See, actually, any type of fault occurred in the system. Either it's a single line to ground fault, or double line fault, double line to ground fault, or 3-phase fault, whatever it is. Irrespective of type of fault, the whole circuit is going to be disconnected. Whole circuit is going to be disconnected. Means if you have LG fault here on phase A conductor, if you have LG fault, all the 3 conductors will be open, not only A. Not only A. The reason is, if only A got opened, B and C are healthy, that may be leading to open conductor fault. Yes or no? For example, you have only 3 lines, 3-phase line. One line was faulted, that line you have disconnected. 2 lines are in active mode. 2 lines are in active mode, and 1 line is not in active mode. That is leading to open conductor fault, right? To overcome the issues of open conductor faults, always the people will suggest, irrespective of type of fault, you try to open all the 3 poles, means all the 3 lines, I can say. Okay, now tell me, we have some pre-fault maximum power transfer capacity as P maximum 1. Pre-fault maximum power transfer capacity as P maximum 1. And post-fault means after clearing fault by opening breakers. After clearing fault by opening the breakers, we have a maximum power transfer capacity of P maximum 3. See, my question is very simple to you. Whether the pre-fault and post-fault maximum power transfer capacity numbers, pre-fault and post-fault maximum power transfer capacity numbers are remains same, irrespective of type of fault. Is it correct or not? Pre-fault, it is same for anything. Whether the fault is a LG fault, LL, LLG, 3-phase, doesn't matter. Pmax1 will be remains same for all the types of fault analysis. Okay? If the post-fault means fault occurred, breaker was opened to disconnect the fault element. In that situation, for LG fault, how much is Pmax3? For LL fault, how much is Pmax3? For LLG, how much is Pmax3? For triple L, how much is Pmax3? Whether all the numbers are equal or not? Nobody is responding. What happened? Nobody is responding. It will be equal, right? That's what I said just now regarding the 3-pole breaker. It will be equal. That's what I said just now regarding 3-pole breaker. Whether the fault is a 3-phase fault or LG fault, whatever may be the type of the fault, all the 3 poles are open. Means simply this line 2 will be thrown out. Line 2 will be thrown out. And you have generator line 1 infinite bus for any type of fault after clearing it. Yes or no? So Pmax1, Pmax3 values will be as it is, irrespective of type of fault. Clear? Now, according to the type of the fault, in the 3 curves, Pmax1 sine delta curve, Pmax2 sine delta curve, Pmax3 sine delta curve. In these 3 curves, which curve will be different? Which curve depends upon type of fault? Which curve depends upon type of fault? Yeah, definitely P maximum 2 value. P maximum 2. Any case it is high channel. Any case it is high channel. Yeah. Yeah. So I will be saying here, kindly observe. So these 2 numbers will be same. You might get a doubt like this. I will write separately. That may be better. It will be same. For all types of faults. Okay. For all types of faults, if the network remains same. Types of faults. And this Pmax3 will be same again for all types of faults with respect to stability. Only the value of P maximum 3. Only the value of P maximum 3 is, P maximum 2 is going to be different. Sir, it will open means 3 phases will open, means the current will not produce. But you have some current in line 1, right? Yugashri, I am talking about only line 2, so-called the faulted line. Only line 2, that is faulted line we are talking. Okay, right. Next. X also remains same. X point also remains same. Only the value of P maximum 2 will be different from one fault to the other fault. Only that we are going to concentrate here. P maximum 2. So I'll write. So P max 2 value, so-called during fault maximum power transfer capacity, will be different. According to type of fault. According to the type of fault, you can say P maximum 2 value will be different. See, our aim is to calculate the value of P maximum 2. Based on that, we are going to decide which fault is severe and which fault is having less severity. Yeah, so this discussion is only for the fault near to CV. Actually, Sivaram Krishna, I am considering that case study here for comparisons. Okay, not necessary at this location, maybe at the midpoint of line. Any location you can take that fault. Okay. Yeah, fine. Let's move ahead. Look, first LG fault I am taking up. Single line to ground fault. Very simple. Just listen. During fault only I am drawing. I am drawing this one only during fault. During fault, if it is a LG, we have positive sequence network, negative sequence network, zero sequence network. All the three should be connected in series. Okay. Now I am drawing positive sequence network for this single line diagram. This is a generator. Positive sequence reactance. And we have 2 lines in parallel. I will show like this. It's a line 1, line 2. At the end, we have some infinite bus. Yeah. Okay. Kindly observe my words. And whatever the fault we said, very close to the bus bar. I will be taking up that fault location as this point. Is it acceptable? Tell me first. This itself I am treating as fault location. Is it acceptable or not? Yeah. Okay, good. So this itself is a fault location. So if you want to write these things, it is XG1, XL1, positive sequence reactances, and these are voltage sources. Now I'll draw negative sequence network now. Negative sequence network means you don't have a source here. And you get only Xg2, negative sequence reactance. And you have 2 lines in parallel. XL2, you can say. 2 lines in parallel, XL2. And here also, it will be like this. XL2. And again, this is our fault location. Okay. Next, zero sequence network. You assume that this alternator is star solidly grounded one. Zero sequence network I am drawing. You assume that the alternator is star solidly grounded. So if you calculate it, if you draw that, it is Xg0. And 2 lines in parallel, XL0, you can say zero sequence reactances. And here you can say the closed one. Fine. And this is a fault location. Now, these 3 sequence circuits we have to connect in series. Kindly observe the connection how I am making. Observe the connection how I am making. These 2 I can add together. Because it's the bottom one is a neutral plane, zero potential plane, and this fault location and this one can be added together. Like this we have to do. Tell me, all of you understood this one, this diagram? This diagram, have you understood? Yeah. Next extension to this now. Just observe this word. This Xg2 and XL2 in parallel, you will get some reactance. And what is that overall reactance of this circuit between this fault location to neutral? What is the overall reactance of this circuit between the fault location to neutral? Anybody? Between the fault location to neutral, what is the equivalent reactance you call? Tell me please. X2 equivalent can we call? Thevenin equivalent reactance. Good. What Thevenin equivalent reactance? Negative sequence Thevenin equivalent reactance, we can call this one. X2 equivalent, negative sequence Thevenin equivalent reactance. Better I will write X Thevenin 2. X Thevenin 2. And between this F and neutral, whatever the equivalent reactance you calculate here, that I am going to call zero sequence Thevenin reactance. Zero sequence Thevenin equivalent reactance. Okay, so now I will be redrawing this one with only positive sequence network, and this circuit whole we replace with X Thevenin 2, negative sequence Thevenin reactance. This circuit whole we replace with zero sequence Thevenin reactance, and these two will be connected in series now. These two will be connected in series. That will go in between this fault location to neutral. Just from circuit analysis. Just from the circuit analysis. Okay. So let me copy the same diagram. Same diagram I am copying. I will make that replacement now. Same diagram I have copied. And I'm making that replacement. Kindly go through it. Look here. So this I am removing, this whole network I am removing. That I will be keeping as simply X Thevenin 2, XTH2. X Thevenin 2 I will call this. X Thevenin 2, negative sequence, Thevenin reactance. And this network I am removing whole. And this I am going to call as X Thevenin naught. X Thevenin naught. Okay, so this is XTH naught. Now, this X Thevenin 2 plus X Thevenin naught, what we have, it will appear at this particular place. I don't know whether you are understanding this equivalent or not. Yeah. A similar procedure on right. Already we discussed about LG fault, right? Already we discussed about LG fault. What we have done in case of LG fault earlier, we constructed positive sequence Thevenin network, negative sequence Thevenin network, zero sequence Thevenin network, and the three Thevenin networks we connected in series. But now what I'm saying, take up the network separately. Don't find out the equivalent Thevenin model. Just to join them in series with respect to fault location. That's it. Yes, good, Imtiaz. Good. Now, in the very next diagram, what I will do is, I am drawing the positive sequence network here. Positive sequence network XG1. And these are two lines in parallel, XL1. Okay, and this is a voltage source on generator side, and it's a voltage source on what we call infinite bus side. Yeah. So in between this fault location and neutral, we will get some impedance here. That is XTH naught plus XTH2. Like this, we'll get some reactance at the middle. Okay, next thing. Listen. See, this XL1 in parallel, I will replace that with XL1 by 2. XL1 in parallel, I will be replacing that with XL1 by 2. XL1 parallel, it will be XL1 by 2. Now, what is the transfer reactance between the two voltage sources? What will be the transfer reactance between the two voltage sources? We have to calculate it. It's a simple one to say. It is a star connection. This star you have to convert into delta. This star, we have to convert into delta. By doing that conversion from star to delta, we are going to get the equivalent transfer reactance between the two voltage sources that will decide the value of P maximum. That will decide the value of P maximum. All of you getting this thing, what we have done for LG fault? Yeah, I need your response. Please respond kindly. Clear? Okay, okay, good, good. Fine. Next thing. For example, if it's a LL fault, what will happen? If it's a LL fault, what will happen? Tell me. LL fault. You have to connect the positive and negative sequence circuits in parallel. Positive and negative sequence circuits in parallel. I am drawing positive sequence network. It is Xg1 reactance, and this is a voltage source of generator. And here it is XL1 by 2. XL1 by 2. And this is an infinite bus voltage. Simple. If you connect positive and negative sequence circuits in parallel, simply can I say that negative sequence Thevenin reactance will occupy this place? I'll say simply negative sequence reactance will occupy this place. Yes or no? Is it okay, LL fault to you? LL fault. Tell me, if it's a LLG fault, you know, positive, negative, zero sequence circuits in parallel. So simply in case of LLG fault, I will be saying LLG fault, observe. LLG fault, same positive sequence network I am taking up, generator voltage source and the generator reactance, and it's a line XL1 by 2. Okay. So what we get this reactance? Anybody tell me here? What we are going to get this reactance between fault and neutral? Between fault and neutral, what is this reactance you get? I need your answer, please. Tell me. X7 2 in parallel with X7 naught. That's it. XTH2 in parallel with X7 naught. Good, good. XTH naught. Okay, next thing. For example, if it is a triple fault, what will happen? If it is a triple fault, what will happen? It will be 0, right? If it's a triple fault, then you take the positive sequence network only, like this, Xg1, and this is XL1 by 2, Xg1 and XL1 by 2. And here you will be having 0. Why? In the sense it is a solid short circuit. Solid short circuit. Getting? Jet-Thevenin 1 also not there. Jet-Thevenin 1 we won't calculate. We'll take only positive sequence network. Sir, what is the difference between LL fault circuit and LLG fault circuit? Simple. In case of LL fault, positive and negative sequence circuits are in parallel. So whatever the negative sequence Thevenin reactance you have, that will occupy between fault and neutral of positive sequence network. Okay. Whereas in LLG fault, positive, negative, and zero sequence circuits are in parallel. Positive sequence circuit already we have drawn. Now, whatever the parallel combination of Thevenin equivalent reactance of negative and zero sequences, that will occupy this fault to neutral place. Fault to neutral place. Now tell me. I will show one simple model. Just observe here. For example, all the 4 circuits: LG fault, LL fault, LLG, and triple L. For all the 4 types of faults, we have the circuit something like this, right? Transfer impedance circuit. Sorry, that network between the 2 voltage sources, looking in this manner. And you know, we will be identifying this point as A, this point as B, this point as C, and this is XA, XB, XC. XA, XB, XC. Now tell me, if you convert that star to delta, if you convert this star to delta conversion, What is that XAB value? That's the transfer reactance which we do generally. During fault, transfer reactance is XAB. XAB. What is the formula for XAB? It will be XA plus XB plus XA into XB by XC. I think all of you getting this one. This is the transfer reactance during short circuit fault. I am saying XAB. XAB equals to XA plus XB plus XA into XB by XC. Simple, simple. I am asking one very simple question. If XC, this one is very low, XC is very low, then how is XAB number? XAB number very high. Transfer reactance is very high, you can say. Okay. If transfer reactance is very, very high value, how is the value of P maximum 2 number? During fault, maximum power transfer capacity, very low number. During fault, maximum power transfer capacity is very low number. Yes or no? Fine. See, if this is very low, how is the system stability? How is the system stability? Is it high or low? Obviously, system stability is also low, right? I've discussed this in the previous case study. System stability decreases. System stability reduces. System stability reduces. Clear? Fine. This only we have to adapt for the previous things. Just observe here. Among these 4 circuits, it's the LG. Among these 4 circuits, this is XC for the LG fault circuit. This is XC for the LL fault circuit. It is XC for LLG fault circuit, and is XC for triple fault circuit. Okay. Among these numbers, among these 4 numbers which we have, which fault is exhibiting highest value of XC? Which fault is exhibiting highest value of XC? Yeah. Which fault is exhibiting highest value of XC? LG. Simple. So as a LG is exhibiting highest XC value, how is the XAB per LG fault? XAB per LG fault lowest. Then Pmax2 during LG fault is highest. Pmax2 during LG fault is highest. Means the system is more stable. If you have LG fault on the system compared to remaining faults. I think all of you getting this. Is it okay? Many of you are saying understood. Yeah. Can we write comparison directly now? Can we write directly comparison? Next you observe. X7 and 2 we have. X7 and 2. Then here X7 and 2 in pair with X7 and not. This number will be definitely less compared to X7 and 2. This number will be definitely less compared to X7 and 2. So after LG fault, LL fault will have the next highest Pmax. After LG fault, LL fault will have the next highest value of Pmaximum. Next highest will be LLG. Next it will be triple fault. Okay. Yeah. See, what we are studying here is, if you have a short circuit fault on the system, for which type of fault the system will be more stable? We are not studying the fault is making the system stable. That's not we are studying here. Understanding what I said? Unfortunately, we get some faults on the system. Okay, different faults we have. If you have which fault on the system will be more stable compared to the other faults. That we are discussing here. Okay, let's say equivalent transfer reactance in the during fault condition. During fault, the transfer reactances will be yeah, just look here what I'm saying. X2 equivalent, please don't confuse with this term. X2 equivalent is transfer reactance during short circuit fault of LG. X2 equivalent of L X2 equivalent of LLG, X2 equivalent of triple L. Okay, and LG fault will have lowest transfer reactance, then LL, then it is LLG, then finally it is triple L. Triple L. Good. A triple LG is same as triple L. Okay, so if that is the case, if you go with P maximum two values, LG, P max 2, LL, P max 2, LLG, P max 2, triple L. So P max 2 for LG is greater, P max 2 for LG is greater, LL, LLG, and then triple L we have. So in this manner, the severity of LG fault will be very less with respect to stability, and severity of triple L fault is very high with respect to stability of the system. Okay, so LG fault is most severe fault. Sorry, LG fault is least severe fault with respect to stability, and triple L fault is most severe fault. You write this with respect to system stability. With respect to system stability. Okay? With respect to system stability. Yeah. Yes, yes, Ashish Raj. Yes. Okay. I will ask one simple question to you. At alternator terminals, which fault is more severe? At alternator terminals, which fault is more severe? Please answer me. Which fault is more severe at the alternator terminals? See, listen. Where you have taken fault in the present study? At what location you have taken fault in the present study? At alternator only, right? At the alternator location only you have taken the fault. At alternator location only you have taken the fault. But now you are saying triple L is more severe here. But in answers in the Q&A you are saying LG. How come it is LG? Triple L is more severe, right? Getting my question? Now you will ask a question to me, sir. Earlier in the fault analysis, you said LG. Earlier in the fault analysis, you said LG. Okay, that is correct with respect to current. With respect to current, LG is more severe. With respect to stability, triple L is more severe at all places. Triple L is more severe at all places, irrespective of the location of the fault. Okay, you want me to tell again? Yeah. So if anybody asks you this type of question, at alternator terminal, which fault is more severe? Then you say this one, sir, with respect to fault current or with respect to current magnitudes, LG fault is more severe. But with respect to stability of system, triple L is more severe. Clear? Right. So you write with respect to stability of system, at any terminals, at any location, including generator terminals. Okay, fine. Yeah, I have written this one. Shivanath Ganesh, I have written this one. Please go through it. So you have a break for 10 minutes. After break, we'll do one problem on this one. Possible, not on this concept, general triple L fault stability concept. We'll do one problem, possible. After that, we'll start the next case study. Next case study means removal of line. Till now, we have discussed the stability analysis only with respect to fault. Now we are going to discuss with respect to removal of the line. Okay. So I have resumed audio video on screen. Resumed audio video on screen. So I will be moving ahead. Some small problem here. Go through it. Let me check first. Do we have or not? See, if you want, you can do problem on that critical clearing angle only. Critical clearing angle. But I will take one different problem to you. May not be with this case study. May not be with this case study. But I will take one different problem to make you understand, or this one from the additional questions file. I'm taking up this problem. Kindly go through it. It may not be from previous case study. It cannot be from previous case study. Yes. Just it is a transient stability problem, analysis problem with respect to what we call fault. With respect to fault. Look, a four pole, 50 hertz synchronous generator connected to infinite bus bar through a power network. The pre-fault, during fault and post-fault maximum power transfer capacities of the network for a fault at certain location are 3.5 pre-fault P maximum, 1.0 during fault, 2.7 post-fault, respectively. The steam input of generator kept at 1.1 per unit as constant. PS value kept as 1.1 per unit constant. Next one. The angular momentum of the system is m equals to 1 by 10 pi second square per electrical radian. If the fault was cleared at an angle of delta C equal to 60 degree. At an angle of 60 degree, the fault was cleared. Then the speed of the rotor in RPM for this clearing is how much? Speed of the rotor in RPM for this particular clearing is how much? It is one of the untapped area in the exam. One of the untapped area in the exam asking the speed calculation. So attempt to do this problem once. Just have a look. I'll write we have a 4-pole 50 hertz generator. 50 hertz generator connected to infinite bus bar through a power network, something like this. Through a power network. Mechanical input remains constant at 1.1 per unit. Mechanical input remains constant at 1.1 per unit. And maximum power transfer capacities, P maximum 1. Pre-fault condition 3.5. During fault, that is P maximum 2, which is 1.0. After clearing fault, that is P maximum 3, 2.7, I think. 2.7. Okay. Angular momentum of the system M. 1 by 10 pi second square by electrical radians. Second square by electrical radians. Okay, next. Fault was cleared at an angle of 60 degree. That's okay. Fault was cleared at an angle of 60 degree. First of all, listen, let's draw these power angle curves just to get some clarity on the question what they have asked exactly. Okay, I'll draw the 3 power angle curves, PE1 curve, PE2 curve, PE3 curve first to get some view, on the problem what they have asked exactly in the or on his requirement, to get his requirement exactly. So it is a power angle curve 1, P maximum 1 sine delta, and we have P maximum 2 sine delta, something like this, I can say, and P maximum 3 sine delta, we have something like this. Clear? So it is P maximum 1 value, 3 per unit, P max 1, and this is a value of P maximum 3, I can say P maximum 3, and this is a value P maximum 2, I can say P maximum 2. P max 1, P max 2, P max 3. Next. Look here. I am showing PS line. TS line is 1.1. 1.1 line, that is above Pmax. Above Pmax to below Pmax. Above Pmax to below Pmax 3. So I am showing the PS line somewhere here. At some place. Okay, I'm showing that PS line. Simple. It's a PS line 1.1 per unit. Next, look back. See, what is that initial operating angle? This is the initial operating angle delta naught. Just observe it. How much is the delta naught value? Initial rotor angle. Delta naught will be equals to sine inverse of PS by P maximum 1. Sine inverse of PS by P maximum 1. And you can write it as sine inverse of PS number how much? That is 1.1 by P maximum 1 how much? That is 3.5. Anybody please tell me what is this angle? What is this angle delta naught? Please tell me. Make it quick, please. (18.317 degrees). Good. 18.317 degrees. That is delta naught. Now, just look at this. Look at this thing. Fault occurred. This operating point A was shifted to this one. I am calling it is B. Operating point A shifted to this one. That is B. And we have an acceleration, right? And omega will become more than omega s. D delta by dt is positive. Delta will continue to increase. Operating point will move something like this. At some point C, we have an angle of delta C. Fault was cleared. And this point will jump to the P3 curve like this. Point will jump to the P3 curve in this manner. Okay, next thing. Please tell me. He said that fault was cleared. Fault was cleared at an angle of 60 degree. Fault was cleared at a clearing angle of 60 degrees. At 60 degree location, the fault was cleared. That's what he said. What is interesting is to know exactly is how much is the speed of the rotor? What is the speed of the rotor in RPM for this particular clearing? The fault was cleared at 60 degree angle. How much is the speed of the rotor at that location? Anybody, how to get the speed? How to calculate speed of the rotor for this clearance? Yeah. Tell me please. How to get the speed value for this clearance? You can't use a speed equation directly here. Why it is so means accelerating power is not constant with respect to time. Because PA is varying starting from delta naught to delta C. So you can't use the speed equation what we have derived earlier. But one equation we have, kindly observe. One equation we have derived it actually. D delta by dt is equals to square root of 2 by m integral of PA d delta. Look at this equation. D delta by dt is equals to square root of 2 by m integral of PA d delta. Now, another equation you know for d delta by dt is omega minus omega s. Omega minus omega s. Now, look here. I want to know what is the omega at an angle of delta c. Omega at an angle of delta c. So I have to find out d delta by dt at an angle of delta c. I have to find out the value of d delta by dt at an angle of delta c in order to get this omega value at an angle of delta c. To get this d delta by dt, I should use this equation. So d delta by dt value at an angle delta c is equals to square root of 2 by m integral of PA d delta. Up to what angle we should take the integration? Delta c. Up to an angle of delta c, we should take the integration. Starting from which angle? Delta naught. This is that interrelation what you have to observe exactly. Following all of you. Now, you calculate the integral of PA d delta starting from delta naught to delta c first. That you substitute in this one. And you will get the d delta by dt in the electrical radian by second. Electrical radian by second. You will try to get. That you substitute here. Find out omega delta c in terms of electrical radians by second. and then you attempt to convert that into what we call mechanical speed and all. That will do. That will do. Okay. So first we have to take up this integral PA d delta starting from delta naught to delta c. So you can write integral delta naught to delta c. What is PA equation? During fault, PS minus P maximum to sine delta with respect to delta. This we have to calculate. All of you getting this one? Sir, had PE2 equals 0, we could have used speed equation. Yeah, if it is 0, you can use it. Okay. If it is 0, you can use it. Use the previous equation what we have done. Even though PE2 is 0, this method is perfect one always. This method of calculation speed is perfect. Okay, let's move ahead with this integral term. It is PS into delta C minus delta naught plus P max 2 cos delta C minus cos delta naught. Okay, let's move to the next slide to take up this integral term. Further, by substituting the numbers, right? So it is equals to, look, PS is 1.1, delta C is 60 degree, delta naught you have calculated, na? That is 18.317 degree. This we should multiply with pi by 180. We have to keep this in radian. Always, whenever you are multiplying angle with some number, you have to keep that in radians. Plus, what is P max 2? P max 2, that is 1. Okay, 1 into cos 60 degree minus cos 18.317 degrees. Yeah, please tell me what is this value of integral? What is this value of integral? You can use Dinesh, you can use d omega by dt equals to PA by M also, but you can't integrate it, right? Dinesh, you can't integrate it because PA is varying with respect to time, na? Yeah, please tell me this number. 0.351. 0.351. What will be the units of this one? Power into angle. Power into angle. So it will be per unit megawatt by electrical radians, because power is in per unit, right? That's why I'm saying this as per unit megawatt by electrical radians. Per unit megawatt by electrical radians. Okay. Now, M value already given in the form of electrical radian by second square. That will substitute, and therefore d delta by dt value at an angle of delta C is equals to square root of 2 by M, 1 by 10 pi, 2 by M, 1 by 10 pi, and that integral number is 0.351. Right? Yeah. Please get this number how much? Square root of 2 by M. Yeah. Please tell me. What is number? 4.7. 4.7. I'm sorry. Here it is per unit megawatt electrical radian. I'm really sorry. By mistake, I have kept that division symbol. It's not by. It is per unit megawatt electrical radian. That's some of you are saying this number. Somebody saying 4.7. Okay, 4.7. You can take 4.7. What will be units of this one? Electrical radian by seconds. Electrical radian by seconds. Next thing. So as we know already, d delta by dt at an angle of delta C is equals to omega delta C value minus omega S. So you can keep this one in electrical form. 4.7 electrical form is equals to omega delta C minus, you keep omega S also electrical form only. Kindly listen. Omega S also you keep in the electrical form, which is 2 pi into 50. 2 pi of electrical. So you take that to the other side. So omega delta C you can get as 2 pi of is I think 314. 100 pi you take if you want. 100 pi plus 4.7 electrical radian by seconds. Electrical radian by second. Yeah, you please tell me this number how much? Please tell me this number. 318.8. Good. 318.85 electrical radian by second. Okay, listen. See, actually, this omega delta C, I can write it as 2 pi into Fc. Look, 2 pi into Fc. That Fc is a frequency of the induced EMF at the instant of clearing. Frequency of the induced EMF at the instant of clearing. So Fc is the frequency of induced EMF at the instant of clearing. At the instant of clearing. At the instant of clearing. Okay, so now you can get that Fc value in terms of Hertz. After getting Fc value in terms of Hertz, right? Speed is equals to 120 F by number of poles. 120 F by number of poles. That way. Simple. So therefore, Fc is equals to 318.85 by 2 pi in terms of Hertz. Tell me this number. How much is that value in Hertz? It's not 500. 50.75. Good. 50.75 Hertz. Now, speed of the rotor for this particular frequency. Speed of rotor for this particular frequency, I'll call NC is equals to 120 F by number of poles. 120 F by number of poles. You can get now 120 into frequency, 50.75. Number of poles will be 4. Number of poles will be 4 given in the data. So if you calculate this number, you may get 1522.5. Approximately 1522.5 RPM. This is one of the way of calculating the speed at any angle you want. At any angle you want, you can calculate the speed just by calculating that integral of PA d delta. Just by calculating integral of PA d delta, you can calculate it. Okay. Yeah. So let's continue with the next case study. Minute, please. So let's continue with the next case study, that is removal of one of the line. Removal of one of the line in the parallel line system. That's also okay, Shivana. Sir, speed is more than synchronous speed. By seeing option also, we can answer in some cases. But Dinesh, they may give all the speeds as more than synchronous sometimes. Okay, so we can calculate speed through omega s as 2 into 314. Okay, we will see that Imtiaz Pasha in doubt session once. What you have asked me, please remind me in doubt session. So let's continue with the next case study. Fifth case study, removal of one of the line in parallel line system. In parallel line system. Removal of one of the line in the parallel line system without any short circuit fault. Without any short circuit fault, intentionally we are doing that. You write that also in bracket. Without any short circuit fault. Without any short circuit fault. Yeah. Let me modify the heading. Removal of one of the line in parallel line system by opening circuit breakers. Opening respective circuit breakers. Yeah. See, this is one alternator connected to infinite bus bar. Alternator connected to infinite bus bar through two lines running in parallel like this. Okay, similar analysis, but I will tell you what's the change here. Similar analysis, but I will be telling you what is the change. It's a mechanical input remains a constant value. It is circuit breaker 1, circuit breaker 2, 3, 4, like this way. Circuit breakers 1, 2, 3, 4. Yeah, very simple, very simple. XD dash is a generator D-axis transient reactance, and this voltage is mod E dash at an angle delta, and this infinite bus voltage is mod V at an angle 0, and this is XL. Okay, so you call it is line 1, line 2 if you want, L1, L2 you call. Without removing that line, without removing that L2, if you draw that circuit, we have generator and we have two lines in parallel. And what will happen to the transfer reactance? Without line removal, what is the transfer reactance value? X1 equivalent you call that. That is nothing but XD dash plus XL by 2. XD dash plus XL by 2. Now, if you call the value of P maximum here, call the value of P maximum in this case, it will be E dash magnitude, V magnitude by X1 equivalent. E dash magnitude, V magnitude by transfer reactance X1 equivalent. Without that line removal. Next, with that L2 removal, in the next slide. Next slide I am showing up. Next slide I am showing that with line removal. With line means L2 removal. By opening the respective breakers means that is CV3 and CV4, you can say CV3 and CV4. What will happen to transfer reactance now? It will be XD dash plus XL, that's it. XD dash plus XL. So transfer reactance will be XD dash plus XL. Then what is the maximum power transfer capacity in this case now? Which is E dash magnitude, V magnitude by X2 equivalent. E dash magnitude, V magnitude by X2 equivalent. Very simple, very simple. How is the value of X2 equivalent compared to X1 equivalent? Greater. X2 equivalent value was more compared to X1 equivalent. As X2 equivalent is greater compared to X1 equivalent, I'll write P maximum 2 is less compared to P maximum 1. P maximum 2 will be less compared to P maximum 1. Okay, so now you are going to get only two power angle curves here in the analysis. One without line removal, second one with line removal. But in the previous cases, what we studied, we have power angle curve in the pre-fault condition, power angle curve during fault, power angle curve after clearing fault. But you don't have that type of discussion now. We have only two power angle curves, PE1 curve and then PE2 curve. Okay, yeah. So let me move ahead to the next slide. I will show the two power angle curves. show the two power angle curves. Observe here. So it's a power axis and it's a delta axis. Okay. Power axis and this is a delta axis. First PE1 curve, P maximum 1 sine delta, P maximum 1 sine delta like this. Right? Next, P max 1. It is PE1 curve. Next, PE2 curve, it will be little below to this one, Maybe you can get the PE2 curve here. So this curve is called as PE2 curve. PE2 curve. Now, this value was P maximum 2. I am saying this value was P maximum 2. P max 1, P max 2. Now I have to show PS line. I have to show the PS line. So I'll show the PS line here at some place. Something like this I am showing. It is a PS line. Let me copy this for backswing. Look here. See the intersection between the PE1 curve and PS line, that itself we are going to name as point A, initial operating point. This one, initial operating point A, at which you have an angle of delta naught. At which you have an angle of delta naught. Done. Next thing. So you write initial conditions as it is previous one. Write quickly. Initial conditions. Rotor angle is delta naught. Rotor speed is omega equals to omega s. All the things what he said earlier. Initial conditions. Okay. So rotor angle delta naught, and the rotor speed omega equals to omega s. Omega is equals to omega s, and mechanical input remains constant at PS. Steam input remains constant at PS, and electrical power output is PE1 value at an angle of delta naught. This is nothing but P maximum 1 sine delta naught. P maximum 1 sine delta naught. And you know that steam input and electrical power outputs both are exactly equal at the initial stage because you don't have either acceleration or deceleration. Okay. So from this you can get the delta naught as sine inverse of PS by P max 1. Similar study. PS by P maximum 1. That's it. Next. Now disturbance means the line removal by opening CB3 and CB4, right? And there is no instantaneous change in the speed as well as change in the rotor angle. But Pmax value will be changed from 1 to 2, so that the operating point will be moving on to PE2 curve without changing that angle. So it may touch to this point B. It may fall down. It may fall down to the point B. Okay. Yeah. So I'll take in the next slide. Disturbance. Disturbance is. So line 2 removal, L2 removal by opening CB3 and CB4. Circuit breaker 3 and circuit breaker 4. Line 2 removal. Okay. Now, you write if you want no instantaneous change in rotor speed, hence in rotor angle and rotor angle in bracket due to inertia. Because of inertia, we don't have any change in the rotor speed as well as a rotor angle. Okay, next thing. But Tmax, maximum power transfer capacity, changed from Pmax 1 to Pmax 2. Changed from P maximum 1 to a number P max 1 to P max 2. Okay, so that implies electrical power output changed from P maximum 1 sine delta naught, P maximum 1 sine delta naught to a number P maximum 2 sine delta naught. P maximum 1 sine delta naught to a number P maximum 2 sine delta naught. Okay. So that implies point A on PE1 curve. Point A on PE1 curve shifted to B on PE2 curve. Shifted to point B on PE2 curve. PE2 curve. See, in the earlier studies, you observe that. In the earlier studies, you can observe that. After the fault has been occurred, we have a change in the maximum power transfer value. And after the fault has been cleared, there is a change in the P maximum value again. Yes or no? But here, once after line removal, disturbance was over. Disturbance was over, and the operating point will be lying only on the PE2 curve from this point. Okay. Now, simply you write at that point B. So this is a jump happened from this A to B. From this point A to B, this is a jump happened. Okay. Now you write at that point B. At that point B. Look here. At that point B, delta is equals to delta naught, and omega is nothing but omega s. But if we write accelerating power PA, which is PS minus P maximum 2 sine delta naught, which is definitely a positive number. Definitely it's a positive number. And you write d omega by dt number is positive at this location. D omega by dt is positive at this location. And what is the value of d delta by dt? D delta by dt, omega minus omega s, that number was 0. D delta by dt, omega minus omega s, that number was 0. Fine. But you know, from point B onwards, omega starts increasing and omega becomes more than omega s. D delta by dt positive, delta will increase. That's it. Simple things what we discussed earlier. Okay. From point B onwards, omega increases, omega greater than omega s occurs, d delta by dt is positive, delta will be increasing now. Delta will be increasing. Delta will be increasing. Okay. Let's continue. Delta will be increasing from delta naught, something like this. So obviously you observe now that operating point will be moving on the PE2 curve, something like this. Okay, omega is increasing in this zone and omega is more than omega s. Omega is more than omega s. But we touch to one point here, that is C. What is the speciality of that C? What is the speciality of the point C? Anybody? What is the speciality of the point C? Accelerating power is 0. Speciality of the point C is accelerating power is equals to 0. Okay. Accelerating power is 0, but still omega is not equals to omega s. But still omega is not equals to omega s in this place, because from B to C omega value was increased, and let's see omega definitely more than omega s. Let me write it first. So from the point B to C, if you observe, accelerating power will be PS minus P maximum 2 sine delta, PS minus P max 2 sine delta. That number is positive, right? So you can say d omega by dt number is positive, and d delta by dt. Let me write first. D omega by dt positive is omega value was increased in that zone, that is greater than omega s. And you know, d delta by dt, omega minus omega s number, that is positive. So delta value was increasing in that zone. Okay. And at point C, let me assume angle as delta 1. Let me assume angle at this point C as delta 1. Okay. Angle at this point C is delta 1, we can say. Yeah. Let me continue. At points, after reaching to points, you write it quickly. Once after completion, please raise your hands. I will move to next slide to take up the point C calculation. Yeah. Look here. At point C, delta value is delta 1, and accelerating power, if we calculate, which is mechanical input minus electrical power output, P maximum to sine delta 1, that is 0. Accelerating power is 0. Means d omega by dt is 0. So I'll say neither acceleration nor deceleration. Neither acceleration nor deceleration. Neither acceleration nor deceleration. D omega by dt value was 0. Okay. Next. But the speed is more than synchronous speed at this place. Speed is more than synchronous speed. As omega more than omega is, yet see, still d delta by dt, if you calculate d delta by dt, you write omega greater than omega s, which is omega minus omega s, that number is positive. So as a d delta by dt value was positive, definitely from C onwards, delta will continue to increase and it will cross the value of delta 1 definitely. From C onwards, delta increases beyond delta 1 and PA becomes negative. PA becomes negative and omega starts decreases. Omega starts decreasing. Clear? Omega starts decreasing. See, as you know, as we said earlier also, B to C, speed is increasing. Point B to point C, speed is increasing. From C onwards, we are entering into deacceleration region. So I can say that the speed is going to be reduced. Speed is going to be reduced. Okay. So at C, at that point C, we might have reached the maximum speed now. Okay. So I'll write, that implies at point C, I'll write, may not be here, I'll write here. Omega equal to omega max at that point C. Omega starts decreasing from omega max, right? Omega max, right? But still, omega is greater than omega s. But still, omega value was greater than omega s. So I can say delta will be continue to increase up to the point where we touch omega equals to omega s. If you don't touch omega equals to omega s anywhere, delta will continue to increase and we will say the system will be definitely unstable. Okay. So delta increases up to the point where omega equal to omega s will occur. Up to the point where omega equals to omega s will occur. Clear? How to decide again whether we are going to touch omega equals to omega s or not? Means that is decided by the already covered area and what is the total area available in the second. Means just look here. I'll try to tell you in this. Whatever the ACB area you have, this one. This is the area A1 we are going to denote. This area is A1. Yes or no? ACB, this area we are going to say A1. And what is the A2 max available to you? What are the corner point X? What are the point X which we should not cross to make sure that the system is stable? This one only. This is a point X which we should not cross to make sure that the system is stable. Now you can observe this whole area is a A2 max, right? Whole area is A2 max. And if you look in this graph, this whole A2 max is greater compared to A1. Means we don't touch X. Before reaching to X, at some point, definitely we are going to get the resultant area, area summation as 0. Area summation as 0, and we will expect that at this point we'll get omega equals to omega s. And this is the angle I am calling as delta 2. I'll call this point as D. I'm calling that point as D. Okay? Yeah. So simple, very simple. At that point D, we might be touching omega is equals to omega s. At that point D, we might be touching omega is equals to omega s. Yeah, simple study. Let me write the next slide. That's from C to D. From this point C to D, we have accelerating power negative number. From the graph I am saying. So obviously d omega by dt number is negative and omega value was decreasing, but still the speed is more than synchronous speed. D delta by dt, omega minus omega s, that is positive, and delta value was increased in the zone. Delta value was increased in the zone. Already at C, omega more than omega s, right, Ankur? Ankur, already omega more than omega s at C. Even though you cross the point C, still omega will be more than omega s only. It won't catch up the synchronous speed within very less amount of time. Yes or no? Right. Now at point D, we have the angle something like delta 2 in the graph I have shown, but you know omega value is equals to omega s. But you know omega value is equals to omega s. And if you write d delta by dt at this angle delta 2, that number is 0. D delta by dt at an angle delta 2, that is 0. In the sense, to make sure that the d delta by dt value is 0, we should call integral of PA d delta is equals to 0. Up to which angle we should do the integration? Delta 2. Starting from which angle? Delta naught. Starting from delta naught to delta 2, we have to take up that integration. PA d delta is equals to 0. Okay. Now you can divide this integral into two parts. You can divide this integral into two parts. First part is from delta naught to delta 1, acceleration. Second part from delta 1 to delta 2, deceleration. First part, delta naught to delta 1. What's the PA equation? What's the PA equation? PS minus P maximum 2 sine delta with respect to delta. This is a PA equation in the first case. Second case, delta 1 to delta 2. In that case also you get PS minus P maximum 2 sine delta with respect to delta. See, if you are solving a mathematical problem, kindly listen. If you are solving a mathematical problem, you no need to divide this into two integrals. Yes or no? If you are solving a mathematical problem, you no need to divide this integral into two parts, because the equation remains same in both integral regions. Equation remains same in both integral regions. Okay. So this we are naming as acceleration area. Acceleration area. So it is of A1, and this is a deceleration area. Deceleration area. So I'm calling it is A2. Right? Acceleration area A1, deceleration area A2, and you will call this is A1 plus A2 is equals to 0, or else you write A2 is equals to minus A1, or else you write magnitude of the A2 area is equals to magnitude of the A1 area. And can we stop stability study here to say that the system is stable in this case? Yeah. Can we stop stability study here to say that the system is stable? Yes or no? Same question. Yes. System is transiently stable. System is transiently stable. Transiently stable, provided that there is no second disturbance. Provided that there is no second disturbance. There is no second disturbance. Second disturbance, and that point D where we have stopped our study, that is not the final stable point to be expected, because even though you are touching omega equals to omega s there, accelerating power is not equals to 0, right? Point D is not the final stable point. Is not final stable point. Final stable point. Point D is not the final stable point to be expected. Yeah, good. So all of you understood equilibrium criteria? All of you understood equilibrium criteria? So next you take up the backswing. Backswing, just you draw that and show the areas and conclude the thing. Conclude the thing. And what is that maximum angle which we should not cross? That you define. That's it. Sufficient. Let's move quickly. Backswing. Yeah, I'm showing the previous slide. Somebody asked. Showing the previous slide. Somebody asked. Just write it. If you are writing this one still. Yeah. So you take backswing as heading. Backswing. In the backswing, we should consider only PE2 curve. You no need to consider PE1 curve. The reason is, what's the reason? The PE1 curve is before removal of line. But now we are having an operating stage of after removal of line. But now we are having an operating stage of after removal of line, so that you no need to consider the PE1 curve now. No need to consider the PE1 curve. You take up only PE2 curve in the study further. Right. And this blue color dotted line, what we have shown is a PS line. Blue color dotted line, what we have here is PS line. Let me show that forward swing also for comparison's sake. Yeah, this one. So here. Simple, very simple. So check the point at which we have stopped our study. Check the point at which we have stopped our forward study. That is the point D here. Showing this point as D. Okay. Now at this point, angle delta 2. Simple. Angle is delta 2. Then omega is equals to omega s. We touched at that point D, of course. But from this, it will swing back because omega further decreasing and omega will become less than omega s. Omega becomes less than omega s. That's why delta will decrease. Delta will decrease in the sense operating point will move down in this manner. Move down in this manner, and we will touch to this point C. Touch to the point C, and in this zone D to C, omega is decreasing. Not only that, omega less than omega s. Not only that, omega will be less than omega s. And this point angle will be delta 1. This point angle will be delta 1. Okay, next. And even though you are touching a point C as PA equals 0, can we assume C is a final stable point now? If the system is stable. If the system is if the system is stable, can we assume now C is a final stable point? Not now. After reaching to steady state. After reaching to steady state, can we assume that C is a final stable point? Yes. Why it is so means PA is 0, right? Pragati. PA is 0. The operating point will not stop there right now. Right now it won't stop. It will move ahead. It will move ahead and will come back. And finally, if it is standing means it may stand at the point C, obviously. That's the expectation what I am saying. Clear? Right. Anyway, right now, even though PA is 0, omega less than omega s, d delta by dt is negative, delta will decrease below the value of delta. Delta will decrease below the value of delta. So in that situation, that operating point will come down like this, and omega will start increase because accelerating power is turning to positive, and we will be having this point as B, at which the angle is delta naught. At which the angle is delta naught, same angle what we have taken earlier, same angle, because areas are equal. And we might be touching omega is equals to omega s here, and here also omega is equals to omega s. But in between that, at the angle delta 1 or point C, we might be touching the speed as minimum number. But in the previous case, you might be touching to a speed of maximum number, omega max. Now you just show these areas. This is the area you can call A3, and this is the area you can call as A4. So this is area A3 I am calling, and this is the area I am calling as A4. Following? Yeah. So, sir, omega equals to omega s and omega greater than omega s, omega decreasing. And then omega minus omega s. You ask me that doubt, Yogeshri, please later. Okay. You want me to write anything? Is it needed? Is it needed to write? Tell me, please. Or else it is sufficient. You want me to write backswing? Sufficient. Good. Tell me, what are the final comment now? The operating point will be swinging in between B and D continuously. Between these 2 points, B and D continuously. And as time progresses, both will coincide towards the point C. And C is a final stable point to be expected. That's it. The final comments you write and draw delta versus time. Compare the delta versus time curve with the previous ones. Compare the delta versus time curve with the previous ones. And draw omega versus time also. Simple. Let's move. I will write quickly. Just copy it. A rotor will be swinging in between. Will be swinging in between points B and D. B and D with respect to time. Okay. So next I will say if damping is considered. Damping is considered. If damping is considered, look here. So the points B and D comes close together. Swing by swing with respect to time, and finally inclined onto point C. Onto the point C. Again speed at the point C. In the forward swing max, backward swing min, again max, min. Omega will vary between omega max and omega min. And finally, omega equals to omega s occurs at the point C. At point C, omega will vary between omega max and omega min. Continuously with respect to time. And finally, omega equals to omega s occurs. Okay. And finally, omega equals to omega s occurs. Write it quickly. Yeah, whoever is completed, please draw the swing curve and omega versus time also. Delta versus time you draw, omega versus time you draw, and compare these things with the fault studies what we have done. Transient stability analysis on a fault. Do that comparison. Yeah, so I'm moving ahead. The next slide. So finally at point C, you will get omega is equals to omega s, means d delta by dt number 0. But always accelerating power is 0, means d omega by dt value was 0. System reaches to steady state. By looking at these two statements, you write simply system reaches to steady state. Okay, after reaching to steady state, what we should check now? dp by d delta. How is the value of dp by d delta at this point? Positive, because it is in the positive slope region of the power angle curve, obviously. Okay, so I'll write at point C, dp by d delta is greater than 0. So system is stable. System is stable under steady state. Under steady state. Under steady state, the system will be stable. System is stable under steady state. Yeah. So what is the final stable angle now? Final stable angle. That will be delta 1. Delta 1, which is sine inverse of PS by P maximum. Sine inverse of PS by P maximum. Delta 1 is a final stable angle. That will be sine inverse of PS by P maximum. Yeah, okay. Next thing, delta versus time curve and omega versus time curve. Think. Swing curve, approximate swing curve, you can say. Approximate swing curve. It's a time axis and it was delta axis. And this is a time t naught. Up to the time t naught, we have an angle of delta naught here. Up to the time t naught, we have an angle of delta naught, something like this. Delta naught. Simple, simple. I'm asking you to observe 4 numbers, right? What is initial rotor angle? What's the maximum angle seen by the rotor? What's the minimum angle seen by the rotor? And what is the final stable angle? Only these things you have to check. Quickly. Delta naught, we have something. What is the delta max? What's the delta max? That is the value delta 2, which is greater than delta naught, of course. What is delta minimum? Delta minimum is what? Tell me. What is the minimum angle seen by the rotor? That will be delta naught only. That will be delta naught only. Means your angle versus time curve will be above delta naught. Above delta naught. And how is your final stable angle? It is delta 1, which is greater than delta naught. Final stable angle is delta f, which is delta 1 greater than delta naught. Let me draw these things quickly. Just as an indication. As an indication, it is a maximum angle seen by the rotor in the swinging, in the present swinging. And it's a minimum angle seen by the rotor in the present swinging. And this will be the final stable angle to be expected. Final stable angle to be expected. So it's a maximum angle seen by the rotor in the swinging, delta 2. Final angle is delta 1 and initial angle is delta naught. Simply you start with delta naught and draw some sinusoid and make it equals to delta naught finally. Okay. So you will be getting delta versus time curve, something like this. So what is the difference you are observing between this case study and the previous 3 case studies? Except first case study. Except the first case study, between the fault case studies we have, second one, third one, fourth one, and this 5th one. What is the difference between 2, 3, 4 to 5? What is the difference between 2, 3, 4 to 5? Minimum angle. Minimum angle. In the earlier cases, the minimum angle is coming below delta naught, right? Below delta naught means during short circuit fault, if you are doing transient stability analysis, minimum angle will come below delta naught and then will rise up, and it may settle to delta naught or may settle more than delta naught. That depends. That depends, right? But in this case, as well as in the generator case, mechanical input increment for the generator, minimum angle seen will be delta naught only. These are some small identifications you have to make. If he is asking to identify which are the following might be the possible stable swing curve. Like that, sometimes we used to get some questions in the exam. Okay, so just they will give 4 curves, 4 delta versus time curves. Which curve is possible? Which curve is possible for this type of disturbance? Like that, they may ask in the question. Okay, yeah. So let's move ahead. Let's move ahead. Next, omega versus time also I'll draw a bit quickly. Omega versus time also I'll draw quickly. So this is a time axis we are showing, and it is omega axis speed. Okay, so it is omega versus time, and it's a time t naught. Time t naught. Up to the time t naught, we have the speed as synchronous speed. Up to the time t naught, we have the speed as synchronous speed. Okay, next you call this a point A. Point A, very simple, very simple. Point A and B both are same. Point A and point B both are same. Next, from B to C, omega increasing. C to D, omega comes back to omega S. I'll show those lines also. Simple. It's a omega S line. I'm taking up omega S line. Simple. From B to C, omega is increasing like this. And C to D, it is coming back to synchronous speed. How is the second omega maximum? It will come down like this and it will go again to synchronous speed. How is the second omega max compared to first omega max? Anybody? Anybody, please tell me. How is the second omega max? Second omega max compared to first omega max. That will be less. By considering damping, Sajjan Singh and Abhijit, by considering damping, that second omega max will be less compared to first omega max. Okay. So just you draw that omega versus time curve simply like this. And finally, you are going to get that omega is equals to omega s. Finally, you will get omega equals to omega s. This is a expected omega versus time. Expected omega versus time. Okay. Next, some small conclusions again. Some small conclusions here. First one. So it was a power angle curves we have taken earlier. And what is the maximum angle seen by the rotor before which we should get omega equals to omega s? Maximum angle seen by the rotor before which omega equals to omega s should occur. Omega s should occur. Before which omega equals to omega should occur. That is nothing but angle at x point, right? That is nothing but angle at x point. Clear? What is that angle at x point? What is that angle at x point? 180 minus delta 1. 180 minus delta 1. You call it is delta x if you want. Delta x, which is nothing but 180 degree minus delta 1. What is the delta 1 value? Sine inverse of PS by P maximum 2. 180 minus final stable angle. That we should not cross. 180 minus final stable angle. That we should not cross. Okay, next thing. I'll show you in the next slide. Can we call this PS as TSL? Can we call this PS value as TSL? Yes or no? TSL, transient stability limit. Can we call this as TSL? No. We should not call this value as TSL. When we will call this as TSL? When we are going to call this as TSL? If you get omega equals to omega s exactly at x location, then we will call this as TSL. Okay, let me show that in the next slide. TSL. Just observe. So it's a delta axis and so power axis. I am showing power axis and delta axis, and it is P maximum 1 sine delta curve. P maximum 1 sine delta curve. I am showing P maximum 2 sine delta curve, something like this. Just observe. It's a PE1 curve without line removal, and it's a PE2 curve after line removal. Next, I am showing that PS line, something like this. It may be a possible one, that's why I'm drawing like this. And this is a point A, and we have moved to this point B after the line removal, and it is moving to this point C. And for example, after reaching to this point X, delta X, we are getting exactly omega is equals to omega s. Okay, so this is the PS. We have PS, and this particular PS value, we are going to name it as transient stability limit. And if you want to show the two areas quickly, this is the area A2 max, and this is the area A1. A2 max and A1 max. Okay, done. In this graph, that respective PS value is going to be called as transient stability limit. Transient stability limit. Done. So we'll do one previous gate problem on this. Previous gate problem. Okay, 1 minute. I have to check it. Check that problem once. Is the screen is visible? Tell me please. Whether the screen is visible or not. Yeah, okay. Only cap, okay. How is it visible screen? Tell me. Yeah. So I'm taking up this question. Please go through it. So asked in GATE 2007, but you have to learn something from this problem. That's the intention of discussing this problem actually. This problem will give a bit good clarity, even more clarity with respect to equal area criteria. Respect to equal area criteria, this problem will give you even more clarity. Go through it. Consider a synchronous generator connected to an infinite bus. Consider a synchronous generator connected to an infinite bus. Say this. Consider a synchronous generator connected to infinite bus by two identical parallel transmission lines like this. X reactance of these two lines are equal. X. Transient reactance of generator X dash is 0.1 per unit, as shown in the figure also 0.1 per unit. Okay, and mechanical power input to it is constant at 1 per unit. Mechanical power input to the generator is constant at 1 per unit. This PS value he said as 1. Okay. Due to some previous disturbance, so already some disturbance is there. Already some disturbance occurred, and rotor angle is changing between two values here. Rotor angle is changing between two values, undergoing undamped oscillations. If the undamped system is saying maximum value of delta equal to 130 degrees. Maximum angle seen by the rotor is 130 degrees. Okay. One of the parallel lines trip due to relay maloperation. Because of the relay maloperation, one of these two lines was disconnected, removed. Okay. At an angle of 130 degrees. At the instant of 130 degrees, it was disconnected, he is saying. The maximum value of the per unit line reactance X. Maximum value of the per unit line reactance X such that the system does not lose the synchronism subsequent to this tripping is. After the tripping has been occurred, system should not lose the synchronism. System should not lose the synchronism such that what is the value of X? Maximum value of X. Maximum value of X. Clear? See, showing in the next slide. Just let me repeat this diagram, what they said. This one I am copying. This is a single line diagram. See, this is a mechanical input, 1 per unit I am showing. Mechanical input PS is equals to 1 per unit. 1 per unit. Listen. See, before that line removal, what is the maximum power transfer capacity? Before line removal, that maximum power transfer capacity I will call as P maximum 1, which is 1 into 1. Voltages are equal, 1 into 1 by, what is the reactance value? 0.1 plus x by 2. So it is 1 by 0.1 plus x by 2. That's it. After that line removal because of relay maloperation. After the line removal because of relay maloperation, what is maximum power transfer capacity? P max 2. End voltages magnitudes 1 and 1 by 0.1 plus 1 of the line reactance is x. So it is 1 by 0.1 plus x, you can say. 1 by 0.1 plus x, you can say. Okay, simple, very simple. Just listen to my words. To make sure that the system is stable after the line removal, to make sure that the system is stable, definitely P maximum 2 should be greater than PS. P maximum 2 value should be greater than PS. Yes or no? For example, if the P maximum 2 is less than PS, then after the line removal, it will go into acceleration. That's it. System will be definitely unstable from the curves, you can see. See, P maximum 2 should be greater than PS is necessary. Is necessary condition, but it is not sufficient. To say that the system is stable. When it is sufficient means we should calculate the x value exactly. How much should be the P maximum 2 value required to make sure that the system is stable? That we have to calculate with the help of the equal area criteria. Okay, right. So you write it. So P maximum 2 must be greater than PS. It's a necessary condition, but not sufficient. It's a necessary condition, but not sufficient. It's a necessary condition, but it's not sufficient. Okay, now listen. Actually, on this system, already some disturbance occurred, and angle is continuously changing like this, as is showing in the figure. And one of the line, what he said here, it is going to be tripped. It's going to be tripped at this angle of 130 degree. At the angle of 130 degree. I will copy this swing curve also. I'll keep that in our solution. It may be helpful. I'm showing that here. Now let me draw power angle curves here. Let me draw the power angle curves. PE1 curve and PE2 curve first. So it's a delta axis and it's a power axis I am showing. Power axis. First, I'll call PE1 curve, P maximum 1 sine delta. P maximum 1 sine delta, PE1 curve. Like this we have. So it's a value of P maximum 1. We don't know that value also, right? P maximum 1 value also we don't know right now. Next, PE2 curve. So PE1. PE2 curve, P maximum 2 sine delta. Showing something like this. It's a PE2 curve. P2 curve. Now I will show PS line. Which is equals to 1 per unit. PS line which is equals to 1 per unit. Showing like this. Kindly observe. This is a PS line I am showing. PS line. Look all of you. Mechanical input line. PS. Listen. See, on which curve you are standing before the line trips? On which curve you are standing before the line trips? Very, very simple question. Very, very simple question. PE1 curve. You are standing on PE1 curve before that line is going to be tripped up. I am showing that angle 130 degree at which the line is going to be tripping out. Showing that angle 130 degree at which the line is going to be tripping out at this particular place. In the first case, I am showing that here. This is an angle delta is equals to 130 degree. Okay, at which the line is going to be tripped. At which the line is going to be tripped. I have taken some location first. I have taken some location. Whether it is a perfect one or not, to make sure that the system is stable, we have to discuss. Tell me, all of you, what is the speed at 130 degree? What is the rotor speed at 130 degree? Anybody? What is the rotor speed at 130 degree? Nobody is responding. Synchronous speed. Why? Why it is synchronous speed? Because the slope of delta versus time curve at that angle is 0. Slope of the delta versus time curve is 0. d delta by dt is equals to 0. So at 130 degree angle, we know d delta by dt value 0. So obviously you can say omega value is equals to omega s at that location. Omega equals to omega s at that location. Srividya, have you understood this? Omega is equals to omega s. Now listen. Omega equals to omega s. All of a sudden, that line was disconnected. Due to relay maloperation, that line was disconnected. After that line disconnection, simply what will happen is, this point what you said on the PE1 curve, it will fall onto PE2 curve like this. The point will fall onto the PE2 curve simply like this. Yes or no? Yeah, tell me please. Now the question is, this is your new operating point, right? This is your new operating point. What is accelerating power at this point? What is accelerating power at that point? Is it positive or negative? How is the accelerating power at that point? PS minus PE, right? PS is this number. P is this number. Shamala, PS minus PE. How is that? P is low compared to PS. Means PS minus PE is positive. So if the accelerating power is positive, omega will start increase. Omega starts increasing. Omega starts increasing means definitely omega will become more than synchronous speed, because already we have omega s there. Already we have omega s. So omega starts increasing and omega will become more than omega s. Then d delta by dt is positive. Delta will continue to increase. Delta will continue to increase, and that electrical power will change on this curve something like this. Electrical power will change something like this on this curve. You see, at all the time, PS minus PE positive, omega continue to increase and system will become unstable. System will become unstable. Getting my point? Yes. So if you choose delta location as 130 degree at this place, system is becoming unstable. So this may not be the location of 130 degree in order to make sure that the system is stable. I don't know whether you have understood this or not. Are you clear about this? So this angle we should not consider now. That angle we should not consider. Okay, good. Next thing. For example, I am showing that PS value, sorry, delta 130 degree, delta 130 degree location at some place here. Let me assume this is 130 degree location. Now all of a sudden, line was disconnected. This operating point of 130 degree will be shifted on to the PE2 curve, something like this. Shifted onto the PE2 curve, something like this. And this is your new operating point now. Tell me please. This is your new operating point. At this new operating point, how is the accelerating power? Positive or negative? How is the accelerating power? Positive or negative? Tell me. That is negative. See, if you have accelerating power negative, omega, what will happen? It will start decrease. It will start decrease from where? Omega s, because already we have omega equals to omega s at 130 degree. So omega starts decreasing from omega s, means omega less than omega s will happen. If omega is less than omega s, d delta by dt is negative, delta will decrease and rotor angle will change something like this, and the system will become stable. System will become stable. So this is a suitable one to be selected. I don't know. All of you clear about this? What's the conclusion now? What's the conclusion now? To make sure that the system is stable, whatever the new operating point we are getting just after the line removal, whatever the new operating point you are getting, that should fall in the deceleration region. Then only omega starts decreasing from omega s, d delta by dt comes negative, delta starts decreasing, and the system will be stable. Can I write that statement now? Can I write that statement? Yeah. Yeah, we are taking that 130 degree at various places. We are taking that 130 degree at various places and we are checking which is suitable. We are taking that 130 degree at various places. It is more than 90 degree. More than 90 degree at any place you can select, right? 130 degree. I am taking it some place, checking whether it is suitable or not. For example, you take it the first one. It is jumping down just after line removal. And after staying at this point, accelerating power is positive. PS minus PE positive. Omega will increase. Already we have omega s. From omega s, it will increase means omega greater than omega s occurs. D delta by dt is positive. Delta will continue to increase like this. And always PA is negative. System is unstable. But so if you take 130 degree at this place, the system is becoming unstable. Let us take one more location. I am locating that 130 degree here. By locating 130 degree here, once after line removal, it is falling on to PE2 curve, but at this location, accelerating power value was negative. As accelerating power is negative, omega is decreasing. Omega decreasing means omega less than omega s will occur. If omega is less than omega s at this point, d delta by dt is negative. D delta by dt negative means delta will decrease and rotor what you call operating point will move down in that manner. Yeah. You do it if it is given 160 degree. What's there in that? You do that one, you'll get it. Look here. So I'll say to make sure that the system is stable, system as stable, the new operating point just after line removal should fall in deceleration region. Okay, so therefore PA new value at an angle of delta equals to 130 degree shall be less than 0. New accelerating power at delta equals to 130 degree should be less than 0. What is it? PA new? PS minus P maximum to sine delta. Sine delta means sine 130 degree. It should be less than 0. Okay, so you can keep the PS value as 1 and P max 2 is 1 by 0.1 plus X you have, and it is sine 130 degree, and this is less than 0. You do this calculation and finally you will get this X value less than 0.667. You do the calculation. Ultimately you will get this type of answer. Check that once. X value should be less than 0.667. Yeah, all of you getting it? Now tell me. Tell me here. You have 4 options here: 0.87, 0.74, 0.67, 0.54. Which is a suitable option? Which is a suitable option? Yeah, that is C, 0.67. 0.67 is a suitable option. Correct answer will be C. What is asking? What is asking in the problem? Maximum reactance value. Is asking the maximum reactance value. Maximum reactance value. For example, you say X less than 0.667. Okay, if you move to the options what they have given, less than 0.667 means 0.54 you may get. Okay, 0.54. For 0.54 line reactance, system will be stable after the line removal. But above 0.54 also system is stable, right? For example, rather than 0.54, if I keep 0.6 per unit, then also system is stable. Then 0.54 is not the maximum reactance allowed. 0.54 is not the maximum reactance allowed. What is the maximum reactance is? Simply whatever the thing you calculated, that number you have to give as your answer. Correct option will be C only. It's not D. It's not D. For D, the system is stable. Okay. For D, the system is stable. Yeah. So we'll stop at this point, this study. And if you have any doubts, you can ask me. Yeah. One more thing, a small announcement here. From tomorrow, we don't have F&S class. From tomorrow, there is no F&S class. We have F&S class in the next Sunday. Next Sunday, right? Next 2 Sundays, coming 2 Sundays. Coming 2 Sundays. Coming 2 Sundays, it will be 2 p.m. to 9 p.m. I will be taking the class. F&S, and by the next 2 Sundays, it will be completed. It will be completed. So today it is 4th. 4th in the sense 4 plus 7. It will be 11. 11th July is one day, and then 18th July is a other date. In these 2 days, I will be taking up the class from 2 p.m. to 9 p.m. to finish the syllabus. It's a kind request from my side. It's a kind request from my side. Okay. Yeah, you might be having some other class. I don't know from tomorrow. From tomorrow, they will upload it. They will update. They will update it. Okay. Yeah. See, after this one, yeah, by the next 2 Sundays, I will complete the syllabus. I will complete the syllabus surely. After this one, we have synchronous motor case study. One thing, synchronous motor case study. It may take hardly 45 minutes. 45 minutes, not more than that. After that, we have to discuss methods to improve the transient stability analysis. It may take half an hour. Maybe within 1.5 hours, we'll complete this stability part, and then we'll start YBus and JetBus. Mostly by the next Sunday or 18th July, first hour, we'll finish the power system matrices, and then we'll complete the load flow on that 18th July. Okay. It's a kind request from my side to adjust this schedule. Load flow analysis, I will discuss on the 18th July. On 18th July, I will discuss the load flow analysis. 11th July, I will discuss the power system matrices. I will upload the answer key tomorrow or day after tomorrow. Okay. Please kindly adjust. Please kindly adjust with this. Thank you. If you have any doubts, you can ask me. Yeah. So you can ask your doubts. You can raise your hands. I'm making all the hands low. Kindly, I'm making all the hands low. Please raise your hands now. Please raise your hands again. Please kindly raise your hands again. Ashish Raj.
Hello, sir.
Tell me, Ashish Raj.
Sir, about that Pmax one, how means I don't understand that if it will increase, how it will make the system more stable.
Max one, actually, that will alter the initial operating point. The
Sir,
delta
means,
naught initial operating point will come down, right?
sir means that delta CR, there will be no difference.
There will be a change in the value of delta CR also at that time.
Sir, will it move towards 0?
No, it won't move towards 0. It may come down, right? Delta CR may come down because of that.
So that's only I was not understanding how it will come.
You have to calculate it, right? Delta CR for that new value. For that new P maximum one value, you have to calculate delta CR newly.
Okay, sir.
Based on that, it will change.
Okay, sir.
Okay.
Okay, sir.
Yeah.
Thank you, sir. One problem, sir. Hello, sir.
Tell me.
Sir, that gate problem, sir. This 21, sir.
21.
Yes, sir. Means 20. This recent year, sir. Of
Okay.
that fault analysis, sir. There is that. Let's see. In book that question number 29, sir. So here is IB mod of IB upon IR. It is asking, and sir, there is no any source, sir. Means which
you
type of
assume the source is a balanced source. Balanced source.
Yes, sir. Means that source will be star or sir delta.
You take okay. What is it?
So it's simple. Three-phase.
Can you read?
Yes, sir. A three-phase balanced voltage is applied to a load zone, and the three-phase sequence is RYB, and we have to find the ratio of IB upon IR.
Tell me page number.
So book page number, sir, 387.
387. See, he is asking that ratio IB by IR, right?
Yes, sir.
See, as a neutral is not connected to ground in this case.
Yes, sir.
You have to assume the line-to-line voltage as balanced.
Okay, sir.
Already you are saying your three-phase balanced source is applied for that.
Yes. Yes.
Means your line-to-line voltage will be balanced.
Voltage.
Okay, you see this. This is one load minus J 10 ohms. And this is other load. It is J 10 ohms. And this is not having any load. Okay, so like this you have. And these are the locations RYB.
Yes, sir.
And you see the line-to-line voltage I am saying RYB sequence only you have to take because he said in the problem. It is VRY. It is VYB. Okay. And this is VBR plus minus. It is VBR.
Yes.
Done. Now you assume VRY is equals to some mod V at an angle 0 degree.
Yes, sir. Actually, I was assuming it to be star connected.
VYB is a mod V at an angle minus 120. VBR is a mod V at an angle plus 120 degree. Now what's your doubt?
So I was doing like that. I was connecting means star source, means star connected source, and I was using VR, VY, and
VR across minus J10, VB across J10. That you are doing.
Yes, sir. Yes, sir. Yes.
It is not suitable, right? Because this neutral is not connected to ground, huh?
Okay, so first that comes first
simple,
in my mind.
Very simple, basic thing, Ashish.
Yes, sir.
How come you say this voltage is equals to VR? Tell me, how? By applying KVL only you have to say, right?
Mhm.
By
Yes, sir.
applying KVL only, you should say that voltage is VR, right?
Yes, sir. Yes.
But as your load neutral is not grounded, you should not say this is VR.
Yes, sir.
But I can say line to line voltage equals to VRY by applying KVL here.
Mhm.
So that
Yes, sir.
VRY will appear across this one. VYB will appear across this one. Okay.
Yes, sir.
Now you
Yes, sir.
calculate this IR current how much, and you calculate this IB current how much based on these values.
Okay, sir.
Then you take up the ratio. You will get it.
Yes, sir.
Okay.
Okay, sir.
Yeah.
Thank you, sir.
Okay. Fine. Imtiaz.
Good evening, sir.
Good evening, Imtiaz.
Sir, last problem, sir.
What you have doubt in that?
Sir, we are getting access exam 0.667 no, sir.
Okay.
I'm not understand 0.54 you not taking.
Okay, if you choose 0.54,
Yes, sir.
the system is stable or unstable?
Stable, sir.
For 0.6,
This also stable, sir.
then 0.54 is not maximum reactance, right? What is asking the problem?
maximum
What
value
is the
of
maximum value of per unit value of X such that the system will not lose a synchronism? For 0.54 system is stable, but it's not maximum reactance. Na? Above 0.54 also system will be stable only, right?
Yes, sir.
So 0.54 is not the option for you.
If in question it's not given maximum value, at that time we can take 0.54.
Then both will be correct, C and D.
Which will correct, sir.
Hmm.
Sir, one more, sir.
Tell me.
Sir, how can we set that transient limit for the PA for PA?
For?
In the in the curve in the sir, P versus delta. In that, how can we set that this is a transient limit? PA
What is transient stability limit for definition? That is the highest amount of power flowing in the network such that the system will not lose synchronism for a large disturbance.
Yes, sir.
Yes or no? What is power flow in the network at any time? Is it with fault or without fault, whatever it is? PS.
Yes.
PS is the power flow in the network, right?
Yes, sir.
As a PS is power flowing in the network in the pre-fault condition,
Yes,
at
sir.
that time, if you have a fault and if the system is capable to withstand,
Yes, sir.
okay, so for that PS value, we will say system is stable.
Okay.
Are you understanding me?
Yes, sir.
You take some PS value, take some disturbance, system is stable. Okay?
Okay, sir.
For that PS value means for that initial power flow, system is stable for the disturbance what you have taken.
Yes.
What is the highest value of PS? What is the highest value of PS? Such that the system will not lose synchronism for a given disturbance.
At point X.
That is a value of TSN.
Okay, sir.
Okay. And from the graph, what we are saying is whenever we are getting omega equals to omega s exactly at the point X, that particular PS value what we have there, that is a value of TSL.
Okay. Yes, sir.
Understanding, Imtiaz?
Yes, sir. I understand. Sir, one
Any
more.
other doubt you have?
Yes, sir. In problem is there, no, sir. Omega is equal to 18.85 electrical radian per second.
13, 18.
Yes, sir.
13, 18, where we have?
In calculation at the last time we can get to pi FC equal to.
Okay. Tell me, what's the doubt you have?
Sir, can we convert 13.18.85 to mechanical radians?
You can convert it.
Where omega equal to 2 pi n by 60. Can we take?
You can do it. But this is electrical and you convert this into mechanical and then make it equals to 2 pi n by 60 and calculate speed n.
Sir, how can we convert sir electrical to and P by 2?
Multiply with 2 by poles.
2 by?
Poles. 2 by number of poles.
Okay, sir.
Okay?
Sir, one more is it? Sir,
Tell me.
for transient stability of the power system, what are the conditions or can we take? For example, P of dp by delta must be greater than 0, no, sir.
Yes, correct.
And d delta by dt must be equal to 0.
0. Yes.
But in workbook,
That's your answer. Leave it. Don't tell me. That's your answer. That's it. Whatever you said is correct answer.
Okay.
Don't consider the remaining things what they have given there.
Sir, one more.
Tell me.
Sir, for two machines, the moment of inertia will be m1, m2. The possible number of the equivalent moment means 3, no, sir?
It will be 2. Why 3?
Sorry, 2, no, sir.
2. Not swinging.
Yes, but in answer is 3. That's something.
Okay. That's 2. That's it.
Means answer is wrong in.
Yeah.
Okay. That's all. Thank you, sir.
Yogashri.
Sir,
Tell me, Yogashri.
back swinging ఒకసారి
Which one?
back swinging.
Which case study?
Case 1 ఉంటుంది సార్. Case 1 ఉంటుంది.
Case 1. Yesterday class.
టుడే క్లాస్ ఉంది సార్. బ్యాక్ స్వింగ్ అని ఒకటి పెట్టారు సార్. పెట్టింది.
We kept back swing in various case studies, right? In which case study you want?
Sir, the circuit LL fault circuit is there, sir.
Okay.
మనము ఆ సర్క్యూట్ లో లైన్ టు లైన్ కాకుండా లైన్ టు న్యూట్రల్ కి కనెక్ట్ చేస్తున్నాం కదా సార్ అన్ని. అది ఎలా నాకు అర్థం కాలేదు సార్. ఒకసారి చెప్పండి.
Those are sequence networks only, Yogashri. We discussed those sequence networks in fault analysis, right? In case of LL fault, you connected positive and negative sequence circuits in parallel in a per phase manner.
లైన్ టు లైన్ కనెక్ట్ అవుతుంది కదా సార్.
Listen. Wait. This is one alternator, right? And these are ABC lines, star grounded. We have a double line fault between B and C, like this. Okay. What we said, with respect to fault location, you construct the positive sequence network, right? And with respect to fault location, you construct the negative sequence network. This is a fault location here, and this will be VA1, and current is IA1 at this place. Voltage at this place is VA2, current at this place is IA2, and to find out the sequence currents, we have to connect these two circuits in parallel. Have you studied this one?
Yes, sir.
Forgot fault analysis already.
Yes.
Just read fault analysis once again. Read fault analysis once again. There we have discussed about it. In the similar manner, we have given the connection in the LL fault also. Tell me, Yogashri, are you understanding?
అంటే ఇప్పుడు ఈ ఇండక్టర్ మిడిల్ లో కనెక్ట్ చేసినట్టు సార్.
Which inductor?
మిడిల్ లో మనం రియాక్టెన్స్ కనెక్ట్ చేసాం కదా సార్.
Okay.
అది ఒక లైన్ నుంచి న్యూట్రల్ కి కనెక్ట్ చేసి ఉంది కదా సార్. అది ఎల్ఎల్ కి కూడా అలానే కనెక్ట్ చేసాం కదా సార్. లైన్ టు లైన్ కి
ఒకసారి నువ్వు ఫాల్ట్ అనాలిసిస్ ఒకసారి చదవమ్మా మొత్తం. యుగశ్రీ హలో
సార్ చెప్పండి.
ఒకసారి ఫాల్ట్ అనాలిసిస్ మొత్తం ఒకసారి చదువు. మళ్ళీ ఎల్ఎల్ ఫాల్ట్, ఎల్ఎల్జీ అవన్నీ ఒకసారి చదువు ఒకసారి. ఓకేనా?
సార్ ఇంకొకటి సార్,
అంటే నువ్వు మర్చిపోయినట్టున్నావు ఆల్రెడీ ఫాల్ట్ అనాలిసిస్. ఒకసారి మళ్ళీ చదువు. ఒకసారి మళ్ళీ చదివితే నీకు ఇవన్నీ మళ్ళీ రీకాల్ అవుతాయి. దెన్ యూ కెన్ ఫాలో ద థింగ్స్ వాట్ వి డిస్కస్ టుడే. ఓకే
సార్, ఒక లైన్ కి ఫాల్ట్ వచ్చినప్పుడు 3 పోల్స్ ఓపెన్ అవుతాయి అని అన్నారు సార్.
we have to open. Why? In the sense, for LG fault, if you open only the faulted phase, it will act as open circuit. Remaining 2 phases are connected, right?
Yes, sir.
Then it will be like a one open conductor fault.
3 కనెక్ట్ చేస్తే 3 ఓపెన్ సర్క్యూట్ అవుతాయి కదా సార్.
Then it is a no load operation. There is no open circuit fault, right?
ఎస్ సార్, 0 ఉంటది కదా సార్ కరెంట్.
Yes, that complete line is disconnected. There is no open circuit.
మీరు 3 ఒక దానికి ఒక లైన్ కి ఫాల్ట్ వస్తే 3 పోల్స్ ఓపెన్ చేయాలి అని అంటే అప్పుడు 0 కరెంట్ వస్తుంది కదా సార్ అంటే.
Yes, correct. Correct.
అదే ఎందుకు ఓపెన్ చేస్తాము 3 ఒక 2 లైన్స్ ఫాల్ట్ రానప్పుడు ఒక లైన్ వచ్చింది అది క్లియర్ చేసుకుంటే అయిపోతుంది కదా సార్. మళ్ళీ 2 దానికి కూడా ఎందుకు తీస్తున్నాం?
ఇది వినమ్మా ఒకసారి విను. ఇక్కడ ఇది ఒక సిస్టమ్ ఉంది మీకు, ఓకేనా? సో ఫర్ ఎగ్జాంపుల్ యూ హ్యావ్ సింగిల్ లైన్ టు గ్రౌండ్ ఫాల్ట్ ఆన్ phase A like this. Okay, you opened only phase A conductor. Phase A conductor you have opened. So phase A is not carrying any current, but B is carrying some current, C is carrying some current. What is this fault? Yogeshri, are you there?
ఎస్ సార్.
Tell me, what is this fault?
ఓపెన్
One open conductor fault. Yogeshri, are you understanding what I am saying you?
ఎస్ సార్. ఓపెన్ కండక్టర్ అయింది సార్.
Single line to ground fault occurred. We opened the phase A conductor. B and C are carrying their own currents. Then LG fault was cleared. LG fault was cleared, but it is converted into one open conductor. Please kindly respond. Have you understood this?
ఎస్ సార్.
Yeah. Now, if this is a case of opening, it is leading to one open conductor fault. Then what you are suggesting here? Open all the 3 poles of this circuit where you are operating. If you do that, this B and C currents also 0. It will act as open circuit. What's the problem to you now? No open conductor fault, right? Yogeshri, please kindly respond. Any doubt you have? Tell me.
Yes, sir. Okay, sir. Clear.
Tell me, Yogeshri. Don't hesitate. Tell me what's your doubt here.
అదే సార్ 2 లైన్స్ కి మనము మంచిగా ఉన్నదాన్ని ఎందుకు మళ్ళీ తీసేస్తున్నాము?
Because of one open conductor you are having over voltage issues. Some issues are there, right? Because of open conductor fault, you have some issues of over voltage and some sort of unbalancing operation of loads and all. To overcome the things, if you are disconnecting any one of the wire, don't disconnect one wire, disconnect all the 3 wires.
ఓకే సార్. సార్ ఇంకొకటి మీరు ఒక సెంటెన్స్ రాశారు సార్, రోటర్ ఈజ్ విల్ బి స్వింగింగ్ అని ఒకటి సెంటెన్స్ రాశారు కదా సార్. అది రోటర్ అనేది రొటేట్ అవుతూనే ఉంటుంది కదా సార్. అప్పుడు
Swinging with respect to infinite bus. You sit on the infinite bus and you look at the rotor. If it is rotating at synchronous speed, that is stationary. Yes or no?
Yes, sir.
And after giving the disturbance, that will be making some oscillation. That's what we are saying, swinging.
Okay.
Okay, na?
Okay.
For example, if it is an infinite bus, we are standing on the infinite bus, and this is our rotor on which we are doing analysis. And how is this rotor looks to you if it is rotating at omega s? Stationary.
Okay, sir.
Okay, but after giving the disturbance, you observe that this rotor is going to make some oscillations between these 2 points continuously.
Okay, sir.
Okay, that is the swinging what we are saying with respect to infinite bus or infinite reference.
Okay. I understood, sir.
Understood?
Yes, sir.
Okay. Any other doubt you have, Yogeshri?
No, sir.
That's it?
Yes, sir.
Yeah, fine. Naveen.
Hello, sir.
Tell me, Naveen.
Sir, what are the important topics, sir, in fault analysis and the stability, sir?
We can't say. We have to read all.
Sir, means in weightage, so syllabus is vast, no, sir. So weightage criteria based on that, tell, sir.
Oh, actually, if I say some topic is important, you will
Yes,
get a question in the other topic. That is this subject significance.
Okay.
Okay, can't say exactly from which area we are going to get the question. We have to read all the areas in this particular subject.
Okay, okay, sir.
Hmm?
Okay, sir.
Okay. Prithviraj,
హలో సార్
tell me Prithviraj.
సార్ మనం ఫాల్ట్స్ కి డిఫరెంట్ ఫాల్ట్స్ కి స్టడీ చేసాం కదా సార్ ఎల్జీ కంపారిజన్
Yeah.
బిట్వీన్ వేరియస్ ఫాల్ట్స్ విత్ రెస్పెక్ట్ టు
Yes, yes,
స్టెబిలిటీ
yes. Hmm.
సార్ ఈ కేసులోకి వచ్చేసరికి మనం పాజిటివ్ సీక్వెన్స్ నెగిటివ్ సీక్వెన్స్ జీరో సీక్వెన్స్ ని కన్సిడర్ చేసాం సార్
Yeah.
ట్రాన్స్ఫర్ రియాక్టెన్స్ కట్టడానికి.
Hmm. Hmm.
కానీ మనం కేస్ 1 అయిపోయాక ఫాల్ట్ స్టడీస్ స్టార్ట్ చేసే ముందు కేస్ 1 అయిపోయాక మనం సమ్స్ చేసాం కదా సార్ ఫాల్ట్స్ మీద.
Yeah.
అక్కడ ట్రాన్స్ఫర్ రియాక్టెన్స్ కట్టేటప్పుడు మనం ఎందుకని సార్ సీక్వెన్సెస్ కన్సిడర్
We have
చేయలేదు?
taken only fault as three-phase fault, right?
ఓకే సార్.
Even in the exam,
సార్
even in the exam, if they said simply fault in the stability analysis, you should consider the fault as three-phase fault only.
ఓకే సార్.
Why?
Because they are opening circuit breaker at a time for all the three.
No, that's not the thing. Actually, this is a most severe fault, right? With
Okay,
respect
sir.
to stability.
Okay, sir.
If your system is stable with respect to three-phase fault, then definitely it will be stable with respect to LG, LL, and LLG.
Yes, sir. Yes, sir.
That's the reason why we do only on three-phase fault.
Okay, sir.
Okay?
Okay, sir.
It's not of easiness, strictly. It's not of easiness.
Okay, sir.
Okay, as it is most severe fault, we are doing on it.
Okay, sir.
That's the way
Sir,
how the people have designed the subject.
Yes, sir.
Yeah. Tell me.
Sir, one more doubt is recent problem is there, na, sir? Last problem, gate problem.
Yeah.
Sir. Here, let us consider, sir, we have taken delta is equal to 130 degrees. It is falling at a X point.
Okay.
Means delta max point. When we write down d delta by theta and d delta by dt and d omega by dt, both are becoming zero at that point.
At what point?
X point, sir, means delta max. Delta is equal to
Okay,
130.
okay. That you take. At that point, it will stop and your system is unstable. That's what I have done here also, right?
That's my doubt is, sir, if you are considering x is equal to 0.67, pi is becoming 0, d delta by dt is becoming 0. So it will reach the steady means a steady state condition there at that point. It will not oscillate. So when it is reaching steady state at that point, we are checking for steady state stability dp by d delta. Then it will become
Okay,
negative.
okay. I will accept with you, Prithvi.
Yes, sir. Then
But the thing
d
is,
will be the answer.
listen. D is the answer if you are choosing. What is the D value? D reactance value?
0.54.
For 0.54, system is stable or unstable?
System is stable.
For 0.6,
0.6 stable.
what is asking in the problem? Maximum reactance. Not simply the what is the value of reactance for the system for which the system is stable.
Okay, sir.
Yes or no?
Maximum reactance for which system is stable, but for 0.67
System will not
is
lose a
unstable.
synchronism. System will not lose a synchronism.
At 0.67, sir.
0.67 or less than 0.67 you have to consider. He's
Okay,
asking
sir.
maximum value, right?
Yes, sir. Yes, sir.
Maximum value you take 0.67. Less than that number, any value you take, system will be stable. That is the meaning there.
Yes, sir. Yes, sir.
That does not mean that if you take 0.67, the system will not lose a synchronism. Maximum 0.67. Below that number, you choose any value. System will be stable.
Okay, sir. And sir, one more normal doubt, sir. Means starting లో మనం దీన్ని చదువుకున్నాం కదా సార్ స్టడీ స్టేట్ స్టెబిలిటీ టైంలో.
Yes.
మనం సింగిల్ డబుల్ మెషిన్ కనెక్ట్ అయి ఉంటే 600 మెగావాట్ దగ్గర PS1 PE PS2 మొత్తం అన్ని ఈక్వల్ అయినాయి సార్.
Okay.
నెక్స్ట్ నేను లోడ్ పెంచి 605 మెగావాట్ చేశాను సార్. అప్పుడు ఇదేమో ఎలక్ట్రికల్ పవర్ ట్రాన్స్ఫర్ 590 మెగావాట్ పడిపోయింది సార్ డెల్టా పెరగడం వల్ల.
Yes.
నేను ఇదేమో ఉమేజీ PS1 స్టీమ్ ఇన్పుట్ పెంచి 605 మెగావాట్ చేశాను సార్.
Yes.
ఈ కండిషన్ లో ఈ నెక్స్ట్ కండిషన్ ఏమవుతుంది సార్? మనం అంటే ఈ కండిషన్ వరకు డిస్కస్ చేసుకున్నాం సార్. నెక్స్ట్ కండిషన్ ఏమవుతుంది సార్?
Next, that electrical power will continue to fall down, right?
సార్ మీన్స్ 590 మెగావాట్ ఏమో ఎలక్ట్రికల్ పవర్ ఉంది, అవుట్పుట్ పవర్ ఏమో
That will
605
come
మెగావాట్.
down, right? That will come down.
అది ఎందుకు సార్? అది
Because you see your what's the load on your rotor? Of the
605
motor.
మెగావాట్ సార్.
605 megawatt is a output power what you need from motor.
Yes, sir.
But input power, how much you are giving?
590 megawatt.
Then there is what we call output is more compared to input. then speed of rotor will fall down.
కంటిన్యూస్ డిసెలరేషన్ ఉంటుందా సార్?
Continuous deceleration, delta will continue to down and electrical power, sorry, increase, and electrical power continue to decrease.
ఓకే సార్. ఇఫ్ స్టీమ్ ఇన్పుట్ మనం పెంచకుండా వెళ్ళకపోతే అది అంటే కంటిన్యూస్ గా అలా పడిపోతుంది.
Then also, even you don't disturb the steam input also, but still your system will become unstable, right?
Yes sir, yes sir.
Only a very simple rule, Prithviraj.
Sir.
If output energy demand is more compared to input energy,
okay sir,
system will not sustain.
Okay sir. Okay sir.
Okay.
Thank you sir. These are my doubts.
Yeah. Ankur.
Hello, sir.
Tell me, Ankur.
Sir, my doubt is in last year question, 2014 question. It's in question being page number 381.
Okay, tell me.
Question number 6, sir. I could not solve, sir.
Have you gone through the solution?
Yes, sir, but sir, I did not understand.
Okay, you take fault at F1.
Yes, sir.
Take the currents as IF1 and voltage as VF1.
Yes, sir.
That's it. Have you taken those locations perfectly? Locations.
Yes, sir. I took.
And then fault at F2, current IF2, voltage VF2.
Yes, sir.
So like this you have. This is EA at an angle delta. And this is a bus A. And this is a bus B. It is EB at an angle 0. Okay, it is EA at an angle delta. F1 location fault I am taking. This is F1 fault. F1 fault. Where is IF1 current?
From the generators.
Huh?
From the generator side, sir.
Where I have to show IF1 current? Here can I show IF1?
Yes, sir.
How? Why I should take IF1 here?
No, sir.
What he said in the problem? Where he is showing IF1 in the problem?
From the bus A.
This is IF1
Yes, sir.
and this is VF1 voltage at this bus.
Yes, sir.
But whenever you have a fault at F1,
Yes, sir.
whenever we have fault at F1,
Yes, sir.
and you assume this whole network is reactive in nature, and
Yes.
this generator B is supplying a lagging current
Yes,
in
sir.
this direction,
Yes, sir.
and this generator also supplying lagging current in this direction.
Mm.
So
Yes,
you
sir.
assume it is IFB current, IFB, and flowing in this direction, IFB going down.
Yes, sir.
Yeah, tell me now, IFB current lags VF1 voltage, can I say? Because as
Yes,
it's
sir.
a lagging current for you, at all the places it will be lagging with respect to its own voltage.
Yes, sir.
For example, you take bus B voltage is something like VB. So I will write IFB is in lagging with respect to VB. And similarly, this bus A voltage is VF1.
Yes, sir.
So IFB is in lagging with respect to VF1.
Yes, sir.
But what is IF1 current here?
Only from the bus A side.
What is that? Negative of IFB, right?
Yes, sir.
So if IFB is a lagging current for you, negative of IFB will become leading current.
Okay, sir.
Just 180-degree opposite.
Yes, sir.
So I can write here, capital IF1 leads VF1. Yeah, please kindly ask me if you have any doubt.
Yes, sir. I understand, sir.
Okay, then what you can write in reverse? VF1 lags IF1, can I write? In reverse. Current
Okay,
is in
sir.
leading with respect to voltage, means I can say voltage is in lagging with respect to current, right?
Yes, sir.
That's it. So this is one option what we have to choose.
Yes, sir.
Now F2 location you consider. Same diagram I have repeated. Where is F2 location? Kindly identify that. Where is F2 location? Fault.
Between bus A and bus B.
Between bus A and bus B. This is a F2.
Yes, sir.
Where is IF2?
From the bus A.
This is the direction of IF2 or reverse direction?
The same directions.
Same direction. IF2. Where is VF2?
In bus A.
Bus A. Fault taken at F2.
Yes, sir.
And this source A will supply lagging current.
Yes, sir.
Because of reactive network, I am saying. Because of
Yes, sir.
reactive network, source A will supply lagging current. Source B also
Yes.
supplies lagging current.
Yes, sir.
Then this is IFA. And IFA will be in lagging with respect to VF2, can I say? Yes or no?
How, sir?
IFA is in lagging with respect to VF2.
Yes, sir. Yes, sir.
It will be a lagging current with respect to all bus voltage further if we take.
Yes, sir.
So I can write IFA lags VF2. But what is IF2 current here? IF2 current that we need, right?
Yes, sir.
How is IF2 current? Tell me. What is the IF2 current? Ankur,
In the same direction. I think in the same direction.
tell me what is that name, Ankur? What is the IF2 current, Ankur?
In the same direction with.
What is that?
iPhone.
What is that? I am asking you. What is that? IFA.
Yes, sir. IFA.
What is IF1
From
in the
the,
first case? What is the IF1 in the first case?
Minus.
What is the value of IF1 in the first case? What happened here? IFB is flowing in this direction. IF1 is in opposite direction. IF1 equals to minus IFB we have written. That I am asking very simple question, Ankur. Just look at the diagram and tell me the answer. Understanding, Ankur?
Yes, sir. I have to. Will be in the same direction with iPhone.
So what is IF2 now?
With the same direction of iPhone. IFA.
In this diagram, you tell me what is IF2.
IFA.
So simply you replace this IFA with IF2, right?
Yes,
So
sir.
here at IF2 lags VF2.
Yes, sir. You can write.
What you can write from this now?
VF2 leading
That's
IF2.
VF2 leads IF2. So
Okay,
you have
sir.
to choose the option according to this.
Okay, sir. Thank you.
Any other doubt you have, Ankur?
No, sir. Thank you, sir.
Matthew,
Hello,
tell me, Matthew.
hello, sir.
Tell me.
Hello, sir.
Tell me, please, Matthew. Rosemary. Rosemary. Rosemary, please tell me, Rosemary.
Hello, sir. Am I audible?
1 minute, Alan. 1 minute, wait. Rosemary, are you able to listen? Alan,
Hello, sir.
tell me.
Am I
Alan.
audible?
Tell me.
Sir, in the transient stability limit definition, it is the highest amount of power flow in the network, no, sir? Sir, network is P, no, sir?
PS is a power flow, right?
Sir, PS is the input to the generator, no, sir?
That is the initial power flow what you have before creating the disturbance.
Yes, sir. but
That itself is that highest value is how much? That's the thing. You should not take that P is varying, which value we have to take. That's not the thing.
Okay,
You
sir,
are
because
getting a doubt that why can't I take P max 2 sir or P max 3? That's your doubt, I know.
yes, sir.
That's not the value. Initially, how much is the power flow we have? What is the highest value of that? For which if there is a disturbance, system will not lose the synchronism.
Okay, sir.
PS.
Good.
Okay.
So then, in comparison between various faults in that
Hmm.
topic, the conclusion we reached that the triple LG fault will be the will be the highest severity, right? Will
With
cause the
respect to
highest.
stability.
Yes, sir.
Hmm.
So in questions while they give, they always refer three-phase fault, right?
You go through the question and whether they have given the statement or not, that you check first.
Sir. So if it is
Definitely,
given,
with respect to fault or with respect to stability, they will give.
okay, sir. In questions of stability, if it's given specifically like LG fault, then we have to take the sequence which you have given, right?
Yes.
Which we have derived. Okay, sir. But in general, we use the three-phase one.
Three-phase. Mostly they will ask questions on three-phase one.
Okay, sir. Thank you, sir.
Yeah. Rosemary. Rosemary, do you have any doubt? Yeah. Subtle.
Hello.
Tell me, Swapnil.
Hello.
Tell me, please.
Sir, actually, yes, sir. Actually, I sent one question on Telegram about fault. Sir, can you see this?
What is that question?
Sir, it about fault.
Okay.
Okay, sir.
What is that question? Please read.
The system shown in the figure is supplying.
Okay. What's the doubt you have now?
Sir, actually here they given transformer having 66 kV, 12 kV rating, and infinite bus rating is given as 11 kV. So in that case, there is a difference between that voltage. So how should we tackle this problem, sir?
What is that? Difference.
Sir, yes, sir. Actually, sir, they given 12 kV as the secondary, second transformer secondary voltage, and infinite bus voltage is 11 kV. So, sir, there is a two different voltage. So, how should we choose, sir, this?
See, what is the 12 kV? Can you tell me?
12 kV is a transformer voltage. Actually, second transformer secondary voltage means actually infinite bus side voltage of the transformer.
Kindly listen. What is the 12 kV given there? Okay, you said it's a secondary voltage of the transformer, second transformer. That's okay.
Yes, sir.
What is the 12 kV?
Actually, rated voltage of transformer.
That's not operating voltage.
Okay.
Why you are bothering about it?
Okay, means we have to assume that transformer is working at 11.
Rated for 12 kV, but infinite bus voltage is 11 kV.
Okay. Means, sir, in this question we have to just calculate the infinite bus impedance Z, and after that we can proceed, na?
Infinite bus?
Means, sir, they said that
you have to consider the pre-fault conditions also here in this problem strictly.
Sir, actually,
He said, listen. He said he is injecting some power of 50 MVA, 11 kV, 0.8 power factor lagging to the infinite bus rate.
Yes, sir.
Based on that, you have to calculate the pre-fault current value.
Okay, sir.
After
Actually,
calculating pre-fault current, you should calculate the induced EMF in the generator, subtransient induced EMF in the generator.
Okay. Sir, actually, I saw another method for this problem. Like that, we have to just calculate the impedance of both sides.
That's a stupid method. Leave it. Current division.
No, sir. No. Actually, we have to just calculate Thevenin voltage at the fault side, and based on that voltage, we have to just divide that voltage by a two-side impedance.
That's what I am saying. That's not the proper method I am saying you.
Okay.
That current division method you are saying me.
No, sir.
Listen, whatever the fault current they will calculate, that they will keep at middle and they will ask to distribute that current between the two impedances.
No, sir, not actually that way. I'm just saying that we have to find the Thevenin voltage at at fault point.
Hey,
By
leave it. Just listen.
yes, sir.
It is your pre-fault circuit,
Yes,
transformer, line.
yes, sir.
Okay, one more transformer,
Yes,
and then infinite bus.
yes, sir.
Okay, you
Yes.
calculate this current first.
Yes,
I
sir.
load, you say I load current, you calculate. Already
Yes.
you know this voltage.
Yes,
That voltage will be, I think, 11/12 unit.
yes, sir.
11
Actually,
by 12.
yes, sir. Where we have to assume the base voltage because the infinite
He
bus.
said it is a 12 kV 100 MVA generator.
Yes, sir. We can assume, but actually infinite bus is also acting as a load now. So we have to. I think we have to consider at impedance of that bus also.
Impedance of that bus. Why you are considering impedance? It will be acting as voltage source only, right?
But sir, infinite bus is supplying load. So where we are going to show that load?
This is the load.
Okay. And this impedance of that load?
What is impedance? It is a synchronous motor.
But sir, in the starting, they are saying that 500 MVA, 500 MVA, 11 kV, 0.8 power factor
this
load.
source is drawing a power of 50 MVA.
Okay.
It's a synchronous motor acting as a synchronous motor now. With
Okay.
zero internal impedance. Why? In the sense it's the infinite bus.
Okay.
Again, you are asking me where to show load impedance.
No,
Huh?
sir. I just want that we have to calculate.
Okay.
Okay,
See,
sir.
you calculate V value.
Yes,
V
sir.
value will be 11/12.
11
because
by
you set 12 kV as a base.
yes,
and you
sir.
assume it at an angle of 0 degree in per unit.
Yes, sir.
Okay. After
Yes.
that, you take the load current.
Yes.
You have already that load details given. Na?
Yes, sir.
Calculate that load current. You will get some magnitude and angle we have to give based on the power factor.
Okay. Means
Okay.
we have yes.
Listen. After
Yes.
doing that, you apply KVL to this loop and you find out this EG double dash.
Okay, sir.
It's a pre-fault circuit.
Yes.
Then repeat the same circuit. Take up the fault wherever they have given. At the midpoint of line is at fault. Na?
Okay, yes, sir.
You draw same circuit again and you take fault at the midpoint of line.
Okay.
Okay. Find out this current, IA double dash. Find
Okay.
out this current, IB double dash.
Yes, sir.
And IA double dash you convert into kiloamperes. IB double dash also you convert into kiloamperes.
Okay.
By multiplying with a proper base.
Okay, sir.
I think the breakers are on the line itself. This is one breaker location A on the line only.
Yes.
This is the other breaker location B.
Okay.
Okay.
Sir. Yes, sir. Actually, sir, IA and IB double dash are transient current, na?
Subtransient fault.
Yes, subtransient fault current. And sir, I think here we have to consider I load current or not. Means add
No,
in that.
see. Once after calculating this EG double dash, load current is already involved, right?
Okay.
EG double dash, how you are calculating with load current only, na?
Yes.
Then again, you no need to make any addition. We are following method 2, subtransient EMF method.
Yes, okay, but sir, in subtransient method, in that time we just added up na I double dash and I load current while
That is
finding
method
fault
1.
current.
That is method 1.
Okay.
Superposition method is one thing, one method. Other method we said subtransient EMF method, second method. Method 1, method 2.
Okay.
I am doing the solution by method 2 now.
Okay.
Because it's easy now for me.
Okay, sir. Yes, sir.
Hmm.
Got it.
Hmm.
Thank you, sir. Thank you so much.
Yeah. Pradeep Kumar. Pradeep Kumar, you do you have any doubt? Jana?
Sir, good evening, sir.
Good evening. Tell me.
Sir, I don't have any doubt, sir. Sir, what about offline classes, sir?
I think government has not given any permission till now to start the offline classes. Okay. Once if they give, they will announce. Okay.
Okay, sir.
Yeah.
Thank you.
Yeah. Fine. So any other doubts? You can raise your hands. Anybody having a doubt, you please raise your hands. Anil.
Hello, sir. Good evening, sir.
Good evening, Anil. Tell me.
I have any doubt regarding this subject. I have a doubt. See the OTS platform.
What is it?
We have a schedule.
I am unable to get you, Anil.
Hello, sir.
Anil?
Am I audible, sir?
No, it's not audible.
Hello, sir. Am I audible? Hello,
No,
sir.
no.
Am I audible, sir?
It's not clear. Your voice is not clear, Anil.
Hello, sir.
Tell me now.
Is it okay, sir?
Yeah.
Sir, I don't have any doubt regarding the subject. I have a doubt regarding on tomorrow's schedule, sir.
Okay.
The schedule is going to given by ACs morning 10 a.m. So in that period, we will have classwork, college classwork.
Okay. You ask that concerned person. You ask your schedule manager once.
Sir, can you please give any mobile number?
You just text me in Telegram. I'll tell you.
Okay, sir. Okay, sir.
Okay.
Thank you, sir.
Yeah. Shamala.
Sir,
Tell
I
me,
have
Shamala.
doubt calculating critical clearing time, sir.
Okay.
So by using this equation d delta by dt equal to root over 2 by area integration of by using that we can find, no, sir?
Yeah, you can find.
But you said we cannot find in disadvantages of this.
TCR. TCR you are asking me.
Yeah.
TCR we can't find, right?
If you find the area, that will be constant, and again we can take this integration.
If PA is constant, then you can find it.
Okay.
If PA is not constant, you can't find time, right?
But we know critical clearing angle, no, sir. From that we can
angle,
find,
I know. Okay, critical clearing angle, you know. Next.
Yeah, from that we can find integration of PA d delta from delta naught to critical clearing angle.
That you can find integral of PA d delta, you can calculate. Then after that, what you will do, tell me.
We know d delta by dt, we will get some constant.
D delta by dt is what? We'll get some number here.
Constant we will be getting, no, sir.
Okay, you will get some number.
Yeah,
then next, what you'll do?
Then we can integrate, no, sir, no?
Whether this d delta by dt is constant throughout that time duration you have taken, throughout that integral duration.
No, it's changing.
D delta by dt is at some angle.
Yeah.
You are not calculating d delta by dt throughout an interval, right?
Yes. Okay, so we cannot.
D delta by dt is not constant value. You are calculating d delta by dt at a particular angle only.
Yes.
Yeah.
But we are integrating this integration of PA delta.
But integral value only will decide how much is d delta by dt at the end angle.
Okay, at a critical angle. Okay. Yeah. Yes. Okay.
Any other doubt you have, Shamala?
No.
So anybody have doubts, please raise your hands. Anybody have doubts, please raise your hands. Rose, tell me, Rosemary.
Hello, am I audible, sir?
Tell me.
Hello, am I audible?
Tell me, please.
Okay. This is in the first chapter. There is a question wherein there is transformer connected to 3 bus bars, which are connected to each other in delta form, having 0.2 pu impedance.
Okay.
And I did not understand how you solved that problem, sir.
That's not a problem. I have taken just an example to tell you about it.
Okay. Sir, what was the conclusion
to tell you about the per phase delta and 3-phase delta, I have drawn the diagram.
Per phase delta. Okay, sir. That was my doubt. Sir, in
It's not
case
a problem actually. It's not a problem. Just to show you where you get a per phase delta. Phase A impedances itself will form a delta sometime.
Yeah.
3-phase impedances will form a delta sometime.
Okay, sir. I understand.
Okay, that per phase delta, 3-phase delta difference I have shown there.
Okay. Sir, in case we have any doubts in power
You can
system.
text me in Telegram or WhatsApp.
Okay. Okay, sir. Thanks.
Okay.
That's all.
Any other doubts? Please raise your hands. Shall we leave for this day?
Sir,
Tell me, Imtiaz.
sir, on 18th July, we have ES exam. Sir.
I will tell you. I'll tell you later.
Okay, sir, but the schedule is 2 to 9. That's
I'll tell you. I will ask him and I will tell you.
Okay, okay.
Yogesh.
Hello, sir.
Tell me, Yogesh.
Good evening, sir.
Good evening.
Sir, actually, sir, there is a little bit confusion in when to take that M in electrical degree and in mechanical degree. Sir.
Where you get it out?
Sir, in general, sir, actually, when in question.
Not general, Yogesh. At what point you get it out? You tell me.
Sir, in problem, sir, today's problem.
Today problem, which slide? Tell me, Yogesh.
Sir, I don't remember the slide, sir, but second or third problem maybe, sir.
Okay, you read that problem once.
Sir, 1 minute.
The calculation of PCR you are asking me?
Yes, sir. Yes, sir. That only problem.
Okay.
Sir, that you have taken that second case. At that time, you have taken in mechanical degree, sir. And in first
what do you want
case,
to calculate there? What do you want to calculate there?
1 minute, sir.
Wherever you have taken electrical M, what you are calculating there? Wherever you have taken mechanical M, what you are calculating there? Just check.
Sir, actually, I have not written the question, sir.
You read solution at least.
Sir, in second, you have told maximum speed seen by the rotor, before which.
Speed means which term? Mechanical or electrical?
Mechanical, sir.
So M value we have to keep in mechanical exam.
Okay, sir.
Okay. Next one. Yogesh.
Yes, sir. Yes.
Tell me.
Okay, sir. Got
it?
Yes, sir. Yes.
Yeah.
No problem. Thank you, sir.
Yeah. Any other doubts? You can raise your hand. So I think nobody's having a doubt. Thank you.